Hi, I'm Christine Alvarado.
I'm Mia Minnis.
And I'm Leo Porter, and we're all professors of computer science here at the University of California, San Diego. Welcome to our specialization on Java programming, object-oriented design, and data structures. But before we start talking about specialization, I want to tell you a brief story. Back in 2008, Google unveiled flu trends, which is this really neat idea that you could predict flu outbreaks based on search terms. What this really just meant was if a bunch of people in San Diego started searching for terms like fever or chills, you could predict an outbreak is coming to San Diego soon. What really made this exciting was that you could predict this long before traditional measurements, which relied on folks going to the hospital or to a medical center.
So that's really cool, but why are we talking about the flu and a specialization on programming and data structures? Well, there are two connections between that story and this specialization. And the first is data. In order to make those predictions, Google needed lots and lots of data. And that's something we have today all around us. From weather sensors to social networks to the human genome, we're practically swimming in data. But it's not enough just to have that data. We need to be able to process it efficiently and effectively. And that idea of processing data efficiently and effectively is really at the heart of software development and computer science.
And it's what you'll be doing in these 4 courses and the capstone project of the specialization. So we'll be talking about object-oriented programming, we'll be talking about both basic and advanced data structures, and then we'll be talking about analyzing the algorithms and thinking about correctness and efficiency. Once we've got the technical background in place, we'll also bring that to the workplace. We'll think about interview skills, and we'll think about avenues for success when you're working in a software engineering or related job. In an academic setting, like on campus here, we would call this course a gateway course. A gateway to what? Well, to computer science as a field. Once you've mastered the foundations, you're ready to delve into whatever you're interested in, whether that be artificial intelligence, cryptography, security, bioinformatics. The world is open to you.
Welcome to this first course on object-oriented programming and user interfaces. In this course, you're going to get to learn how to design graphical interfaces, handle user input, design class hierarchies, including inheritance and polymorphism, and begin thinking about program efficiency.
And you'll be doing all of this in the context of a really cool project. So you'll be reading in earthquake data from around the world in real time, and then mapping that data onto a picture of the real world map. And then what you'll do is make this map interactive, customize it, personalize it, and share it with your fellow learners and the world.
Speaking of personalization, we recognize that you're coming to us with different backgrounds and different comfort levels with programming and computer science. We expect that you've all had some basic course in Java programming, but that doesn't mean that you'll work through this course or this specialization at the same speed. If you're more comfortable and you've had more experience, you'll be able to work through the courses faster and focus on that project. If you need a little more support, that's also fine. There's a path that will provide you with that extra support. Most MOOCs are self-paced, but we're here to provide you with some guidance to find the path through this course and this specialization that's right for you. So, without further ado, this first module is going to dive right into that project that Mia just told you about. It's going to be a lot of fun, so let's get started. Hi, I'm Christine Alvarado.
I'm Leo Porter.
And I'm Mia Minnis.
Welcome. We're so glad you're joining us for the third course in the specialization. We hope you enjoyed learning Java programming from our excellent colleagues at Duke and that you're ready to extend your skills further. We'll start where you left off by looking at the details of designing and implementing classes in Java. We'll start by refreshing some of the basics and then move on to core object-oriented concepts like class hierarchies, inheritance, and polymorphism.
Just like in the Duke courses, you'll be building projects with real-world relevance. You'll notice, though, as your programming skills are ramping up, the projects get more ambitious. In this class, you'll be visualizing earthquake data live on a map. You'll be able to build a core project and then customize and personalize it, and then have the opportunity to share it with a broader learning community. Throughout the course, you'll also hear from industry professionals about how they use object-oriented programming, like you're learning in this class, in their career.
You'll also find a number of new elements in our courses as well. First, we're going to be switching from BlueJ to Eclipse as the preferred programming environment. If you don't have any experience in Eclipse, that's totally fine. We'll give you the help you need when you need it. Secondly, we're going to be introducing a number of new video series. The first of these is called Concept Challenges. In Concept Challenge videos, you'll be learning alongside UC San Diego students as you tackle challenging problems. We'll give you more details about these new video series in the upcoming videos. Lastly, we know you come to us with different programming backgrounds. For those of you who are more comfortable with programming, Feel free to move more quickly through the course, focusing on the programming assignments. For those of you with less experience, we'll give you the help you need when you need it. Many of the courses on Coursera allow you to pick the pace that's right for you. We're helping you find the path that's right for you as well. So let's get started.
Hello again, I'm Mia Minnis, and I'm a professor of computer science here at UC San Diego. And my background and my research is at the intersection between mathematics and computer science, between theory and applications. And what I really like to think about is the power of algorithms. I like to think about abstract ways of organizing and structuring data and then applying them to really interesting real-world problems and solving those problems. And you'll have the opportunity to do just that in the project in this course. And so what this video is about is showing you a prototype of the project and getting you really excited to jump right in and get started developing yourself. So if you take a look at this map over here, you'll get a picture of what you'll be developing in the project. And I'd like to start off by saying that the machine, the engine under the hood that helps us do the visualizations on this map that you're seeing is really thanks to Till Nagel and his team at the University of Applied Sciences in Potsdam and all of the other contributors to the Unfolding Maps library. Part of what we're thinking about and developing in this course is the ability to build large-scale projects using existing libraries, and we're really fortunate to have this library as the foundation for the project. So let's take a look at the project and see what we're doing. You'll see we have a map of the world in front of us, and there's all sorts of markers and features and stuff on this map. Now, don't worry, we will walk you through the project step by step, so don't be intimidated by the amount of information that's being displayed. I hope that you're inspired by the amount of information, and this information is real live data. And so it's really interesting that by the end of this process, you will have a way of interacting with live data. And the data that we have in this project is from earthquakes around the world. It's put together by the USGS, taking seismic information from all over. And what we're doing in this visualization is depicting each earthquake as a either a square or a circle on this map, and then coloring that square or circle on the map based on attributes like magnitude, like depth, and like time, so how long ago the earthquake happened. So all of that is encoded in this key, and you will be able to create and style your own legend as well. And what that key tells us is, for example, that this red square red square marker over here is an earthquake that happened in the middle of the ocean, sort of south close to Antarctica, and it was a relatively shallow earthquake. And the fact that the square is not too big, not too small, means it was maybe an average sized in terms of magnitude earthquake. And then we also have interactivity built into this project, which is really cool. So for example, if we hover on top of that red square, we see a little pop-up that says that this earthquake was magnitude 5.1. Now that's not the only interactivity. So for example, we notice that there's a fair amount of activity going over on in Asia, and we can double click on that part of the world and see that Japan, for example, has a lot of markers around it. And so we could look around and see that some of these earthquake markers have X's on them, and we look at the key and notice that that means that they occurred in the past day. And we might zero in on Tokyo, for example, and when we click on the triangle which depicts the city Tokyo, notice that a bunch of earthquake markers disappeared and only a few remained. And so in this project, you'll be able to implement this interactive feature that when we just want to focus in on a particular city, only earthquakes that are close to that city stay visible and all the others disappear. And then if we click on Tokyo again, everything comes back into view. So that's a taste for the project that you're developing in this course. It may seem somewhat complicated, like it has a lot of features, and it does, but what we'll be demonstrating throughout this course is a really good approach for dealing with large-scale projects, which is to break them up into manageable pieces. And the way that we've done that follows along with the modules of the course. So at the end of each module, the end of module assessment will typically be a part of the project that you'll be implementing that uses the concepts and the ideas that you're thinking about and learning in that module. And so you'll see how each time you acquire a new piece of information or knowledge or skill to do with programming, you'll be able to immediately apply it in this project. So I hope you're as excited about this project as I am, and let's get started.
Hi again, I'm Christine Alvarado, and in this video I'm going to give you some information that will help you choose your own path through this course. So when I'm not teaching, what I like to do is I like to build programs and curriculum that help bring in a diverse set of learners to study and work in the field of computer science. And one thing I've learned about reaching a diverse audience is that you need diverse courses with diverse support structures. So we've engineered this diversity into our course and into the whole specialization. We know that you're coming to us with lots of different motivations, backgrounds, experience levels. So one size fits all is not going to work for this course. And that's okay. That's actually great. We love that you're coming from all these different backgrounds. And what we want is for each of you to feel challenged, because otherwise what's the point? But also never to feel overwhelmed. We want it to be the case that when you feel like you're starting to get overwhelmed, you can always have some more support to help you with your learning. What we've designed is a course where we have different video styles, different video series to help meet that goal. So you're not going to want to take this course by just sitting down and watching the videos one after another. What you're going to want to do is pick and choose a path through the videos that's right for you. And to help you do that, I'm going to tell you about our different video series. But first I want to say that at the end of the day, it's all about what you can do. Mia described this really cool project that you're going to be doing throughout this course, and that's really what we want you to be able to do. So what we care most about are these end of module assessments, which are a lot of the time going to have you building a piece of that project. So if you're feeling really advanced and really good about the material, always feel free to race ahead and just start working on that project or do the end of module assessment. But if you want a little instruction, which most of you will, you'll want to watch some of the videos. So the first video series that I'm going to tell you about is our core content series. So these are the videos that we expect everybody to watch. They're mostly lecture style, and they're going to introduce you to the core concepts and skills that you're going to need to do the end of module assessments. Once you've watched those videos, we're going to probe your knowledge a bit more with our concept challenge series. Again, we encourage most learners to watch these videos, and what they're going to do is they're going to ask you to think about the material you just learned in a new way. And Leo's going to tell you more about these concept challenges in just a minute. The next series that we have for you are additional support videos. Now, we don't expect everybody to watch these videos. These videos are designed for if after watching the core content and doing those concept challenges, you don't quite feel ready to tackle the end of module assessments, you might want to watch these additional support videos. The last two video series that we have, we're really excited about. These are series that aren't designed to deliver content so much as to put the content that you're learning in context. So the first of these series is called In the Real World. And we've got a team of real-life Google engineers talking about why what you're learning is important in their work at Google and in general in the software industry. So that'll be a really good opportunity for you to learn not only why what you're learning is important, but how it's important to these individual engineers. And then the last series that we have for you is called When I Struggled. And what you're going to see in this series is a number of UC San Diego learners, as well as us, talking about our own experience learning the material that you're going to be learning in this course. We'll talk about a time when we struggled with the material that we're presenting. And then we'll talk about how we overcame these struggles. So we hope you'll watch both of those series and that it'll enrich your experience in this course. So again, to summarize, the standard path we imagine a learner taking through this course is that you would watch this introduction with the Google engineers talking about why these concepts are important in the real world. You would go through and watch the core concept videos and perform these concept challenges, maybe watching some videos about when some learners struggled with these concepts along the way, and then perform the module level assessment. And you would repeat that for each module. But if you're feeling more advanced, you might just want to race right through those core concept videos and get to that end of module assessment faster and get developing on those projects. And we encourage you to do that if you're feeling comfortable. And again, if you feel like you need a little more support, you've got those support videos available to you. So anytime you feel like you don't quite understand what's going on, you need a little more help, go ahead and pull out those support videos, and we hope that you'll find the support that you need. So choose the path that's right for you, challenge yourself, and have fun.
Hi again, I'm Leo Porter. I'm a computer science professor here at UC San Diego. One of my areas of research is computer science education. What we like to do in that area of research is look at the best practices for student learning in the classroom. One of the best practices we know about in computer science is peer instruction. With peer instruction, students get to tackle hard problems, discuss it with their peers, and then participate in a large class-wide discussion with the professor. We do this in a number of the courses here at UC San Diego, and we'd like to bring this to you. And we're going to do this through a series of videos known as the Concept Challenges. So let me walk through an example here. So here we have you watching a video. Now let's assume this is from a previous class in Java that you've taken before where you learned first about for loops. So you watch the video on for loops, and then you get done with the video, and the question becomes, well, did you learn it? I mean, there's certainly areas of the video that you probably understood well, but there may be some areas that you didn't understand as well. So the best way to find out whether or not you really understood the material is to solve problems. So we're going to ask you questions to help elucidate what areas you're strongest in and which areas you're not. So a question might look something like this. So you've just watched a video again on for loops, and here's an example for loop. And the question here is asking how many times does I less than 10 execute? Now the reason we'd ask a question like this is because we expect a number of folks will get this wrong. In fact, we want you to get a number of these questions wrong because that means it's an opportunity for learning. What we expected is a lot of novice learners would answer B here. They would say that the loop executes 10 times, so I less than 10 will execute 10 times. But the condition I less than 10 actually executes 11 times. And we'll talk more about that as we go forward. So after you solve the problem on your own, after you've tackled the problem yourself, what you're going to then see, or what we hope you can do, is work with other learners around you. So if you have anyone else in your neighborhood or friends who've taken the same course, this is a great time to get together and discuss the question. And by discussing it with your friends, you're going to find out, one of you might say, well, wait a second, does it execute that last time? And then you realize, oh shoot, yeah, it does actually execute 11 times. But if you don't have some friends around you, what we're going to give you is also a series of videos where you're seeing UC San Diego learners discussing the question. And there you'll hear them say things like, well, wait a second, it's really easy to forget that last check. Oh yeah, so the answer must have been 11. And then after you hear the UC San Diego learners discussing it, you're going to hear one of our explanations. So the full course of one of these questions is going to look something like this. You're going to pause, try to solve the problem yourself. You're going to discuss the question with other learners around you if you can. You're then going to watch a video of the UC San Diego learners discussing it, and then you're going to confirm your understanding by listening to our explanation. By solving these kind of hard problems, you're going to understand your material much better. You're also going to identify areas that you might need improvement, and that's where more support videos and the forums come in.
Hi there, my name is Adriana and I'm a software engineer for the shopping team at Google in Mountain View.
Hi, my name is Roshni and I work on identity and authentication at Google.
Hi, I'm Landon Judkins and I'm a software engineer at Google's Pittsburgh office.
Hi, my name is Nita Yi. I'm on the Google Fiber software engineering team.
I'm Kadechi and I'm an engineer on the Google Docs team.
Hi, I'm Matt Healy. I'm a Google engineer working on conversational shopping in our Pittsburgh office. Welcome to the Intermediate Programming Specialization.
Now that we've given you an overview of the various features of our course, what we're going to do now is just dive straight into objects. Now for some of you, this may be a bit of a review, and we're providing this just so that we're all on the same page going forward. But if you feel like it's too much of a review, feel free to skip ahead to the practice quiz at the end of the week.
All right, in that first module, you were introduced to the project that you're going to be doing throughout this course, and we hope that you think it's as exciting as we do, visualizing this geospatial data. In this module, though, we're going to be stepping a little bit away, and we're going to be talking about some of the concepts that underlie the code that you're going to be writing. So by the end of this module, you're going to be able to motivate the use of classes and objects in programming. So why do we want to use classes and objects when we write our programs? You'll be able to write classes in Java and then create instances or objects of those classes. And you'll be able to describe the parts of a class like member variables, methods, and constructors. So in order to motivate the use of classes and objects in programming, I want to go back to my favorite definition of computer science. And of course, software engineering and software development, which is what we're focusing on this course and this specialization, is a major part of computer science. So my favorite definition of computer science is that computer science is the science of using and processing large amounts of information to automate useful tasks and learn about the world around us. Of course, all using a computer, because none of this would be possible if we didn't have the computational power that the computer affords us. And I'm going to zero in on this line in the definition, this idea of using large amounts of information. These programs that you're going to be writing and programs that people write, if you think about programs out in the world, deal with huge amounts of information. So much information, it's almost impossible to get your mind around it. So one of the fundamental questions in writing programs is, how do we organize this information? How do we organize it in a way such that our programs are easy to write, easy to maintain, and easy to debug? Well, the philosophy behind object-oriented programming is to build our programs in a way that match the problem that we're trying to solve. So if we go back to our project and the problem we're trying to solve, it's to visualize geospatial data on a map. And if we think about what's involved in solving that problem, we can think of lots of real-world objects and entities that are part of this problem that we're solving. So we can think of things like the map itself. That's an object that we're all familiar with. Shapes. Shapes are objects that have properties. We could talk about the shapes of the countries, for example, in this map. Locations in the map. Colors of the objects in the map, even the window in which the map is displayed. Plenty more objects as well, but these are all ideas that have real-world counterparts. And the idea behind writing an object-oriented program to solve this problem is that we're going to structure our code around these real-world concepts. So in order to build our code in this way that matches the real world, we're going to design these things called classes. And what classes are just custom data types that we get to define to match the problem that we're trying to solve. Now, of course, you're familiar with classes because you've been working with Java for some time now, but we're going to talk about really the details of creating and using classes. So a class is a new kind of data that we, the programmer, get to define. And it's kind of like a factory. It can produce pieces of data with a template that we get to define. So I'm going to use this factory icon when I talk about class definitions. On the other hand, an object is the thing that comes out of this factory. It's a piece of this data with this custom type that we've defined, and some associated functionality that goes along with that data. And I'll represent the objects with this little symbol here to represent the things that are coming out of the factory as we create objects using our classes. So you can think of this like a real-world factory, right? Like a car factory. A car factory knows how to produce, say, one kind of car, and it can produce many of that kind of car. And once the cars are out in the real world, well, at first they all kind of look the same, but then each individual car can be customized and it can be changed in its own way without affecting all the other cars that came out of the factory. The same thing's going to happen for our classes and our objects in our Java programs. So we're going to go through an example of creating a class, and the class we're going to create has to do with this map example that we've been working with. So here's a map of the world. I'm going to zoom in on one particular place in the world, which is where this orange box is, which is approximately where I'm standing right now on the campus of UC San Diego. So here's the University of California, San Diego campus, and I'm about right here on this map. So what I want to do is I want to build a class that can represent my location in the world, or can represent anyone's location in the world. So the question I have to ask myself is, what do I need to know in order to represent a location? Well, for this example, I'm going to represent the concept of a location using two pieces of data, the latitude and the longitude of this location. And in my case, for this location right here, you can see these are approximately my latitude and longitude coordinates. So let's define a class that represents this notion of a location. Here's my class definition. So I'm telling Java that I want a new class called simple location. And you can see that on the top line in this declaration. I say public class simple location. Simple location is the name of the class. The keyword class tells Java that I'm creating a new class. And public, which we'll talk about more in some of the next videos, just means that my class is public to the world. Anyone can use it. Inside, after that first curly brace, is the definition of my class. Now, before we look closely at the definition, I want to point out that all of this code has to exist in a file called simplelocation.java. That's just a rule that Java enforces, that when you're creating a class, you have to put it in a file that has the same name as the class. And that's if the class is public, which our class is. So all this code is in a file called simplelocation.java. So let's look a little closely at the definition for this class. Up here, you can see the data that I have associated with my simple location. I have a latitude and a longitude, and I'll represent both of these using double type variables. These are what are called member variables. These are variables that exist throughout the class that represent some essential pieces of data that I need to represent my simple location in this case. And notice that they're declared outside of any methods, but inside the declaration of the class. So they come after that open curly brace for the class, but not inside any particular method. My class also has some methods associated with it. So it has, for example, that method that you see down there at the bottom, the distance method. And what the distance method does is it takes some other simple location out in the world as a parameter, and it returns the distance between one simple location and the simple location that's passed in. So that's something that my class can do. So these are the methods. These are the things that my class can do. And I want to zero in now on this special method called the constructor. So this is the constructor, and this is a special method that gets called when my objects get created. So when I ask Java to give me a new object of type simple location, it's going to call this method here, which is called the constructor. And the reason that you know it's the constructor is that it doesn't have a return type. So it simply says public, and then the next word in the declaration of this method is just the name of the class. So public, simple location, that's my constructor. This constructor happens to take two arguments, and it takes the values of those arguments that are passed in and stores them away in those member variables latitude and longitude. Now you might see this keyword this.latitude, this.longitude. You might be wondering what it is. We're going to talk about that in just a couple minutes. So all of this together is my class declaration, simple location. My class has two member variables and a couple of methods, and again, it's in the file simplelocation.java. So now how do I use this class? Let's take a look at some code that actually creates objects of type simple location and does something with them. So now I'm going to go over into a totally different file. I'm going to go into a file called locationtester.java inside a totally different class, because everything in Java has to be in a class. And I'm going to look at a main method inside that class. This main method is fairly simple. It just has 3 lines of code. And the first 2 lines of code are creating new objects of this type simple location, the class that I just wrote. So you can see here that I declare 2 new variables, UCSD and Lima, and I'm creating 2 new simple location objects to represent the location of where I'm standing here at UC San Diego, and then the location of Lima, Peru. When I call new, and then say simple location, and then have the parentheses and pass in those arguments, what that's doing is that's going over into the simple location class definition and calling the constructor. So those arguments you saw being passed in, those are going to go in as arguments to this constructor, which is going to store those values away inside the class, the object that just got created. So I call the constructor twice, I get 2 new objects. Then I can use those objects in some code like I do down here. So what I'm doing here is I'm taking my UCSD simple location object, and I'm calling the distance method on it, passing it in the simple location object that represents the location of Lima. So let's take a look at how that works. When I call that method, it's going to invoke this method distance that's inside the class simple location. All right, so let's look in a little bit more detail what's going on here so we can understand the difference between UCSD and Lima. So when I call UCSD.distance and pass in the parameter Lima, like I mentioned before, it invokes that method called distance inside the simple location class, which you can see right here. Now I'm showing you just a little bit of what the body of that method might look like so that I can illustrate a couple of points. We're comparing the distance between two simple location objects. One of those objects, Lima, is passed in as an argument to the function, and that's going to be stored in the parameter other. So I can see that other is used inside the body of the method when I get its latitude and its longitude. But what happened to UCSD? How are we getting the latitude and longitude of UCSD? That's where the keyword this comes in. This refers to the calling object, which is the object that called the method or on which the method was called. So in this line of code, UCSD.distance and then pass in Lima, UCSD is called the calling object because it's the object that occurs before that dot. So when I'm inside this method, this will refer to the location of UCSD. So that way I can get the latitude and longitude of where I'm standing here at UCSD and compare it to the latitude and longitude of Lima, Peru, and return the distance. Putting it all together, when I run this code by compiling it and running it, I see that the distance between where I'm standing now and Lima, Peru is approximately 6,568 kilometers. So those are some object basics. In the next couple of videos, we'll introduce you to some more subtle details and interesting things you can do when creating classes and objects. All right, so when I was first learning about objects, I was taking this class, and the professor was at the front of the room talking to us about objects. And he kept saying, objects this, objects that, and I just kept getting more and more confused. I was sitting here thinking, objects, they're like things. What the heck is an object? And finally, I got up the nerve to raise my hand and ask the professor, what is an object? And he kind of looked at me, this look on his face like, oh dear, where have I gone wrong with this poor student that she doesn't know what an object is? But he was very patient with me, explained what an object is, and after he explained it, I realized that I actually knew more about objects than I thought. I just hadn't necessarily associated the word object with the concept that I already knew a fair amount about. So that was kind of an example of vocabulary tripping me up. And as I learned a little bit more and got more sophisticated with designing and implementing objects, it all made more sense. And I look back now and I wonder how I could have possibly struggled with something that seems so simple to me now. But that's how it is when you're first starting out. Okay, now that you know the basics of creating classes and objects in Java, let's talk about overloading methods, which is another thing that you're going to do and work with a lot as you work with classes and objects. So by the end of this video, you'll be able to give examples of what overloading methods is in Java. You'll be able to explain how to overload methods and how not to overload methods in Java, and you'll be able to explain why it's useful and why we want to do it. Let's go back to our simple location class that we worked with last video. So we saw this class, here it is. It has a couple of member variables. It has a constructor, and it has a method called distance. Of course, you know by now that it must be in a file called simplelocation.java. Now let's say right now we have one constructor. It allows the user to create objects of type simple location by passing in a latitude and longitude. But let's say that the user doesn't want to always have to pass in a latitude and longitude, and they want to be able to create simple location objects without passing in any parameters. Right now, the user of our class can't do that because there's no constructor defined that takes no parameters. But we can fix that. We can create a new constructor that takes no parameters and creates still a new simple location object. Now, you might wonder, well, where should the simple location object be if the user doesn't give us any parameters? And since I'm here at UC San Diego, I'm going to create my class that will always create simple location objects here at my location at UC San Diego, unless the user tells me to create it somewhere else. So what I've done is I've added a new constructor that takes no arguments, which by the way is called a default constructor. It's just the constructor that you can invoke without passing in any data at all. and it will give my parameters, it will give my member variables, latitude and longitude, these default values, which is the location of where I'm standing right now. I still have my other constructor, which takes the two arguments, latitude and longitude, lat and lon, and those two constructors can exist happily together in the same class. This is exactly what I'm talking about when I talk about overloading methods. So I've now created a class where my constructor has been overloaded. There are two different copies of the constructor that take different numbers and types of arguments. They both do the same thing, more or less, in that they both create a new object, but how they assign values to latitude and longitude differs slightly. So I can not only overload constructors, I can also overload the methods in my class. So before I had one method called distance, and it took in as a parameter another simple location object. And that was fine, but maybe I don't want to force the user of my class to have to create a whole simple location object just to find the distance to another location. So I can overload the distance method by creating another version of it that takes in two parameters, other lat and other lon. So instead of having to create a whole new simple location object just to pass it into the distance function, the user of my class can now call my distance method by passing in two parameters representing the latitude and longitude of the place that they're trying to find the distance to. So two examples of overloading. Why do we care about overloading? Why is this useful? Let's take a look at how you're going to use it extensively in your project. So this is a little snippet of code that we looked at back in Module 1 that uses this unfolding maps library to create a new map and display it to the user. And what it does is it creates a window of size 800 by 600 and then puts a new map inside that window. And when I run it, I see something like this. I've added a line of code that zooms in on San Diego, so you see San Diego rather than the whole world. So that's what I see when I run this code. But what if I decide that I don't really like the fact that the map takes up the whole window? I'd like to shrink the map down slightly so there's a nice border around the edge of the map. I can do that. And I can do that by invoking a different version of the unfolding maps constructor. So this is an overloaded version of the unfolding map constructor that takes 4 additional parameters. So my original call to unfolding map just took 2 parameters. Now I'm calling the unfolding map constructor that takes 6 parameters total. And these 4 additional parameters I've added specify the x and y position of where the map should appear in the window, as well as the width and height of the map. So when I run this code, what I see is a window that has a nice border around the map that it displays because the map is slightly smaller than the window size. So this is pretty useful. But you might wonder, well, how do I even know? How do I know what constructors are available to me? That's where the Java documentation comes in. So you can go to the unfolding map Java doc, just like we showed you in Module 1, and you'll see all the constructors detailed there. So here's the first constructor we called that took 2 parameters, and you can see what it does and what those parameters are. And here's that second constructor that we called that took those 6 parameters. And you can see that the second parameter is the x position of the map, the third parameter is the y position of the map, and so on and so forth. And if you do go to the unfolding map documentation, which I encourage you to do right now, you'll see that there are actually like 8 or 9 different overloaded constructors for unfolding map. So you can create unfolding map objects by passing it a wide variety of information, and each of those constructors will do something slightly different. So before we end this video, I want to caution you against something that seems really useful, but is actually not possible in Java. So you might think that it's a good idea to overload the distance method instead of by changing the parameter list, by changing the return type. So let's say you want a distance method that returns a double type, but you also want a distance method that's slightly less precise and returns an integer type. So you say, oh, I'll just overload the distance method and make the other one return an integer. Unfortunately, that is not allowed. You can't do that. Java will complain. You have to have some difference in the parameter list when you overload a method. You're not allowed to have a method with the same name and the same parameter list and a different return type. And the reason for that is a little bit beyond the scope of this course, but it has to do with how the compiler works. At compile time, Java-C, the compiler, has to decide which version of the overloaded method you're actually trying to call. And it does that by using the parameter list. It can't do that by using the return type alone. So Java doesn't let you do this type of overloading. So that's all for overloading. And in the next video, we'll talk about a few more details of objects and classes. Okay, in this next video, we'll layer on some more details of building classes in Java. We're going to talk about the keywords public and private and protecting your data and methods inside your classes. So by the end of this video, you'll be able to describe what those keywords mean and their effect on who can access the data and methods inside your classes. And you'll be able to also talk about how to use getters and setters to allow customized access to the data inside of your classes. So as usual, we're going to go back to this simple location class that we've been developing. So this class, as you know, has two member variables, latitude and longitude. And we originally declared them both to be public. So let's take a closer look at what that means. What that means is that anyone can access these member variables from any class at all. So when I create a new variable of type, a new object of type simple location, I can get at the member variable latitude or the member variable longitude to read its value or to change its value. So if I go over here into the location tester class, I see that I've created two new simple location objects. I can change the value of latitude inside the object stored in Lima. That's totally okay because that member variable is declared to be public. So I can access it from anywhere. Similarly, for methods, I've declared my method distance to be public, which means that I can access that method anywhere. So over here, back in my location tester class, I'm calling the distance method, which is also totally allowed, because again, that method is public. On the other hand, if I were to declare my member variables private, what that would mean is that those variables would only be accessible from within the simple location class itself. So only inside this class definition, nowhere else. No one else has access to either read or write those variables. Same thing goes for methods. If I make a method private, I can only call that method within the class I'm defining and nowhere else. So if we look at what that means, if we look at this constructor, these two lines of code are just fine. I'm using this.latitude to access the member variable latitude and this.longitude to access the member variable longitude. Perfectly okay because I'm inside the class simple location. However, if I go back to that class location tester and look at this line here that's trying to change the value of latitude in the simple location stored in the variable Lima, that's no longer allowed because now I've said that that latitude variable is private. It can only be accessed from within the simple location class, and we're no longer in the simple location class. We're now over here in the main method inside location tester. So that would cause an error. So it's actually, despite this error that just got caused, it's actually a good idea to make your member variables private. Because you, as the class designer, want to really have ultimate control over who gets to see and change the data that's stored in each object of the class that you're creating. So as a rule of thumb, always make your member variables private. Now, methods can either be public or private, depending on whether they're for world use, like that distance method, or whether maybe they're just helper methods that are designed to be used only within the class itself. We'll talk more about that as we start talking about more sophisticated class design. But for now, let's focus on this rule of thumb that we should make our member variables private. So if our member variables are private, nobody else can access them. They can't see their values, they can't change them. So that seems like a bit of a problem. We probably sometimes want to be able to give a little bit more access to the member variables in our class than that. So the way we get around that problem is through the use of what are called getters and setters. So this is an example right here of a getter. And the purpose of a getter is to take the value of a member variable that's private and expose it outside of that class. So you can see this getter here gets the value of the member variable latitude, which is private, and returns it to the outside world. So the variable itself is still private, but now I can gain access to that variable by calling this getter. So if we go back over here to the code, we can see that if I try to access the variable directly, say print it out, I get an error. But when I call that getter method, that's perfectly fine. So I can actually get access to the value of that latitude variable through the getter. And now notice that in this code so far, going back here, I haven't provided my user of my class with any way to actually set or change the value of latitude. And that may be what I intend as the class designer, that once that latitude variable gets set in the constructor, I may never want anybody to change it again. And in that case, I would just simply provide a getter and not provide any way for the user to change the value of the variable. But let's say I actually do want to allow somebody to change the value of the variable. In that case, I would provide what's called a setter. So here's my setter. What it does is it takes in a value, lat, and it changes the value of the private member variable to the value that was passed in by the user. So a setter sets the value of a member variable, usually a private member variable. So now I've got a getter and a setter for my latitude variable. And you might be thinking, I would be thinking if I were you, why didn't we just make that member variable public? If we're exposing the ability to change it and read it, we might as well just make it public, right? So here's why. Having the getter and the setter allows us more control as class designers. So let's say we want to allow the user to change the value of the latitude, but we're a little bit unsure that the user of our class will know what they're doing when it comes to legal latitude values. So we can put some precautions in place that allow the user to change the value of that latitude, but only to values that are legal latitude values. So the way we would do this is we would modify our setter to, rather than just blindly accepting whatever argument was passed in, we would have some checks, some logic inside of that method that said, okay, if it's out of range of negative 180 to 180, then that's not a legal value. So we're going to print out an error, inform the user of our class that, hey, you tried to set your latitude variable to an illegal value. That's probably some bug in your code, so you should probably go check that out, and not change the value that's stored in the latitude variable. Otherwise, we can happily accept the value because it's within the legal range and change the value of that variable. All right, so that's it for the details of classes and objects. You now know all the basics of creating classes and objects. So next you'll take a short practice quiz and then move on to the next module.
As a software engineer, I use the words private and public every day. Even though it might sound trivial, it's extremely important to get those right. You make everything private and you end up with code that cannot interact with anything else. You make everything public and you end up with code that's extremely vulnerable, maybe even useless.
Congratulations on completing the first week of the course. We're going to continue right where you left off, and we'll start diving into memory models and scope. Again, this might be a review for some of you. If you feel like it's too much to review, feel free to skip ahead to the graded quiz at the end of scope. After completing scope, you can get started with the programming project, and you'll build your first application in Unfolding Maps. The programming assignment for the first course module is really aimed at just getting us up to speed and running with Unfolding Maps. I know that many of you are eager to get programming, but before we can get there, you're going to have to get Unfolding Maps set up and running in Eclipse first. So please follow through our text and our video guides to help set up Unfolding Maps for your system, and then turn to the forums if you run into problems. But before we get there, what I want to show you is an example of a finished programming assignment for this first module. We'll give you the code to create the map on the left, which is centered on us here at UC San Diego. Specifically, we're really right about here. Notice that on this map, I'm able to zoom in and out. So zoomed out, I'm able to zoom in, I'm able to zoom in towards UC San Diego, and we're really right over here. Now, being able to zoom like this is pretty amazing. A lot of work goes into making something like that happen, including getting the map data from Google Maps to the handling of my mouse scrolling in and out. These amazing features are really just part of the libraries and Unfolding Maps and processing, which is why we're using these libraries for this project. All right, back to our assignment. We're going to give you the code to produce that image on the left, which is our map on the left, which is zoomed into San Diego. What we want you to do is create the map on the right, which we zoomed in to where you live. Now, I live in San Diego these days, but I grew up in Pullman, Washington, which is on the east side of Washington State, and Washington State's on the west coast of the United States. So this is really just a small programming assignment just to get started with unfolding maps. The big step is really just getting unfolding maps and working on your system. So select the right video guide for installing unfolding maps, Java, and Eclipse on your personal system. And I'll see you again for the assignment walkthrough.
In this video, we're going to show you how to get the starter code for the project and get it set up in Eclipse. So you've probably already found this setup document, which is in week 1, getting started with the project. It's talking about how to set up Java Eclipse and the starter code. And I'm going to assume that you've completed part 1, which is to set up Eclipse and Java. And we're going to jump down to part 2. So about halfway down the document, this is the part that we'll be going over, getting and setting up the starter code. So you can download the starter code from this link here. And what you want to do is download it and unzip it somewhere on your system. And the only restriction is we want you to put it somewhere that is not inside your Eclipse workspace folder. So once you've downloaded and unzipped the code, you'll go over here into Eclipse, and you should see a blank workspace if you haven't done any other coding yet in Eclipse. So what you'll want to do is to get the starter code set up, you go to the File menu, and then in the File menu, you'll click Import, and that'll open up a new window. And what we want to do is we want to import an existing project into our workspace. So that's under General, so I expand the General tab if it's not open already. Then I'm going to click on Existing Projects into Workspace, click Next. And then what I have to do is tell Eclipse where to find the code that I want to import. So I go over here and I browse, and I'm going to browse back to where I saved and unzipped that starter code. And I just put it on my desktop. So I'll go up here and find my desktop, and here it is down here at the bottom. So I select the UCSD Unfolding Maps directory, and then I click OK, and you can see that it imported this project, or it gave me the option to import this project in this window here. So the only other really important thing that you need to do is make sure that this Copy Projects into Workspace option is selected. We actually want to copy the files, the source code, and everything else from wherever we saved it into our workspace directory. So just make sure that's checked. And then you click Finish. And then what you're going to see is that our code and everything else has been successfully imported into our workspace. So you can see that now I have this starter code. If I expand it out, you can see that there's a whole bunch of files associated with this project. And if I open up the source code, I can see that it's divided into these organizational modules, basically called packages. So there's one package for every module that has a programming assignment. So module 1, 3, 4, 5, and 6. And that's where you'll find the starter code. So here we can see the starter code for module 1 in a file called helloworld.java. And I can open it by double-clicking on it. And I can even run this starter code by clicking this button here and selecting Run as Java Applet. You might have multiple choices there. If you do, just select Java Applet. I won't run it right now because I don't want to give away what it does. I'll let you wait until you start on the project to figure out what that does. But that's how you would run it. And then the other thing to notice is that there's this package called demos. And if you look at that, that's going to have a bunch of demos that we're going to be working with throughout the course in the videos. So if you want to run some of the code that we talk about in the videos, look here in this demos folder. We don't have all of it here, but we do have some of it. So you might find it here. All right, and so the last thing I want to tell you about is where to actually find all of these files on your file system. So remember when we checked that import into workspace button, that option when we imported the whole package? Well, what that did was it actually copied all of our files into our workspace. So if you go over here into our file finder, you can see that this folder here, UCSD Unfolding Maps, that's where we can find all of the actual files associated with our project. And you can see here in the source folder, and for example, module 1, this is where my actual .java file resides. But you'll be editing it through Eclipse. But if you want to know where it actually is, here it is. Okay, now you're all set up and ready to go, so have fun with the project. Okay, so now that you've learned how to create classes and objects, in this video we're going to show you a really powerful way of reasoning about your code and about the variables in your code that's called drawing memory models. So by the end of this video, you'll be able to draw memory models for variables that contain primitive type data like ints and doubles and floats, and you'll be able to update those memory models to reason about the values of those variables in your code as your code runs to try to figure out what is your code actually doing. Now, this is a really interactive lesson, so we want you to get out your pencil, get out your paper, and draw these memory models right along with us. Now, when I ask my students to get out pencil and paper in class, they kind of look at me like I'm crazy, like, this is computer science. Why do I need a pencil and a piece of paper? And I actually usually walk around the room and say, hey, get out your pencil, get out your paper. Now, obviously, I can't do that with you, but if it helps, imagine me kind of knocking on your door, knocking on your car window, asking you to get out your paper and your pencil to draw these memory models right along with us. It'll be a lot more interesting, and you'll learn the concepts a lot better. So, to warm us up, let's look at this piece of code, and what I'd like you to do is just trace through this code and tell me what are the values of the variables var1 and var2 at the end of this code. In other words, what does this code print? All right, so if you got that example right, great job. This actually turns out to be a somewhat tricky example that a lot of people have trouble with. So if you did have a little trouble with it, don't worry, because what we're going to do now is we're going to use this example in order to illustrate this idea of drawing memory models so that you'll be able to get questions like this right forever, so for all of the future. And why is it important to be able to reason about code like this rather than just write code? Well, it turns out that people who are better at writing code are also better at reasoning about their code, and vice versa. So practicing reasoning about code is a really important skill in order to become a better coder and software developer. So let's step through this code line by line and draw the memory model for this code as it runs. Let's start here on the first line. That first line is a variable declaration. What we're actually telling Java is, hey Java, I want some new space to store a value of type integer. And that space I'm going to label with the label var1. So in my memory model, what I'm going to do is I'm going to draw a box. That represents the space that I'm going to have to represent this variable, and label it with the name of the variable. So there we go, and you should do the same on your piece of paper. The next line of code here is an assignment statement. So what that's telling Java is, hey Java, take the value on the right-hand side, which in this case is 52, and place it into the variable on the left-hand side, which in this case is var1. So in our memory model, we'll take that 52 and we'll put it in the box for var1, which is where var1 stores its value. All right, next line, another variable declaration. So we need another box labeled with the new variable name, which is var2. The next line is another assignment statement. Now this is slightly more complicated than the last assignment statement because the thing on the right-hand side is not just a number like 52. It's another variable. So what we need to do is we need to get the value out of var1 so we can then place that value into the variable var2. So we look in the box for var1. We see the value there is 52. So what we'll do is we'll copy that value over here into the variable var2. So now var1 and var2 both store the value 52. Now this is a really important point, that var1 and var2 are not the same variable. They're not tied together in any way. They just temporarily store the same value because this assignment statement told Java to take the value that's in var1 and put it into var2. But there's no connection between these two variables, which you can see in the memory model diagram. So now when we go on to the next line, which is another assignment statement, and take the value 127 and put it into var1, you will see that only the value of variable var1 will change. So I'll take that 127, replace the 52 that was already there, and the new value of var1 is 127. Now we're down here at the last line, which is this print statement, and all that's left to do is read the values out of those boxes for the variables. So when I print out var1 and var2, they'll have the values that you see in the boxes of 127 for var1 and 52 for var2, and this is what prints. So those are some simple memory models using just primitive type data, and in the next video we're going to show you how to get more complicated using objects.
What we get to do in this video is take the concepts that you talked about with Christine and apply them in an example so we can really work through them together and see how they help us step by step. So the key concept that we're going to be developing and thinking about here is that of memory models, and we're going to see how they apply for this code snippet that we'll trace through now. So let's think about what happens in the first line of code. First things first. And in this first line of code, we both have a variable being declared and then a value being assigned to that variable. So in our memory model, whenever we have a new variable, we want to denote that by writing the name of that variable and then drawing a box where we'll record the value of the variable. Okay. So we've drawn var1, we've drawn that in our memory model, we've got a box for it, and the value that's being assigned is the right-hand side of the equals over there, which is 17. And so we put that in the box. Cool. Now we can move on to the second line, and in the second line, well, we're declaring a new variable, so we have to update our memory model, which means that we need to write var2, our new variable that we just declared, and give it a box as well. And now we think about what goes into this box, and we look at the right-hand side of the assignment statement, and the right-hand side of the assignment statement says we want the value of var1 plus 1. But the value of var1 is recorded in our handy memory model right over here. It's 17. And so we add 1 to that, and the new value of var2 is 17 plus 1, which is 18. Cool. Okay, 2 lines done. We go into the next line. And the next line is now just a pure assignment statement. And what we want to remember is that for this assignment statement, we're taking the value on the right-hand side of the assignment statement. And what we'd like to do is assign that to be the new value of the variable on the left-hand side. Okay, so on the right-hand side over here, we've got var2 plus 1. And so we can look in our memory model for the current value of var2, which is 18. And so the value that's on the right-hand side here is 18 plus 1, or 19. So that's what's over here, this value. And what we do is we take this value and we copy it into the box for var1. So that means that var1's new value is that 19. Okay. And now we get to display our results. We get to display what we've done by printing out. So we've got the system.out.println command, and what we're writing here is var1 colon space and then the value of var1, which we read off our memory model, and then we've got a comma, a space, var2, and then I'm running off the screen, but I'm going to put the next value right over here, and that's the value that we can read off of var2, 18. And we're done. Yay. So in this support video, we're going to take our work from the previous one. We've traced through some code, and right now what we'd like to do is test it and test our understanding. So by the end of this video, you'll be able to write testing code to verify the output of your trace of some Java code execution, and you'll be able to use Eclipse to run that code. So make sure that you've got Eclipse open and we can work together as we're developing the testing code. So we start with an example, and this is a piece of code that we used in the previous video, and we've used memory models to understand and to conjecture what's going to happen at the end of running this code. So doing that, if you think back to the previous video, you saw that we used memory models to expect that the system will print var1 colon 19 comma var2 colon 18. Okay, great. We've made this guess. We are pretty confident. We know how to use memory models, but we'd still like to check. And when we get to more complicated code that we've traced through, it's good to have another way of checking our understanding. And so a very good technique to doing so would be to put the code into a program that we can actually run. All right, so what that means is that our code needs to be in a class, because in Java, everything is in classes. And so we can create a new file in Eclipse and call that file, for example, int assignment tester.java. Tester is indicating to ourselves that this is a testing class. And so we define a new class, public class int assignment tester. Remember that the class name has to match the file name. And then in the main method for that class, we stick the code that we want to test. Because when we run this class, when we run the code for this class, we know that the main method is going to be what's being executed. Okay, so we've defined this new file, we've put the code that we want to test into the main method, and now in Eclipse we can run the code. And so remember that in order to run code in Eclipse, we have at least two choices. We can use the icon that has the white triangle and the green circle, or you can go into the Run menu and run the code in that way. And then in the window right underneath where we put in the code, we'll be able to see the output and be really happy because it matches what we expected.
All right, something I struggled with when I was learning computer science, and also I still really kind of struggle with it today, is just simply compiling and running and testing my code. I'm not really sure why, but when I started out programming, I was just terrified to compile and I was terrified to run because I was so afraid of the errors that were going to be in my code. And of course, we all have errors in our code, but it was a visceral fear. And I always thought, oh my God, like the computer's going to explode or something, and I would just not do it. So it would lead me to write these huge methods and these huge programs before I compiled or ran anything. And it was a big mistake. So I got over that just by kind of practicing more, hitting that compile button and the run button, and realizing that nothing happens. Your code breaks and you fix it, and it's not a big deal. So that's what I've learned, but it's still kind of scary for me sometimes. So in the last video, we drew memory models using only primitive type data. In our case, last time it was integers. But this time we're going to add objects into our memory models. So our goals for this video are the same basically as the last time, only this time you'll be able to draw memory models using object type data and primitive type data, and reason about code that uses both primitives and objects. So before we begin, let's just give an example of the two different types of data. You're probably already familiar with this from your earlier courses in Java, or courses in Java. But Java has two fundamentally different kinds of data. It has primitive kinds of data, which consist of only 8 types. So Boolean, byte, short, int, long, float, double, and char. Those are the 8 primitive types of data in Java. Everything else is an object, whether it's an array or a user-defined class or a class that you find in a library. Everything else is an object. So obviously learning how to add objects into our memory models is going to be really important for reasoning about code. So here's a short snippet of code right there, just 2 lines that show an example of both a primitive type, the integer, and an object type, which is our class simple location, which we defined in the last lesson. We're going to reason through a short snippet of code that combines both integers, primitives, and these objects of type simple location. We're going to step through this code the same way we did in the last video and draw the memory model as we go. So to get things started, we've got a nice, easy variable declaration and assignment statement. And you already know how to handle this one. This is just an integer, just like we looked at before, var1. We create a box. We put the value of the variable in the box. In this case, it's 52. So that was easy, no problem. Let's go on to the next line. The next line turns out is pretty easy as well. All it is a variable declaration. So we handle this in the same way, regardless of the fact that it's actually an object type variable. That doesn't matter for our variable declaration. So we're going to make a box and label it with the variable's name. There it is. It's this next line where things get interesting. This is an assignment statement. And what we're doing is we're creating a new instance or a new object of type simple location. And then we're setting the value UCSD equal to whatever happens when we create that new object. So now to understand what's going on here and how it's going to affect our memory model, we need to look a little more closely at what happens when we create a new object in Java and what's going on in your computer's memory. So when we say new simple location, what Java's doing is it's creating a new object, which means it's allocating some space in your computer's memory to store that object. So let's take a closer look. What it's doing is creating that object, which is allocating some space, and it's doing that in a part of your computer's memory called the heap. So it creates that new object in the heap, and then what it does is it puts that object at some location in the heap that has some address. It's not necessarily, we don't know where Java chooses to create that object. So we'll just represent that address where Java creates that object with this little @34. So that object is at location 34. That's just a random number that I picked off the top of my head. It's wherever Java happened to create that object in the heap. So now what happens is when we've created that new object and Java creates it at location 34, what it actually does is it doesn't place the whole object inside the box for UCSD. It places a reference to that object in the box for UCSD. In other words, it places the location of the object, wherever it's stored in the heap, into the box for UCSD, and that's called a reference. So now I said 34 is just kind of a made-up number. I don't necessarily know that this simple location object exists at the location 34. So typically in my memory model diagrams, rather than making up arbitrary locations for all of my objects, what I'm going to do is I'm going to draw an arrow from the box for the variable UCSD to the object that's created in the heap. But remember that this arrow really just represents this reference, this number that represents the address, or something like an address, of where to find this newly created object in the heap. So it's actually a number in the box, but that number effectively represents the location of the object in memory, so we draw an arrow from the box to that location in memory. And that arrow is actually the value of the variable UCSD. All right, so now we've got our new object. We've got the value of UCSD, which is a reference to that newly created object in memory. Now let's look a little bit closer at what that object looks like over there in memory. So this class simple location has two member variables, and both of these member variables are stored inside the object. So we can open up that object, look inside, and we can see that inside we actually have two variable declarations. There's latitude and longitude. So we're going to draw boxes just like we did before with that integer var1. We'll create a box for latitude and a box for longitude and label them both with their names. Those boxes are going to store the values of latitude and longitude when that object is created. And where do they get their values? Well, they get them from the constructor. Those values that get passed in are the values that go into the latitude and longitude variables inside that object, which is over there in the heap. So this is the complete memory model after these first three lines of code. We've got our primitive variable var1 storing the value 52. We've got our object type variable UCSD, which stores a reference, which is essentially just a number representing the location of this newly created object in memory, which we represent in our memory model diagram as an arrow. And then we have our object, which has two variables inside of it, latitude and longitude. The next line down creates another new variable, and it creates another new object, and then we'll create a link between the two by storing the reference to the new object in the new variable. So let's take that down piece by piece. In order to draw this part of the memory model, what you would do is you would handle the declaration first, draw that box, label it with the variable's name, which is Lima, draw the new object over here in memory, put the two member variables that are inside that object as boxes labeled with their names inside the object, and then link the variable Lima to the newly created object by placing a reference inside the box for Lima, which again is the value of the variable Lima. All right, so we're almost there. This is the last line. Let's look at this last line of code, which actually changes the value of latitude inside the variable Lima. So let's say, for example, we want to tweak the value of the latitude variable, make it a little more precise. What happens in our memory model when we make this change to the variable latitude inside the object Lima? Well, what Java says when it sees a statement like this, lima.latitude, what that means is it wants us to follow the arrow from Lima into memory to the object it finds there and find the variable latitude inside that object. So that's how that we know we're not talking about latitude up there in the UCSD object. We're talking about latitude down in the Lima object because we say lima.latitude. So we go to the box for Lima, we follow the arrow, and then look in that object to find the variable latitude. We find it, and that's where that value, negative 12.04, is going to go. So we change the value of the variable latitude inside that object, and that's all there is for this code. And here we have the final memory model representing the state of all the variables and all the memory in this code when the code is finished running. So now that you've mastered these memory models, you should be able to reason about lots of different examples involving both primitive variables and object type variables. So we've got a sequence of challenges and practice videos for you to try out your new skills.
Welcome back. We're going to do a challenge question at this point. So you've learned a great deal about memory models, but let's see if we really understand it well. What we're going to do in this video is we're going to walk through 2 questions, the first of which will just be a question where we stop and come back. And the second question is where we're actually going to walk through the full concept challenge procedure. Again, the procedure is you're going to pause, think about the problem, solve it yourself, discuss it potentially with other learners, watch a video of UCSD learners discussing it, and then confirm your understanding with our explanation. So first, to get things started, what I want to give you is an example piece of code. I have the simple location class that we've already been working with, and then I'm just going to create in main an example of one of those objects. So what I want you to do is pull out your pencils and paper, pause, draw the memory model as it stands right now, and then come back. So if this was the model that you drew, you were spot on. And this gives us a good starting point now for our next question. So we're going to scale the question a bit. We've got a single variable now within main. We've also got 2 objects that we're creating within main. The question here is, what memory model is going to result? Again, pull out a piece of paper and a pencil, draw this yourself, and then we'll come back together.
Hi, my name is Hazil.
Hi, I'm Julia. And I'm Monica. And let's just get started. Okay, so far, looking at this, I noticed that there are 2 objects. So we can immediately cross out C.
So how are there 2 objects?
They both are simple location objects, so wouldn't they point to like a simple location inside the heap? Yeah, but each one is a new simple location, so they don't point to the same area in the heap. They point to different areas because they're both new objects.
So Washington, D.C. gets its own place?
Washington, D.C. gets its own place.
So there are 2 objects because there's 2 news, right?
Right, there's 2 news.
So that means C is not the answer.
Yeah, that's what I thought.
Okay.
But the part where I got a bit confused on was when I tried to look at each of the different locations in memory. And I understand why latitude is -12 for each one of these, but I don't really get why D doesn't point to -77, or whether it actually is just -77 in the box.
So we know that D is primitive, which means that it's just a constant number.
Right.
So primitive types, which are constant numbers, do not need an arrow. That's what I think.
Well, why don't we need an arrow though? I mean, it's inside the object's memory area.
But the item itself is not an object.
Oh, okay, I see.
So then you just write it directly into the box for both cases?
All right, now that you've heard an explanation about this from our UCSD learners, you're already seeing how this works. And really the only way to do this is to trace the code just as they did. And I'm going to do that for us here. We're going to start at the very top of main, as we always do, and we're going to have a double variable D that's assigned the value -77. You can see that's within the scope of main in the drawing below. Then I'm going to create a reference for Lima. And just like we did at the very start here, is I'm going to actually now create this object. So when I call new simple location that allocates space on the heap, you can see that on the right. And then I'm going to pass in as parameters -12 and -77. That's the value of D at the time that it's passed in as a parameter. Perfect. All right, now we can do the second piece. Now we're going to create a second object, we're creating a reference for a second object, which is called WashDC. And now I'm actually going to create the object by calling that new simple location. So again, new simple location allocates space in the heap for a new object. And I'm now going to call this method passing in these 2 parameters. And the key part to this problem is really what happens with lima.long. When you call a constructor and you're passing these values as parameters in Java are always passed by value. So 38.9 is going to be copied over as exactly 38.9. And lima.long is going to be evaluated to be the -77 that it is. And then that -77 is what's passed for long in. Now we're going to copy the values over just like we did before. We're going to copy into this .lat. We're We're going to copy into this dot long. And then at the very end of this constructor, we're going to hook up wash DC to that lat and that long, or that object that contains the lat and the long. So this is our memory model at this point. Was this close to what you got? I hope it was. If it wasn't, it's worthwhile walking through a couple more of these memory model problems. Keep in mind that when you're drawing memory models, the purpose of this is to really understand your code. It's difficult to reason and debug code if you're not drawing the memory model associated with it. As we continue working through this module, it's important that we have these concept challenges. So the reason we're doing these again is that it's important to test your own understanding. So you can listen to us talk about the material, but until you've really tried to apply it, you don't know for sure whether or not you're understanding it correctly. So this is an opportunity for you to identify potential misconceptions in your understanding, or to gain confidence in the fact that you're understanding it properly. The process again, we're going to pause, you're going to try to solve it yourself, you're going to discuss it with potentially other learners around you, you're going to watch UCSD learners talk about the concepts, and then you're going to confirm your understanding with our explanation. So the problem for this one is to walk through this code. Again, always start executing in main. And at the very end of main, there's going to be a print. And the question is, what gets printed?
Hi, I'm Tianki.
Hi, I'm Peter.
Hi, I'm Joe.
All right, so let's go ahead and get started. So I guess we can all agree. So location 1 is going to create a new simple location with those values, and location 2 is going to create another simple location with those values as well.
And we're talking about objects right here?
Yeah.
Okay.
So we're gonna have two different objects, location 1 and location 2. Mm-hmm. What I got stuck at was when location 1 equals location 2. So what I was thinking was that the values inside location 2 are actually gonna copy over into location 1.
Oh, like a whole new object?
Well, not exactly a whole new object, but just the values of the latitude and longitude into location 1. So currently,
like rewrite.
Yeah. So currently, location 1 has 39.9 for the latitude, and what I was thinking that location 2's latitude 55.8 would overwrite that. Am I right, or?
I think those are like two objects, right? Like they are separate. So I think the third line is just change the reference here, so it won't like override like the every like member variable here.
So like rewrite the arrow instead, like where location 1 is pointing?
Right.
All right, so location 1 is now going to reference to the same object that location 2 is referencing,
and you just follow the arrow.
All right, okay. So that means that location 1's values do change, but it's just because it's referencing a new object.
Correct.
Yeah.
All right. So when location 1.lat gets negative 8.3, that means that the latitude of location 1 changes to negative 8.3, but since that's the same object referenced by location 2, does that mean location 2's latitude changes to negative 8.3?
Yeah, I think so.
Yeah, because it's all just one object.
That was a great discussion by the UCSD learners. Let's walk through the code again one more time. So you're going to start in main. You're going to create a simple location reference, loc1, that's going to point to an object. And we just did those memory models, so we'll do this one a little bit more quickly. We're going to recognize that this is going to create a reference loc1 pointing to an object on the heap which has these values. We're then going to create a second object. This one's going to be loc2, and loc2 is pointing to a different object on the heap. The key part of this problem is what happens in this next statement. What happens when you assign loc1 to be equal to loc2? What really happens there? To understand that, we're going to have to think about what those references really mean. So loc2 points to this object, and what that really means is that loc2 has a numeric value, which is an address for that object on the heap, and that object on the heap actually has that address. So you can think of loc1, we're throwing in arbitrary addresses here, but loc1 has address 1, it points to that object on the heap. Loc2 has address 2, and it's pointing to that object on the heap. When you do loc1 equals loc2, you're really copying essentially the reference. that means is you're copying the address. So loc1 is now going to point to the exact same thing that loc2 does. Now, when we do loc1.lat equals this negative value, you're going to realize loc1 points to the same thing that loc2 points to, and it's going to change that object pointed to by loc1. Then we're going to go to print this. We're going to print using the loc2 reference, but again, loc2 and loc1 are pointing to the exact same thing on the heap. So when loc2 prints out its lat and long, it's going to print out minus 8.3 and 37.6. Again, drawing these memory models helps you understand how to work through these problems.
In this support video, we'll be practicing two really important skills. First, we'll be tracing code using the memory models that we've been talking about before for both object and primitive data. But we'll also be developing a skill of tracing code and talking about it in high-level terms, beyond step-by-step what each statement does. Now, you want to make sure that you're ready to participate, get a pencil out, and work with me through this. You'll learn much better if you're working through it yourself as well. So let's start with a piece of code that we'll be thinking about and take a few seconds to read it carefully and try to explain in your own words what this piece of code does. All right, welcome back. It's very useful to try to think about how the code and the syntax that we have in Java translate to steps and procedures that we can understand as high-level human beings. So for example, if we're thinking about this in words, what we might say is that we create a couple of objects and then we try to assign those objects to one another. When we say assign objects to one another, that's very imprecise. And so this gives us an added perspective on the benefit of tracing code and on the benefit of the precision that comes with memory models. All right, so let's see what we do when we trace the code. We remember that in order to declare simple location type objects, what we need is to think about the simple location class, and we're using the class definition that you've seen in the core videos for this module. So you'll be fairly familiar with this definition, but you can look at it here as well. The first line of code that we have is a declaration and an assignment statement. We're reserving some space in memory. We're labeling it UCSD, and what we would like to have there is a reference to a new object. That new object is of type simple location, and it's initialized using the constructor to some values. So what that means is we have a box in our memory model. It's labeled by the name of the variable UCSD, and we point to this new object that we've created whose instance variables, latitude and longitude, are set to 32.9 and negative 117.2 respectively. And that's all there is to that first line. So now we go on to the next line, and that next line has exactly the same form. We're declaring a variable. That variable is of type simple location, and so we have a reference to a new object. That object is being created by the constructor, and those instance variables have their own values. And notice that those instance variables for this new object are completely separate from the variables that we had for the previous object. We've constructed completely new copies of these objects. All right, now we get to the third line, and in this third line, we're not creating any new objects. We're not declaring any new variables. What we're doing is we're doing an assignment statement. And an assignment statement, what we would like to do is to assign the value on the right-hand side to the variable on the left-hand side. And so let's think a little bit more about what's actually stored inside these variables. So UCSD, that box in our memory model, has an arrow to an object, but remember that arrow to the object is our visual shorthand for saying we have stored the address in memory of that object. So something like @15. 15 is a made-up number here. It's to indicate some address, the address of the object that we created before. Similarly, the box associated with the variable Kumamoto stores an address, which is the address, the reference to a new object of type simple location. So it's got a different address because we've got two different objects. Now what we need to do in this assignment statement is we need to copy the contents of the box Kumamoto to the box UCSD. And so that means that the @34 reference gets copied into the UCSD box. And so if we think about that in terms of our memory model, what's happening here is that now both of these variables refer to the same object, the object at the address @34. Okay, so that's what we've done with this assignment statement, but now what happens when we go to the last statement in this code snippet? Here what we're trying to do is we're trying to assign the value that's stored in the variable UCSD to the variable Kumamoto. But if we look at that value that's stored at the variable UCSD, it's the address of the object that we had before that was also pointed to by Kumamoto. So actually executing this assignment does nothing at all. It's saying copy @34 to Kumamoto, and that was the previous value of Kumamoto before as well. So at the end of executing this line of code, if we were to test it using the strategy we talked about before by throwing it into a class and execute it into the main method of a class and then running that piece of code, then we see that both UCSD and Kumamoto, both of those variables pointed to the same object with the latitude and longitude variables set as we did when we constructed the Kumamoto object.
Okay, the last lesson in this module is talking about variable scope. Now you may already be familiar with the notion of variable scope, but we're going to introduce it again because it's such an important concept. And we're going to do more than just introduce the notion of variable scope. We're going to also incorporate it into those memory models for reasoning about Java code. So by the end of this module, you'll be able to describe the notion of scope and Java's rules for scope, as well as draw those memory models to incorporate scope and reason about code using those memory models. So get out your pencil, get out your piece of paper, make sure you're not driving, and you'll draw these memory models right along with us. So we're starting off with a little warm-up question. I want you to look at this code. This code should look pretty familiar to you by now. And I want you to identify the 6 variables that appear in this code. So pause the video for a second, see if you can find 6 variables in this code. All right, welcome back. Hopefully you found 6 variables. If you didn't, don't worry about it. Here's the 6 variables that I found in this code. Now, you may have also identified that keyword this as a variable. It's not quite a variable. It behaves a little bit like a variable. We'll talk more about that later as we add in scope into our memory models. But here are those 6 variables. There's latitude and longitude, which are the member variables in our simple location class. There's latin and lon_in, which are the parameters to our method, to our constructor. And then over in our main method, there's lima, which is our simple location object, and then that tricky one, which is the parameter to the main method, args. So all of these variables are not necessarily created equal. So even though latitude is a variable in this code, if I try to refer to latitude over here in the main method, what do you think is going to happen? So take a minute, take a guess. What happens if I just try to directly access the variable latitude in the main method? So if you tried this, you will have found that it caused an error. If you try to access latitude in this location, in this main method, Java is going to tell you that this variable latitude is not defined here. So this brings us to the idea of scope. The scope of a variable is the area in the code where it's defined to have a particular value. And in this case, in the main method, that variable latitude is not defined at all. It hasn't been declared here. It was declared over in the simple location class. It was one of the member variables. So I can't get at it in main. So let's talk about a few different types of variables and types of scoping rules for those variables. So the first kind of variable we're going to talk about is called a local variable. A local variable is a variable that's declared inside some method. For example, lima is a local variable. And if that variable is declared inside the method, outside of any block like an if statement or a while loop, then that variable can be used and has a particular value that you set it to all the way through that method. So in this case, I can use the variable lima anywhere inside the main method, but not outside the main method. Second kind of variable I want to talk about are parameters. Parameters are those arguments that we pass into methods, and they behave basically just like local variables. You can use them anywhere inside the method. You can change their value if you want to, and essentially they're just like local variables. The third kind of variable are called member variables. Now you're familiar with member variables already. They're those variables that belong to a class rather than being declared locally in any method. They're declared outside any method in the class. And this means that these variables, their scope is actually the entire class itself. So you can refer to latitude and longitude from any method inside this simple location class. So they have kind of a broader scope or a wider place, array of places where they can be used than those local variables. So that in a nutshell describes scope and a few different kinds of variables. But really what we want to do is be able to reason with this notion of scope. And in order to do that, we're going to go back to our memory models. So here's where you're going to need that pen or that pencil and that piece of paper. We're going to trace through this code. It's only 2 lines of code, and we're going to layer in this notion of scope into our memory model. So we're going to start you off with a simple statement here, which is just a variable declaration and an assignment statement. So you know what to do. You draw the box, you put the value in the box. There you go. There's our variable. It's called lat, and it stores the value -12.0. But now we're going to, as I mentioned, layer in a notion of scope. So this variable doesn't exist just anywhere. It exists inside the scope of the main method. So the way I'm going to denote that in my model is I'm going to draw a box around that variable and label it with the name of the scope that I'm talking about. So I've got a fancy box with some shadows, but in your drawing on your piece of paper, just put a simple box around it, label it with the name of the method, which is main. My next line down, I declare another local variable, lima, inside of the main method as well. So that also goes into the box representing the scope for main. Now things get a little bit interesting because lima is an object type variable. It's going to store a reference to a simple location object. So that simple location object, as we've looked at before, gets created over here in the heap, which is a separate part of memory. So the simple location object gets created, and its 2 member variables, latitude and longitude, get placed inside the object that gets created on the heap. So that latitude and longitude, they're not inside main scope. They're over there in the scope of the object. So that's how I'm going to denote them in our memory model. But when the constructor gets called, we get some more variables that get instantiated. We get those parameters, lat in and lon in. And they have their own scope, which is local to the constructor for simple location. So I need to draw that scope in together with the variables lat in and lon in. So I've got another scope box for the constructor with the parameters that I've passed in. Those parameters, of course, get their value from the arguments that I passed when I called the constructor. Now I'm going to add one more thing to the scope of the constructor, and that is this keyword this. So we talked about this before. This refers to the calling object. And in any method that's inside the class, we have access to this keyword this, and what this stores is a reference to the object that we just created. So in this case, we see that object over there on the heap. We have our keyword this, whose value is a reference to that newly created object. And I'll put this inside the constructor scope because the constructor has access to this. So now we can go ahead and trace through the rest of the constructor. We see that that first line of the constructor takes the value of lat in, which is inside the constructor scope, and copies that value over into this dot latitude. So we follow the arrow and copy that into the member variable latitude inside the object. Same thing happens with the longitude variable. We just copy the value from lon in over into the object's version of the longitude variable. Now the constructor is over. So what happens to its scope? Well, when a method ends, its scope disappears. So all those local variables, the parameters, any variable that has been declared locally, they disappear, they go away. You could never use them again. They're just gone. And now, as we know, the constructor is over, so we return back to the main method and set lima to have a reference to that newly created object. So that's basically it for adding scope to your memory model diagrams. There's just one more subtlety I want to touch on before we finish off this introduction to scope, and that's the keyword this. So we've been using it, and it's very useful, but it's not strictly required in Java. So I don't have to preface my member variables with a this dot. I don't have to preface calls to methods inside my class with this dot. I can omit this, and Java will work just fine. It will figure out what I'm talking about just fine. And let's take a closer look at how it does that. So if I leave off the keyword this, what Java is going to do is it's first going to say, oh, I see a variable name called latitude. I think that's probably a local variable. So I'm going to look for it inside the scope of the method that I'm currently in, which in this case is the constructor. But in this case, it's not going to find the variable latitude in the constructor. So what it's going to do instead is look over in the object whose basically that was the calling object for this particular method. So it looks over here in the simple location object. Now it finds the variable latitude, and that's the variable that gets changed with this assignment statement. So that's all there is to scope, and we've got some practice problems for you, which we hope you'll enjoy.
Hi, and welcome back to our module on scope. It's time for another one of these concept challenges. Again, the flow for this is you're going to pause, think about the problem yourself. You're going to discuss this if you have other learners around you. You're going to watch the UC San Diego learners tackle the problem, and then you're going to hear our explanation. So the question here is going to involve essentially two classes. You've been working a great deal with simple location, and we're going to keep using this class, and that's the one on the left. We've got a tester class on the right, and that tester class has a main method. It's within this main method where you're going to see a number of things get declared, and then something get printed. The big question is, what gets printed?
Hi, I'm Tianki.
Hi, I'm Peter.
And I'm Joe.
So what actually happens when we go back to our main method and we look at lat gets negative 12.0? Is that going to change Lima's latitude value since that's what we took in as the variable?
Well, I think since we were just working with a primitive data type, then it was just like getting a copy of it, right? It wasn't like doing the whole arrow thing like before. Like we're not pointing to an old object, we're just getting a copy of its data.
All right.
And regarding the scope, I think the double here is just in the main scope, so it won't have any access to the object itself, right? So you change the number here, you just change the number in this scope. Right?
Oh, like locally?
Yeah, just like locally.
All right,
And
so
not the object.
So even when we come back to the main method and we look at lat gets negative 12.0, that's not going to change the latitude in our Lima.
Right.
I see.
They just have the same name, but like two different access, I think.
Oh, okay. So in the end, when we print out lima.lat, it's going to remain whatever we created it in the first place, which was negative 15.5. All right, cool.
As you saw when the students were discussing, the key to solving this problem is tracing through the code. So what we're going to do is exactly that. Now with our code, we're always going to start with main, as we have in the past. And we're going to start with the very first line in code, which is that double lat equals minus 15.5. So just so we know with all the memory diagrams, I'm going to start by creating a scope in main. I'm going to declare space for a variable named lat. The first thing I'm going to do then is fill that with minus 15.5. And that does the first line of code. Next step, we're going to create a new variable called lima, right over here. And that's just a reference. Then we call new simple location, pass it a lat, and a minus 77.0. That operation is now going to call the constructor. So let's move to the scope of the constructor. Box this off as the scope of main. Box off the scope of my constructor in simple location. CTOR stands for constructor. And within that scope, I've passed now two parameters. So it has two variables, both lat_in and long_in. Each of those parameters just are now pre-filled with the values as defined at the time of the call. So lat was minus 15.5. That's this passed by value in Java, so minus 15.5. And long_in is going to be minus 77.0. The other piece here was we said new simple location. The act of saying new actually allocates space on the heap. So what I'm going to do down here is create that space on the heap for a simple location object. And that object is going to have the private instance variables lat, and long. At this point, we already see that we have a number of cases where we see the variable lat. And that's going to be at the heart of this problem. So let's continue walking through the code. So we're right now in the middle of simple location, where we've already passed in these two parameters. And what we're going to do now is actually do this line of code. So this dot lat refers to the object on the heap. This is my simple location object. And it's going to be assigned the value of lat in, which is minus 15.5. So I'm going to copy that value over. The next line of code is going to behave exactly the same way, right? All it's going to do is copy minus 77 into long. Now we finish this constructor, and at the end of any method, as we know, these variables essentially get destroyed. I'm just going to do a quick line through it to say that our constructor variables are gone, and we're now back in main. So within main, the very next line of code we're going to execute is right down here. It's going to say lat equals minus 12. What lat are we referring to? Well, I'm going to look at my local scope. I have a variable named lat, and I'm going to change it to be minus 12. Now, I've already made one mistake here. And that mistake is, when this constructor finished, it would have returned a pointer to this. And I failed to connect this to the object on the heap. All right, now that's connected properly. We now would have done the change to this to be minus 12. And now we're going to try to print lima.lat. So I'm going to follow my pointer, my reference out to lima, and I'm going to check what value does lat have. Well, the value is minus 15.5. What's going to be printed then is exactly that, minus 15.5. What we see from this, walking through this code, is that as long as you trace through the code, you draw your memory diagrams, you're going to be able to solve this type of problem.
So you've now heard a lot about objects, you've heard a lot about memory models, you've heard a lot about scope, you've worked through some concept challenges, and now we have an opportunity to put it all together. So buckle in, get ready. This is going to be a tricky example, but we're going to get through it together. So what we're going to do here is take the simple location class that you've talked about a lot with Christine, and we're going to change it a bit. So remember that simple location, we want to encode the latitude and the longitude. And so far we've been encoding them as two instance variables. Each of them is a number type, a primitive type double. But now we're going to twist things up a bit, and we're going to define a new class, a different class called array location. And we're still going to want to record the coordinates of that location, but we're going to try to implement this by recording them in an array. So it's an array that we're called coords, and the kind of information that's stored in that array are still going to be doubles. All right, so let's think about how we might define this class array location and then try to use it in the main method. Okay, so for our class definition, we define the instance variable coords of type array that's going to contain doubles, and then we're going to need to define the constructor. And the constructor, when it receives a parameter that's specifying an array that indicates the coordinates, we're going to say this dot coords equals coords. Okay, so that's going to be the definition of our constructor. And then we might go ahead and want to try to use these objects. And so in our main method, you can imagine a situation where we start us off by defining a new array and initializing it to 5.0 and 0.0. And if you look on a map, you'll see that those are roughly the coordinates of Accra in Africa. And so then we might want to create a location and label the variable that's pointing to that object, that array location object, and call it Accra, and say that variable Accra is going to point to a new array location with the coordinates as specified in that previous array. And then we might want to go ahead and get ready to think about a different location. And so we might want to use our coords array and store the value 32.9 in the 0th index and negative 117.2 in that the index 1. And if you recognize those are the coordinates for UC San Diego. And And then, just to check that we haven't messed anything up, we might debug our code by printing out the coordinates pointed to by the accra variable. And so what I'd like to do now is pause, and I want you to, first of all, think through what you think will happen when we do this. And second of all, open up Eclipse, type in this code. Remember that your file name is going to have to be arraylocation.java to match with a class name. And see what happens, and see if you can explain what happens. And when we come back together, we'll work through the memory models and figure out together what happens and why. So welcome back. Before we do the big reveal and say what actually happened, let's step through and see if we can predict it. Okay, so stepping through the code means we have to run together through the main method, and we're going to pretend to be the computers running this code. Okay, so the first thing that we have to do is we're declaring the variable coords, and so using our memory models, that means that we need to write the word coords next to a box in the scope of the main method. And what we want in that box is a reference to a new array that is initialized to the values 5.0 in index 0 and 0.0 in index 1. Okay, so the coords variable is in main's scope, and the array object that we created is in the heap. And so what's stored in the box for coords is a reference to the array. Okay. What's important here, what's important to keep in mind, is that an array is not a primitive type, it's an object type. Okay, so far, here's our memory model, and we've gone through one line of code. Now we get to the line of code that we will spend the most time on, and this is when we now declare the variable accra, and this variable is going to be of type array location, which means that what we want to do is, still in our main's scope, draw a box with accra, and what we're going to fill in there is a reference to an object. But in order to refer to an object needs to be constructed, and that's what that keyword new is doing. It's saying, hey, I want a new object, and the kind of object that I want is the array locations object. And so I have to go to the array location class and see that in the heap I'm going to have an array location instance, and the instance variables associated with that array location instance, well, they're listed right there in the class definition, and I need a coords variable. And now I'm going to go ahead and follow the constructor to initialize the variables in the instance that I have of the object that I have of type array location. So in the constructor's scope, I have another variable that's called coords, and that's my local variable for the constructor method that is the parameter to that constructor method. So the constructor array location has as a parameter a variable that's called coords. And what we do in this constructor, going back, before we go ahead and see what's in the meat of the constructor, we have to see what the value of that parameter is. So let's think about what's passed into the array location constructor when we were in the main method. When we were in the main method, what we passed into array location is coords. Too many coords! We can take care of it. We know what to do by looking at the memory models. The coords that's a parameter to the constructor is the variable in main's scope. And so the red arrow is what needs to be copied into the value of the variable in the constructor's scope. And so now the constructor's scope coords variable also points to the variable, to the array that we had in the heap. All right, so when we call the array location constructor, what we're doing is we're creating a new scope for the constructor. We've got a variable in there that is the parameter to that method, and that variable is initialized to the value that was passed in, which is a reference to the array in the heap. Okay, so now we need to remember one more thing when we have a constructor, and that is that we want a variable as well in the constructor's scope called this. And what this does is point to the location in the heap where we've allocated space for the object that we're creating. And remember that when we finish with a constructor, what we'll be returning to main is that reference to the object that we've just made and initialized. Okay, so here's our picture so far, and now let's figure out what's happening when we actually execute the code in the array location constructor and try to initialize the variables in the object that we've created. So the one line of code in that constructor is an assignment, this.coords equals coords. So what we're trying to do is we're trying to assign the value on the right-hand side to the thing on the left-hand side. And so on the right-hand side, we just have coords, but we're in the constructor's scope, so that variable is the circled variable coords that has that red reference. It's pointing to the array in the heap. And what we're doing is we're copying that reference to this dot coords. So remember, when we have a dot, that means that we can find the variable by following the arrows. So we look at where this points to, and this points to the object of type array location in the heap. And what we're doing is we're setting the value of the variable coords in that object scope. So this dot coords, that variable in the heap that belongs to the object, is going to now point to the array in the heap that was pointed to also by coords in the constructor scope. So we have all of these arrows, references pointing to the same array, but notice that we're still missing one, we've got one box empty, and so we're going to want to fill in that box, but we're going to be able to do that. And let's think about that, how that happens. So let's think about what's going to happen now that we've executed the one line of code in the constructor and finished with the constructor. So we're done the constructor, and what happens now is that the reference that was contained in the this variable in the constructor gets copied into the variable that gets assigned the new object. Okay, so that yellow arrow is now allowing the variable accra to point to the object that we created in the heap. But also we have to do a couple of things when we finish executing the constructor. We notice also that once the method finishes and returns its value, its scope goes away, and all variables associated with it just go away. And so we can erase it from our memory model. We don't need to think about it anymore. Okay, so we finished our constructor. Our memory model is now a little bit cleaner, and we have in our mains scope a couple of variables, and they point to a couple of things in the heap. And so now let's think about what happens as we continue executing the main method. So we go ahead and we try to set the value of at the first position in the coords array, so at index 0, and we're setting it to 32.9. And so what we're doing is we're saying, let's look at coords in mains scope, and we're setting the value at the first position there to 32.9. Cool, we can do that. Similarly, we look at that same reference to the same array, and we change its second position at index 1. Cool, we did that. But now, let's think about what happens when we print accra.coords, its value at its index 0. And so when we think about that number, well, we need to find it by following the arrows. So we go to the variable accra, and it's got a reference, and so when we say accra.coords, we want to follow the reference from accra all the way over to its object and look at the variable in that object scope, coords, and that coords is also pointing to the same array that we had in the heap. And so notice that what we get output is 32.9. Okay, pause and think. There's something weird happening, right? We wanted to store in the accra object the coordinates of accra. But then we were able to do something outside that object without any setter methods, without going into the variables of that object. And without doing that, we were able to change the value of the instance variables in that object. And that is not a good thing. So this is what happens when we're too loose about using object type variables as opposed to primitive type variables, they can change on us without us intending to have them change. And so the moral of this example is A, memory models help us in actually tracing through code and figuring out what happens. And B, when we have objects and basically object types which include arrays, something that's not primitive, then we really have to worry about what is allowed to refer to that object and how can its values change in perhaps unintended ways. Okay, so hopefully you feel like you can do this yourself as well with any example that's thrown at you. This is a tricky one, so if you need to go back and look at it again, do. But now you're ready to go continuing on with this module and beyond.
Welcome to our next module on object-oriented programming in Java, where we'll dive into the details of inheritance and polymorphism. In the project for this module, we'll be going further with our graphing of earthquakes onto the world map. The past assignment was really neat. You displayed earthquakes on a map and had their appearance determined by the magnitude of the earthquake. But knowing the magnitude of the earthquake alone isn't really enough information to understand the potential impact of that event. So we'll be going further with this idea in this module by making the earthquakes appear differently based on the location of the earthquake, the depth of the earthquake, and optionally, the age of the earthquake. But we'll continue to visualize the magnitude of the earthquake as the size of the marker. So there are a number of steps with this assignment, but let's try to break it down into 4 high-level goals. The first goal is to add markers for major cities. If you don't see your city here, please feel free to add it. The second is to figure out if the earthquakes occurred in the land, and if so, occurred in which country. Then you want to draw the earthquakes differently if they occurred in the land or in the sea. And you'll again change the size of the earthquake based on its magnitude. Now where earthquakes occur matters, as the threat they pose is affected by whether or not they're underwater and could cause a tsunami, or if they're in land and could cause physical damage to surrounding areas. The third goal is to change the color of the marker based on how deep the earthquake occurred. Again, the depth of the earthquake changes its potential impact to the surrounding areas. Lastly, as an optional goal, you can add an X to the earthquakes which occurred in the past day. To accomplish these goals, we'll be using features of both inheritance and polymorphism in Java. So be sure to check out the videos on these topics if you're unfamiliar or uncomfortable with those ideas. This was one of my favorite parts of the project. I hope you'll enjoy it too. In this module, we're going to begin looking at inheritance and polymorphism in Java. Now, inheritance and polymorphism are incredibly powerful features to any object-oriented programming language. But unlike loops or conditionals, you don't necessarily need to use inheritance and polymorphism for your code to work. When you first started programming, you probably could have put a lot of your code in main and gotten away with it. But as your code grew, you started using methods, and then later started using classes. Likewise, as the complexity of your project grows and you start working on large software design projects, you start having to use inheritance and polymorphism to be able to handle the complexity of the project. You've already worked with inheritance and polymorphism to some extent by having used the keyword extends in your previous modules. What we're going to do here is start working in more detail with inheritance and polymorphism. The goal here for this single video is to look at the value of inheritance in itself. We're going to do this by posing a potential problem. Imagine you're a software engineer at a university, and you've been working for some time on a person class. You've actually tested the code. It's much longer than the code that you see here, and you're very happy with it. But your software design team comes back to you and says, we really can't just have one class anymore. This needs to start behaving differently for students or faculty. So you think about how are you going to solve this? And there's a couple of potential solutions. Neither of these are going to be good solutions, so I'm not going to dive into too much detail with them, but let's talk through what you might try to do. The first option is really to say, well, I'm going to keep all of this in the person class, and I'm just going to have it behave differently if you're a student or faculty member. And I'm going to do this by having a Boolean, which just says whether or not you're a student. True if you're a student, false if you're faculty. I'm going to add a constructor that handles it this way as well. And then in each of my methods, I can just do if student, do the code for the student, else do the code for the faculty. And at this point, this doesn't seem like that bad of an idea. But what's going to happen is your software design team is going to come back to you later and say, you know, we can't have all students behave the same. Undergrads and graduate students are going to behave differently. They have different needs. Graduate students have thesis advisors, things like that. And then they'll come back to you and say, well, we need to behave differently if you're a full-time student or you're a part-time student. So what you'll do is you'll add now Boolean flags to say whether or not this is a graduate student or not, and a Boolean flag to keep track of whether or not you're full-time or not. And now your method's going to start looking something like, if you're a student, and you're a grad student, and you're full-time, and if this sounds really ugly, it is. In fact, this kind of ugly code has a specific name for it. You may have heard of it before. It's called spaghetti code. Now, I like spaghetti, but I don't like spaghetti code. Spaghetti code is code that you're going to write, you're going to realize how bad it is, you're going to throw it away, and you're going to start over. So this solution we're not happy with. Let me pose another potential solution. Let's just take my person class and copy paste it into two files and rename one to be student and rename the other to be faculty. And then within the student class, I'm going to change all the code to match the behavior of a student. And then within the faculty class, I'm going to change all the code to match the behavior of a faculty member. At this point, this seems like a pretty reasonable solution. This will actually work for a little while. But it's not going to work indefinitely. Take a few seconds to think about where it might go wrong. All right. If your answer had anything to do with either consistency or the ability to store all the objects in one data structure, you're on the right track. So let's talk through both of those. What's going to happen is your design team is going to come back to you. And they're going to say at some point, you know, having a single string name isn't sufficient. We really need you to break this out as first name and last name. And this isn't a major change. So you go into your code, you start changing all the instances of name to now work with first name and last name, and you fix all the student class. And then you're going to realize, wait, I had name in the faculty class too. And you can't just copy paste the code that you just changed in student into faculty. You're going to have to rewrite all the faculty, do all the changes you just made in student to the faculty code. It's going to be tedious and it's unnecessary. But more important, what if you make a mistake? What if you miss a change in faculty that you made in student? This is going to be really hard to keep consistent. The other problem with this is there's probably some code that has an array of persons right now. What's going to happen if I now break this into two classes, only student and only faculty? Well, I can't keep that single array of persons anymore. I'm going to have to keep two arrays, one for students and one for faculty. I know there's no clean way to keep a single data structure for all persons. And you might say, well, why is that important? Well, what if I wanted to just sort by the time that the person came on campus? That'd be really hard to do. I could sort the students potentially, and I could sort the faculty, but how do I merge those? It's going to get ugly pretty quick. So neither of these answers are things that we're happy with. What do we want then? Essentially, we figured out the goals by looking at these two examples. The goals here are, one, to keep all of our common code in one class. It'd be great if we could do that. We also would like it so that if we have different behaviors, I split that different behavior into different classes. And lastly, I want to be able to keep all these objects in one single data structure. Now, these are somewhat lofty goals, but the good news is they all come to us with inheritance. We're going to dive into the details about how to do this in the next video. In the last video, we began to see the power of inheritance and polymorphism in Java. In this video, we're going to start diving into the details. How do we make this work? The goal here is to use the keyword extends and recognize what that does. We're going to talk about the relationship between superclasses and subclasses and what those terms mean. And we're going to use UML diagrams to design our first class hierarchy. We left off with the last video saying we want three key features. We want to be able to keep common code in one class. We want to be able to split out differing code between different classes. And we want to be able to keep all the objects in one single data structure. In this video, we're going to show how we can do 1 and 2 by designing our hierarchy. Item 3 will be in the next video. Where we left off was talking about three different classes: a person class, a student class, and a faculty class. And in a sense, we want to have all the common code in the person class, and we want to have our divergent code in the student and the faculty classes. To do this, it'd be great if we could have all the power of person and all the features of person get inherited into the student class. So let's focus on that one first. Now, it might seem really powerful to inherit all the features of another class, and it is, but you can do it with just one keyword, extends. So if you say extends person, that means inherits from. It means the student class is going to inherit from person many of the features of the person class. So when you've used this before in previous modules, this was a really powerful thing to do, to say extends. So what do you get when you, before I say that, let's talk about some terminology. The person class here is a base class, sometimes called a superclass and sometimes called a parent class. The student class here is a derived class or a subclass or a child class. Now, what features do you actually inherit? You inherit public instance variables, and that makes sense. You're going to inherit the public methods, so students are going to get all the public methods of person. You're also going to inherit the private instance variables, in a sense. So we'll talk about that in a little more detail. So since you're inheriting the private instance variables, do you really still need to have that instance variable within student called name? No. In fact, it's a really bad idea to do that. That would be called a hidden variable or shadow variable. And it's hard to discern which name variable you're talking about, the one in student or the one in person. So you actually wouldn't have that, because you inherit it automatically from person. But there is one catch. Because it's a private instance variable, you can only access it through public methods. So you'll have to use the getters and setters to access name. Now that we have an idea of how we can use inheritance, let's start talking about how we can design an inheritance hierarchy. Now, if you're working on a whiteboard with a design team, you're not going to want to write out the whole class. You're going to want to have a very small representation of a class. The way to do this is something known as a UML diagram. I have an example of this on the right. Now, there's a number of different variants of how you can display this. This is just one example. I have the person class name at the top. I have the instance variable string name, and then I have the method below that. So you have, again, class name, instance variables, and methods, all within this concise representation. Let's add in the student class, which is extending person. When I add that in, you're going to recognize that's blank, and that's because there are no instance variables and no methods within student. Now that keyword extends, along with person, is going to say student inherits from person. And to do that, all you have to do is draw that line. So that line just says student is inheriting from person. But let's start talking about our full hierarchy. Let's bring back in faculty into this. So we have our person class, and I have two derived classes, my student class and my faculty class. This alone is already an inheritance hierarchy or a class hierarchy. What I want you to do is pause. Take a few seconds to think about what would belong in a student class that wouldn't belong in a faculty class, and vice versa. Again, take a few seconds, pause the video, and we'll come back. All right, there are a number of good answers here. Let's just talk through a couple that I thought of. So students get grades in their classes. In the American education system, we use something called a GPA, which is essentially just an average of all the grades that you've gotten. Students would have these, faculty would not. So in the student class, I'd have an instance variable named GPA, and then I'd have an accessor method called getGPA. What belongs in a faculty class that wouldn't belong in a student class? Well, maybe an office number, office phone, but also a salary. So faculty get paid, students generally do not. So I'm going to have an instance variable called double salary, and I'm going to have a method called getSalary to get access to this. We've already started designing our inheritance hierarchy. We have the code that's common up in the person class, and we have the code that's divergent in the student class and the faculty classes separately. This answers items 1 and 2 from our desire list. But we haven't answered 3 yet, and that's coming up in the next video.
For example, I work on Google Docs, and what we do is we'll use a base class for representing format buttons. So every button has a specific style, an image, action that the button does, and we'll use that and we'll extend it to make things like the bold button, the italic button, the underline button. Another example of Google APIs that use inheritance is actually found in Android, where we will extend the activity class. So an activity is a single focused thing that the user can do within an app. and an app can be made of several activities, and we use inheritance to prevent us from repeating code.
In the last video, we began using the keyword extends to unlock the power of inheritance in Java. We also designed our first class hierarchy, and we're going to continue with that in this video. The goal here is to understand what the term is-a means and how it defines a relationship necessarily between classes. In the last video, we saw how designing our class hierarchy and using the keyword extends gives us the first two features on this list. It allows us to keep all the common code in one class. It allows us to split out the different behavior between separate classes. But what we didn't answer was how can we keep all the objects in one single data structure? And to figure this out, let's play an old-fashioned matching game. What I have here on the left is a reference, and on the right I have an object. What we're going to do is essentially play matching game. We're going to try to figure out, can you have this reference point to this object? Let's start off with person P equals new person. You've done this a whole bunch. Is this legal? Absolutely. The reason this is legal is because a person is a person. Somewhat reflective, we kind of recognize that. We'll use this term, though, again as we go forward. Likewise, is a student a student? Absolutely. A student is a student. Where this gets interesting is, can you have a reference, person, point to a student object? What I want you to do is think about this just for a few seconds. Do you think this should be allowed? I hope you said yes. This should be allowed. Now, this is new. You've likely always ran code where the reference was the exact same thing as the object. But you're actually allowed to do this. And the reason you're allowed to do this is because a student is a person. All the capabilities that a person has, a student has to have because it's derived from person. This is fantastic, because what this allows us to do now is to keep one single array of student and faculty objects. So this code, where I create an array of persons, or references to persons, and then I can fill it with references to a person object, to a student object, and to a faculty object. This code compiles and will work just fine. So we can now keep, whether you're a person, a student, or faculty, all in one data structure. This is fantastic. But we haven't finished our matching game yet. Can you have a student reference point to a person object? The answer here is no. Why? Well, not all the features of a student are necessarily within a person. And you can think about it kind of loosely as an analogy of, if you walked up to a random person on the street and asked them what their GPA is, well, that's probably not a very polite question to ask in the first place. But if you were to ask it, most people would say, I'm not a student, what are you asking me? This is why you can't do this. Now, why I brought up this example is because when we get to polymorphism in just a few videos, references and objects are going to become front and center. We're going to talk about what decisions are made at compile time based on reference type, and what decisions are made at runtime based on object actual type. But before we can get there, we have a few more details to work out with inheritance in the next videos.
So one of the problems I had when learning about inheritance was the is-a relationship. And my professor used some analogy along the lines of animals, and like a lion is an animal, and for whatever reason that went right over my head, and it really frustrated me because I feel like all my peers quickly picked it up. And so I reached out to my professor after class, and he just twisted the analogy to be cars, and he asked me what kind of car I drove, and I answered, I drove a Toyota. And so he just relayed that same analogy, but back to cars and Toyotas. And he said, a Toyota is a car, but not all cars are Toyotas. And for whatever reason, that really clicked with me, and that's what it took.
All right, you've learned a little bit about inheritance, and you played that matching game with Leo, where you learned what kinds of references can refer to what kinds of objects. And it turns out that is a really, really tricky idea to get. So we've got a concept challenge for you that's going to exercise your ability to make those matches. Don't worry if this is a little bit tricky. It takes a while to get it. So work through it, you know the drill. Work through it on your own, answer the in-video quiz, discuss with others, watch our learner videos, and then watch our explanation. So here's your challenge. We've got 3 classes. There's a person class. It has a name, member variable, and it has a getName method. There's a student class, which extends person. It has an ID member variable that's an integer, and it has a getID method that returns an integer. And there's a faculty class, which also extends person. It also has an ID variable, but this time it's a string, and it has a getID method that returns a string. We have 5 statements over there on the right that create new objects and assign references to refer to those new objects. All of those statements compile and run just fine. Your question is going to be to answer questions about which of an additional series of statements work and which cause errors at either compile time or runtime.
Okay. My name is Linda.
My name is Mustafa.
My name is Jason. So how did you guys answer question 1?
I seem to think that question 1 didn't have any issues. S is a student, and they're trying to get the name from the student, and N.
Well, I thought there was a problem with that because when I look at the class student, I realized there is no method called getName.
That's true, but student extends from person.
So it will inherit all the parent class methods.
Oh,
yeah, it's a public method.
Oh, so like you want to inherit the person's getName method.
Right. Yeah.
Oh, okay, I see. How about the second P equals S?
For the second one, I also thought it was fine.
That's fine?
Because person P is a new person, and if you change the reference of P to become the object created from student S equals new student, then every student is a person.
Okay. So that's the part that I missed. I was thinking it would be a problem because student and person are not the same type, so I wasn't sure if you could cast it that way.
Oh, right. Okay. So pretty much like the P instead of referencing to person, now is referencing to students.
Mm-hmm. Okay.
That makes sense.
Yeah.
How about the next line?
I didn't think that would work because person doesn't have a getID method,
Right.
so like where would it be looking to get that?
I thought that like during compile time error, since P is still a person, it will go into the person class and then look at, oh, where's the getID method?
But didn't we just update the person class with pointing to a student class?
The compiler doesn't know that.
Yeah.
I think the compiler still sees it as a person object because it was.
It's only at runtime that the compiler will see that P is actually a student.
Oh, okay. Even that, I believe we have to cast it, I guess.
Right.
How about the third line of code? Faculty equals person.
Person. Well, person isn't necessarily a faculty member. So like he was saying that if you go around and like ask a random person on the street, they might not have the information for a faculty. So
Right.
I'm not sure if you can cast the faculty as a broad term person.
Right. Not every person is a faculty.
Right.
Okay, yeah, that makes sense. And then the last one, object, O equals a student, or object class equals student class.
I think we previously learned that every object inherits from the object class.
Yeah.
Right.
Oh,
so
I
the S
see.
is a student.
Okay, like every class would inherit object, meaning there's implicit extent.
Yeah, exactly.
Perfect.
All right, let's step through these lines one at a time to figure out which ones work and which ones cause errors. This first line here, it's pretty straightforward. It creates a new variable of type string called n, and it's going to set it equal to s.getName. So first we need to figure out, what is s? Well, s is a student reference. It's a reference to a student, and it actually does refer to a student object. And you can see that right here when we created that student object and assigned the reference s to point to it. So now we can look in the student class and see if there's a getName method. We look here, no getName method, but that doesn't concern us too much because student extends person. So now we can go up in person and look if there's a getName method there. And sure enough, there is. It returns a string. So this will run just fine, again, because this getName method is public. So everything's good. This line will work just fine. The next line says that the reference P should be set to refer to the same location that the reference S refers to. Now, S refers to a student object. So what we're saying is that P should now refer to a student object. And we have to figure out if that's okay. Is it okay for a person reference to refer to an object that's actually a student? So you ask the question, are all students people? Is a student always a person? And I hope the answer is always yes. So that should be just fine. That line works as well. The next line here says that int m gets the value of p.getID. So now we have to think about things a little more carefully. So what we're asking, assuming that this line has already completed and p now refers to a student object, we want to know, is it okay to call p.getID? Well, there is a getID method inside the student class, but the problem is that p is a person reference. So the compiler doesn't know that p actually refers to a student object. The compiler is going to complain about this statement here. It's going to say, p is a reference to a person. I don't know about this getID method. There's no getID method in person class. And so I'm going to cause an error. We can fix this with a cast. So if we wanted to fix this problem, we would just insert a cast here. We could cast p. So instead of just p, we'd say student, and then p right there, and then dot getID. Because we know that object is actually a student, so that's fine to do. But again, be a little careful with your casts, because the compiler will trust you no matter what you say. So we can do this in this case, because we know that's the truth. All right, so the next statement there, so going back actually to the last statement, this statement right here, this statement right there does not work as written, but it will work if we add that cast. Let's consider the next line, where it says f gets the value of q. So what is f? F is a faculty reference. It's a reference to some sort of faculty object. And what is q? Well, q is a reference to a person. So now we need to figure out if a faculty reference can point to a person object. And again, we will ask the question, are all people faculty? And the answer to that question is, of course, no. So we can't set a faculty reference equal to a person object. That will cause an error. And there's nothing that we can do to make that work. If we try to cast q to a faculty, the compiler might accept it, but at runtime, we're going to get what's called a class cast exception, because it's illegal to cast a person object to a faculty type. So that line will not work. What about this next line, where we say O equals S? So O is an object type reference, and S is a student object up here. Well, that should work, right? Because everything in Java is an object. So object type references are allowed to point to any kind of object that they want. So that one's pretty straightforward. That works. So now we're done. And to summarize, what we found was this first line here was just fine. The next line here was also just fine, because all students are people. The next line is not okay, but we could make it okay with a cast. The next line there was not okay, and there's nothing we could do to make that line work. And finally, this last line here was just fine.
Welcome back. At this point, we've been talking about what's inherited. We've used the terms private and public, and those visibility modifiers impact what gets inherited from one class to another. What we're going to do now is spend a little more time looking at the different visibility modifiers and how they impact us, particularly in relation to inheritance. By the end of this video, you should be able to use the appropriate visibility modifiers when you're writing your classes. Up to this point, you're comfortable probably with public, which is less restrictive, and private, which is more restrictive. So public gives access to any other class, whereas private gives access only to the same class. Well, at this point, you likely have learned this rule of thumb. You should make all your instance variables private. You should make your public interface, your public methods, public. You can also have private methods. Those are your helper methods. This rule of thumb is actually still going to apply, even if we talk about the other visibility modifiers. But it's important to know how they apply. The other visibility modifiers are protected and package. So protected gives you access to within the same class, anything within the same package can access it, and any subclass can access it. Package, also sometimes called default, you have access from the same class, and you have access from the same package. The only difference really between package and protected is that package loses access by any subclass. So subclasses that are still in the same package, you still have access to, but subclasses outside your package, you're going to lose. To really understand this, it helps to see an example. What I have here is a sample class. And that sample class has a public variable, a protected variable, a package variable or default variable, and then a private variable. Let's add a whole bunch of other classes. Some within the same package, the dotted line denotes package, and then some are subclasses. We have subclass 1 in the same package. We have subclass 2, which is outside the package. We have other 1, which just happens to be another class in the same package as sample. Then we have other 2, which is a class not in the same package and has no relationship in terms of inheritance with sample. If you have the public visibility, so W is accessible from anyone else. Now notice that I'm just saying public W. I'm not putting the public int. You can fill in the value there yourself. So public, anyone can access. Protected, you only lose, essentially take away access to other 2. So things within the same package as well as subclasses can access this variable. Now, what I'm concerned about here is why does other 1 have access to my variable x? Just because it's in the same package? Does that really make sense? Is that who we want to have access to our variables? In general, this is not a very good idea. And this is why we don't recommend using protected. If we look at package access, what you see is that we now have taken away access to the subclass 2 from what we had from protected. But you'll notice that other 1 still has access to y. Again, why is some other class in the same package happen to have access to my variable? It doesn't make much sense, and this is why we don't recommend package access either. Lastly, we have private access, which you're comfortable with, which just means within the same class, you can access this variable. Now that we've walked through the different levels of access, you see that public is the least restrictive and private is the most restrictive. But we still are going to apply the same rule of thumb. Always use public or private. There's only rare cases that you'll ever want to use protected or package. So when I was working on a really large project in graduate school, I hit this point where I was changing around my code, and I knew the right thing to do was to do inheritance. I was basically making 3 objects, but I was a little bit lazy with the software infrastructure. I was like, you know what, I'm just going to do this in one class. I can make this work. And it worked for a little while. So I worked on it for a few weeks, got the code working, but over the next couple of months, I kept running into bug after bug after bug related to this code. And finally one day I had to go to a group meeting for a research group and say, I'm going to need to take 2 weeks and rewrite the code properly. And I did. I lost 2 weeks of my life doing it, but it worked after that. No more bugs. So I learned inheritance the hard way. As we continue on in this module on inheritance, what we're going to do next is look at object construction in Java. Now you've already written constructors before, so you might say, well, wait a second, why are we revisiting this? Well, the reason we're revisiting this is because now that we know inheritance, we now know some more details about how objects actually get constructed. So the goals of this video is to recognize that all objects actually are derived from the object class. And you may already know that, but we're going to dive into some details about how that actually works over the course of the next few videos. And then we're also going to look at how Java actually constructs or initializes its objects really from the inside out. And we'll talk about what we mean by that in just a moment. We're going to keep working with this in hierarchy that we've been working with before, where we have a person class as a superclass, and a student and the faculty classes as derived classes. And we're going to focus in on essentially one line of code. Student S equals new student. We know that the new statement, new, is actually an operator. And that operator means allocate space. And the second piece of this is, once given that space, pass a reference to that space to the constructor for initialization. In fact, constructors really should be called initializers. And you'll see in other programming languages that they're actually called init. So really what the student constructor does is just initialize the variables associated with student. And the way that's going to do this is essentially from the inside out. So you're going to go all the way up the hierarchy, all the way up to object, and then you're going to come back down. As you come back down, you're going to initialize all those variables. And what we're going to do is step through this step by step to understand how this works. So first thing you do, after you've done new, you've created the space for the object, you pass that space to the student constructor. The student constructor then, its very first line of code is going to send you to the superclass constructor, in this case, person. The very first line of code of the person constructor is going to immediately send you to its indirect superclass, or in this case, object. Now, the object constructor can initialize the variables associated with object, essentially filling in that part of the object. Once it's done, it returns back to person. Person now can initialize its variables, and then it's going to return back to student. And student now is going to initialize the variables associated with student. And through this process, we've essentially initialized all these variables going all the way up to object and all the way back down. And that's what we mean by initializing it inside out. But what you might be thinking at this point is, wait, I don't remember ever extending from the object class. And you may not have done so explicitly, but it still happens. And we'll talk about how that happens in the next video. In the last video, we saw how objects are constructed from the inside out in Java. And the way this happens is really through compiler rules. We're going to talk about what those compiler rules are and how those compiler rules work in order to ensure, again, that the object is created from the inside out. What we left off in the last video is we'd seen the process. We'd seen how student calls person, which calls object, and then those constructors return back, and in the process of returning back, they actually initialize the variables. But you said at the end, well, wait, I don't remember extending object. Well, where did we do this? And this introduces our first rule associated with the compiler. So let's revisit where the compiler plays a role in our process. You write code, human readable Java code, and that gets sent off to the Java compiler. Java compiler is going to do a number of passes. In fact, there's a number of potential specializations you could write essentially just on how the compiler works. What we're going to focus in on is essentially a couple of passes the compiler does in terms of inserting code. When the compiler is all said and done, we know it produces the bytecode, which we then run on our Java virtual machine. So what is the Java compiler doing, and what are these rules? Well, what it does is it's going to change the code. So if you wrote this class, public class person, and you just have your single instance variable, and I've done away with any other code, it's just this class, is this actually what gets compiled? In a sense, no. Because the compiler takes this code, and it's going to change the code a bit. What it's going to do is follow 3 rules that we're going to talk about in this video. First rule is, if you don't have a superclass, the compiler is going to give you one. It's going to give you object. So even though you wrote public class person, the compiler is going to insert the terms extends object. By doing this, now you see how person inherits from object. It's just because it inserts those lines of code implicitly. But where then did we call the person constructor or the object constructor? We know now that person inherits from object, but we don't know where those constructors are getting called. That's where the next set of rules come. So first off, if you don't have a constructor, Java is going to give one for you. It's going to give you a default constructor, so no arguments. And then it's going to apply another set of rules, which are associated with all constructors. This set of rules, or rule 3, is that the first line of a constructor has to say either this, and then some arguments, so call another constructor within the same class, or it has to call one of the parent class constructors, a superclass constructor call. It has to do one of those things. And if you don't do it, Java is going to insert super. So it's going to insert a call to the default constructor of your superclass. So now we see that we've added this line to the person constructor. In a sense, you had the code on the left, but the compiler is going to insert all those elements in blue on the right, and that's what's really going to get compiled. So now that we have an idea of how this worked for person, I want you to pause and think about what would happen to the student class on the first pass by that compiler. Alright, if you were thinking we should add a very similar constructor to student that we did to person, you're on the right track. We can't, it already extends from person, so we can't extend from object. It already has a superclass, so there's no need to do that first rule. But the second rule applies. It has no constructor, so we have to insert a default constructor. And then the third rule applies if I have to make sure I call the default constructor of my superclass as the very first line of my default constructor here. So you're going to take that code in black above, and it's going to get transformed into the code in blue below. So when we were curious, how is the compiler making sure that the construction and the initialization of our variables happens essentially from the highest level of the hierarchy all the way back down? It's because the compiler makes it happen. Now there's still kind of one leftover problem, and that is we haven't actually initialized anything, right? All of our default constructors have done no initialization. They've just made sure they go all the way up to object and all the way back down. And we had at least one variable, and that was name, the instance variable with person. In our next video, we're going to see how to initialize that. In the past couple of videos, we've been starting to look at how class creation or object creation happens in Java. Specifically, how does inheritance apply to object creation? In the last video, we actually looked at a number of compiler rules. Now, these compiler rules are what the compiler does when it looks at your code. Now, the reason we want to know about these rules is because it's going to help us trace our code. In fact, we're going to see an error in our code here in just a little bit, which comes about because of these rules. We're also going to use same class constructors and superclass constructors to help with class creation. Now, we started by saying all objects are created from the inside out. In the last video, we saw how the compiler rules make this happen. But what we did with the last video was essentially just create a number of default constructors without actually initializing anything. So what we're going to do now is modify these to initialize the name variable. Again, you've likely initialized a variable before in a constructor. What we're focusing on are the elements that apply to inheritance. So let's start off with our person class. Remember that the extends object was automatically put there by the compiler, and what we're going to do instead of having it automatically put there is we're going to explicitly put it here. Likewise, I'm going to explicitly put the default constructor, which would have been inserted by the compiler anyway. And what we're going to do now is modify this default constructor to initialize the name variable. So let's add a string argument to the constructor. Let's add this.name equals n, and just do what we would have done before. Now, to be honest, if we didn't have that call to super, we'd be fine. But because I've now inserted this line, I've got an error. Remember that rule? The very first line of a constructor has to be a call to your same class constructor or to a superclass constructor. I have broken this rule by saying this.name equals n. And because I have a call to super after that, this is going to produce a fairly cryptic compiler error. Now you know what that error means, and you can fix it by just switching the order. So now I'm calling my superclass constructor correctly, and now I can initialize my variable. Let's modify the student class now to initialize the variables there as well. So let me take that default student constructor, and I'm going to make changes to it. I'm going to insert string n, I'm going to insert as a parameter, and I'm also going to initialize that variable. Is this going to work? I want you to pause and think about this for a few seconds, look at the code, and see if there's any errors here. If you start to recognize that I'm not allowed to say this.name, you're right. That's a private variable in the person class. I'm not allowed to directly access that in the student class. I'd have to use a getter or a setter to do so. But I don't have a getter or setter. Is there a way for me to do this? Can I initialize name without having a public getter or setter? The answer is yes. All I have to do is change this now to call the superclass constructor that takes an argument, which is going to initialize to be name. Perfect. So just cross out those two lines, replace it with super with that name variable being passed in, and it's going to initialize everything properly. Let's go a little bit further with this, though. Let me add one more constructor to that student class. let me add in, so this is our code from where we just left off, and now let me add in that noarg default constructor. Now what you might be tempted to do with that noarg default constructor, and let's just throw in some kind of default name here, is to just say super student. This would work. It's not the worst idea, but is there a better way to do this? Yes, there is. Right? There's no reason I should be calling the superclass's argument constructor when I have one in my own class. A better way to do this would be to do it like this. I should use my own same class constructor if it's available to me, because there may be code within my same class constructor which does things that I want to initialize based on this. I shouldn't just jump straight to the superclass. By having done all these pieces, we now see how object creation happens in Java. We see that it happens from the inside out. We see that everything inherits from object. And we now know how to use superclass constructors and own class constructors to design our classes better.
All right, in Leo's video, you learned how objects are created from the inside out. So in this concept challenge, you're going to be tracing through some code that calls some constructors. And the goal is to figure out what gets printed as these constructors run. So you know the drill, you've done these before. What you're going to need to do is you're going to need to be somewhere where you can spend a little time on this and pause the video, answer the quiz by yourself first, and then find some friends, find some people you're taking the class with, either in person or on the online forums. Try to discuss this question, see if you all agree, and then watch our learner video. And finally, watch our explanation. So if you're ready to go, here's the challenge. You can see over here that we've got two classes. There's a person class and a student class. And those classes have a number of constructors. The person class has a single constructor. It takes one argument, a string. And the student class has two different constructors, a no argument constructor, and then a constructor that takes one argument. So what we're going to do is we're going to make a single call to the student constructor, to the default constructor, right up here. And it's going to create a student object. And the question for you is, what gets printed when we make that call? So go ahead and pause the video and take the online quiz that's coming up.
I'm Linda.
I'm Mustafa.
Hello, I'm Jason.
Okay, so for this first question, I was a little unclear on the answer. My instinct was to go for E, for let's say just number 2, because the new student is the no argument constructor in the student class, and it just prints out number 2.
I was really confused about this too.
My first instinct was like it would be 3, 2, 1, because when you have a class and then it goes to a constructor, it goes from the inner one and the most outer one.
Right.
And then I looked at it more carefully and I realized when you go to students, there's a super is implicitly inserted.
Well, I was confused because the no argument constructor first called another this constructor with the student. So I didn't know if it went first to the superclass or to the other constructor within the one class. Because then the constructor within the one class calls super as well. So.
All right, so now that you've had an opportunity to work through this problem yourself and hopefully discuss it with some people, let me go through our explanation. So what we're doing is we're creating a student object right up here. Student S equals new student. And you can see that we're calling the default constructor. So we're going to jump right over here to the default constructor for the student class. So public student, no argument constructor. But if you look at the first line of this constructor, you can see that what it immediately does is it calls the one argument constructor for the student class, which has one argument, which is the string student. So we're going to jump down here to the one argument constructor and start executing there. We start executing there, but again, the first line in that constructor says to call the constructor of the superclass, which is person. We pass it an argument, which is what it requires. And we go up here and start executing the constructor for the person class. We haven't printed anything yet. We haven't really executed any lines at all. We're just sort of getting ready to call these constructors. So we're going to go over here, get ready to call the one argument constructor for the person class. And the first thing that it says is that it sets this.name, so the name field in this object we're creating, equal to n, the string we pass in. That's fine. And then the next line here is a print statement. So system.out to print line number 1. So this is the first print statement we've encountered. So we're going to print number 1. That's the first thing that gets printed. So where does it go now? Well, we're finished with this constructor. Here's the end of it. So we have to remember where we came from. Well, where did we come from? Well, we came from down here, the one argument constructor for the student class. And we just finished calling the constructor for the superclass. And we're now here on this line that says to print out number sign 3. So that's what we'll do next. Print number sign 3. So that's the second thing that gets printed. Finally, this constructor ends, and we'll go back to where we came from, which was the first constructor, the default constructor for the student class. We just finished the call to the one argument constructor. We're down here at this print statement, and we're going to print out the number sign 2. And that's all there is to it. So this is what gets printed. Number sign 1, number sign 3, and number sign 2. Okay, here's another concept challenge for you, all about constructors. What happens when we call the constructor of the student class? We've got our familiar classes here. We've got our person class, and we've got our student class. And the constructors, check them out. They're a little bit different. We've got a one argument constructor for the person class, a no argument constructor for the student class, and then this additional method here in the person class, which is set name, which will set the name field inside the person class. So we're going to ask you to reason about what happens when you call the student constructor. And this is a concept challenge, so we want you to do the same procedure that you're used to. Just take that individual quiz first by yourself, then find some people to chat about this question with, and then watch our learner video, and come back and watch our explanation.
Hi, I'm Alicia.
Hi, I'm Joanna.
Hello, I'm Justin.
Okay, so what did you guys put?
I think it's a compile time error because student doesn't have a name, so how can you set a name it doesn't have?
Yeah, but I thought that since student extends person, it actually inherits the name from persons. So then I actually put student because I thought that now it goes into constructor for person and sets the name to student.
Yeah, I also thought the same. One thing I did notice was that student calls person's no argument constructor, and I noticed that there's no no argument constructor in person, so I think that's the reason why it causes a compile error. Yeah.
Okay, so yeah, it's probably a compile time error then.
Yeah.
All right, now that you've worked through this yourself, let's work through it together. All we're doing here is we're calling the student default constructor. So let's trace through the code and see what happens. So we go over here to the student default constructor, and you might be tempted to just directly go and execute this line that says this dot set name to the string student. But the problem with that is you'd be forgetting that the compiler actually inserts some code into this constructor. If the first line of the constructor is not either a call to the superclass constructor or a call to a constructor within the class, the compiler is going to insert a line to the superclass constructor that takes no arguments for us. So in order to trace through this code, we need to insert that line so we know exactly what's happening. So let's do that now. So now that we see this call to the superclass constructor, we know that we have to go up to the person class and find a constructor with no arguments. So we go up to the person class and we look for a constructor with no arguments. I don't really see one, do you? It's not there. And it turns out that Java will not insert one for us if we already have a constructor that takes an argument. So this is going to cause a compile error. So if you chose compile error, you'd be correct. And the reason we're going through this example is it turns out it happens a lot that you have a situation like this. I have it happen to me all the time. And the compile error that you're going to get is very, very cryptic. You're going to read it and be like, what are you talking about? There's no constructor with no arguments. I didn't try to call a constructor with no arguments. Well, you didn't, but Java did, and that's what's happening.
Hi, and welcome back to our module on polymorphism and inheritance in Java. Today we're going to be talking about method overriding. And you've already used method overriding when you did draw and setup methods back when you designed your GUI, but here we're going to dive into method overriding in a bit more detail. So the goal here today is to be able to create methods that override from superclass methods and to be able to contrast overloading from method overriding. Back when we first started talking about inheritance, we had 3 goals, and overriding really helps us have all 3. So we want to have common code in one parent class. And we can do this if we don't override a method. So if the method just exists in the superclass, we get that common code. But if we want our subclasses to behave differently, all we have to do is override the method, and now we get that different behavior. And because of polymorphism, which we'll get to in the next set of videos, we'll see that this allows us to be able to have all of our objects in one structure and still be able to call the appropriate method. Now, it's really common for new learners to mix up overloading and overriding. So I want to talk just real quickly about overloading and overriding. Overloading is the same class that has the same method name but different parameters. So this is a different method signature within the same class. This is different than method overriding, where you have a subclass that has the same method signature, which means the same name, same parameters, as a superclass. So now let's start looking at some more detail with a few examples. So the first example is to look at the object class itself. So we have a method in the object class called toString. Now the odds are you probably already ran a toString method before, but if you haven't, toString prints the contents, or a string representation essentially, of an object. Because it's in the object class, all objects in Java can override it. So let's do this for our hierarchy. So we have our person class at the top. It has a name and a get name, and we're going to add the toString method to it. And to do so, we're going to override that object method's toString method. Now, a really basic way to do this would be to just return the name. And since all we have right now in our person class is a name, this is really all we can really do. And then in our code that calls it, we're going to create a person P, we're going to create a person that has the name Tim, and then we're going to call this method. So you can just do system.out.println and put p.toString, and that will return a string, and that is what we want. And it doesn't call the object toString method, it's going to call the person toString method because of overriding. Now it turns out the toString here in this context is unnecessary because println actually automatically calls toString if you ever pass an object as a parameter to println. So I'm going to just display it this way from here on. Now if we run this code, what's going to happen? It's just going to print Tim. All right, well let's add to our inheritance hierarchy. So now I'm going to go to my student class where we've already added a student ID and a get student ID, and now we're going to add the method toString. So here's the code to essentially have that student ID and the ability to get access to it. And now what I want is I want to be able to print a student ID number followed by the information about the person. In my first version of this code will look something like this. So return this.getStudentID, then a colon, and then this.getName. And the concern I would have here is what if the person changes? So the only reason I wrote this.getName right now is because I know that's what person does. So if you try to call toString on person, it prints the name. But person could change, so this really isn't the right way to do it. What I want to do instead is call the toString method within person. And to do that, I'm going to use that super keyword, just like we saw from the constructors, to say, I want the method from my superclass. So now, if we walk through this code, I'm going to do student s equals new student. I'm going to print out that, which is going to call the toString method. The question is, what do we expect to see happen? Well, we expect to see the student ID number now followed by the name, which is exactly what we wanted to have happen. What happens now if I change the reference type? What if I make the reference a person instead of a student? And I still try to call s.toString on that person. Is it going to call the student toString method, or is it going to call the person toString method? Well, what do we want to have happen? We want to have it print out the student information, which is exactly what it does. Why is it going to print the student method? Because of polymorphism. And we'll get into that in the next lesson. Welcome back. In this lesson, we get to start working with polymorphism in detail. Now, polymorphism, along with inheritance, is one of the most powerful features that we have in the Java language. So what we're going to do here is just revisit why we have polymorphism. So your goal from this video is just to be able to explain its purpose and why we have it. Now, we've already done some polymorphism. You've already had a different superclass reference pointing to a subclass object. That, at its very heart, is polymorphism. What we're going to do then is do a couple of examples then with the hierarchy that we already have. So our hierarchy again is the person class, or the student class, or the faculty class. And now you've noticed that I've added to this faculty class to now have, it has an employee ID number, which is a string. It has a toString method, just like person does, just like student does. So all three of our classes now have toString methods. We're going to use this in the next context. We said in the very first videos on inheritance that one of the nice features is that you can have a single data structure point to multiple objects of that type. So I'm allowed to have a person array, which has room for 3 references, and have one of those references be a person, one of those references be a student, and one of those references be faculty. And the reason I'm allowed to do that is because a person is a person, a student is a person, and a faculty is a person. So I'm allowed to have this array. And what I'd like to do then is just iterate through the array and call the toString method on each of the elements. And what I want you to do is pause for a few seconds and think about what should happen when I do this. All right, if you were saying, I hope it calls the toString method for each of the objects based on their dynamic type, you're spot on. That's exactly what we want to have happen. I want the toString method for person to call the person's toString method. And I want the toString method for student to call the student's toString method. And I want the toString method being called on that third element to be called on the faculty member, the faculty object. And that's exactly what happens. So what polymorphism gives us is the ability to keep all of our objects in one big collection and then call methods on every single one of those elements, and the appropriate method is what actually gets called. But this does get a little confusing at times because we have a different reference pointing to a different type of object. To understand this in more depth, we have to look at compile time rules and runtime rules, and we'll do that in the next video.
Hello, I'm Ken. One time when I struggled during a program assignment was based on polymorphism and inheritance. What you had to do was create classes of different animals and connect them through inheritance and polymorphism. And what was hard about it, when I first opened the assignment, it was just a blank screen, a blank text editor, and I was overwhelmed. I didn't know where to start. What really helped was the online posting and everyone conversating on Piazza and that forum. What also helped was just really not stepping away from it just a little bit and giving it some time, just because I was so overwhelmed by it at that moment. Just really calming down and taking a break from the material and then revisiting it allowed me to, I think, get it done.
Hi, welcome back to our lessons on polymorphism. So with the lessons today, we're going to focus on compile time rules versus runtime rules. And once you understand that, all the magic that might appear to be associated with polymorphism goes away. There's a saying here in our intro classes at UCSD, which is think like a compiler, act like a runtime environment. That phrase comes from one of our really popular lectures here, Rick Ord. And why I like that saying so much is that there are 2 pieces that happen whenever you execute code. The first step is a compiler has to interpret the code you wrote, and the second step, that's when the runtime environment gets to execute that interpreted code. So you have to be able to see your code in 2 lights. You have to do this especially when we're thinking about polymorphism. And the truth is, you've already started to wear these 2 hats when we started talking about constructors. So let's continue with this by looking at the compile time rules and the runtime rules when it comes to polymorphism. So what this is going to allow us to do then is to step through the decisions made both at compile time and at runtime. So the rules, first off, compiler rules. The compiler can only know the reference type. Doesn't know the runtime type of the object, it only knows the reference type, which means when you try to call a method on an object, it can only look in that reference type class for that method. The goal of the compiler is to output a method signature, which will then be executed at runtime. So let's walk through this in detail with our example. So we have our person class, we have our student class. I've got a person reference point to a student object, and I'm going to call the toString method on that student object. The compiler only knows that this is a person reference. So when you try to call toString, it's going to look in the person class and find that toString method. Then it's going to emit a method signature, a compile time, which is a no parameter toString method, which is to be executed at runtime. That leads us then to our runtime rules. At runtime, you have to follow the exact runtime type of the object to find that method. So what you're going to do is match the method signature, which was emitted at compile time, to the appropriate method within the actual runtime class. Let's walk through that. Where we left off was the compiler had already emitted a method signature, which was toString with no arguments. And when we attempt to do s.toString, now at runtime, it knows that s is actually a student object. So it's going to find the toString method in student, and that's what's going to be executed at runtime. So now that we know these rules, let's look at a couple more examples. So the first is, let's say I have a person class, s, pointing to a student object. And what I want to do is call the getSID method on my student. What I want you to do is take a few seconds to think about this. What do you think is going to happen? All right, if you said this is going to cause problems, you're right. The reason it's going to cause problems is because the compiler can only know that s is a person reference. So the compiler can only look in the person class for that method. It's going to look there, and it's not going to find a getSID method, which means the compiler is going to give you an error. It's going to say, I can't find this method in the person class. Now, you might say, well, wait a second, I know this is always going to be a student object. It should be allowed to call SID. Well, we're going to be able to do that, but we're going to have to do that through explicit casting. We're going to cover casting in the next video. Continuing working with polymorphism in Java, specifically continuing with the compile time decisions and the runtime decisions that are made. To help aid a compiler, we can sometimes use the term casting. So the goal of this video is to be able to walk through those decisions at compile time and runtime, and also be able to cast objects. Where we left off in the last video was we had just done this example where we attempted to call the getSID method on a student object, but we were unable to because s is a person reference. What we'd like to be able to do is tell the compiler, hey, I know this is going to be a student at runtime. Could you let me call this method? The way to do that is casting. Now, casting of objects works very similarly to the way it works for primitive types. So we always have automatic type promotion, so you can always go from int to a double, and likewise, you can always go from a subclass up to a superclass reference. This technique is sometimes called widening. Likewise, we can explicitly narrow, so we can explicitly cast from a double to an int, and likewise, we could take a superclass and explicitly cast it down to be a subclass. This again is known as narrowing. Now, I can't stress this enough. You have to be careful when you narrow. The reason why is because you're telling the compiler to trust you. You're saying, trust me, compiler. I know this is going to be a subclass reference at runtime. And the compiler's going to believe you, and then you're going to try to do this at runtime. So let's walk through this again now. Let's fix this with casting. So I've got my person reference, student object. I can't call getSID because it's not in person. But the way I can fix this is by casting it to be a student reference, and by doing so, now the compiler will look in student, find getSID, and it'll let you execute this code. This is going to work just fine. But what if I change this and I make it so that it's a person reference pointing to a person object? I'm still going to cast to student, and I'm going to try to call getSID. And what I want you to do is pause for a second and think, what do you think should happen here? If you're thinking that this is going to cause problems, you're on the right track. There is no getSID method in person. How could it possibly call that? And the problem is really going to come about at the point of the cast. If you try to do this, you're going to get a runtime error, and it's going to say class cast exception. What it tried to do was it tried to cast your person to a student, and it couldn't because it's a person object. In a sense, you've broken the compiler's trust at this point. Again, you told the compiler, I know this is going to be a student, and it didn't turn out to be. What would be really great is if we could just test this. Say, is this a student before I do the cast? And the way we can do this is using an operator, instance of. So this performs a runtime check of whether or not there's an is-a relationship. So if you say s instance of student, what it's going to do is going to check, is s an instance of a student? Or does s have an is-a relationship with student at runtime? Now if you do this check with a conditional, you'll then be able to only execute this when it actually is a student object. At this point, with the compile time decisions we discussed and the runtime decisions we discussed, polymorphism should make a great deal more sense.
In this concept challenge, we're going to have some fun with polymorphism and dynamic binding. We want it to be a little bit challenging, but hopefully not too far beyond the reach of what you can do with your new knowledge about how this works. So you know the drill. You're going to pause, answer the question on your own, discuss it with people around you or online, watch our learner videos, and then confirm your understanding with our explanation. So what's the problem? Here it is. We've got two classes for you, the student class and the person class. The person class is the base class. It has a private member variable name and then a number of methods. There's one constructor, it takes an argument. There's a method called isAsleep. It takes an integer argument and it returns a Boolean. The integer argument indicates the time of day in terms of hours on a 24-hour clock. And a person is asleep between the hours of 10 p.m. or 22 and 7 a.m. So between those hours, isAsleep will return true. It also has a toString method, which just returns its name. And then it has a status method, which also takes an integer argument for the hour. And what it's going to do is it's going to check to see if the person is asleep at that hour. And if it is, it will say the person is offline. It'll print a message to that effect. And if they're not asleep, then it'll print a message saying the person is online. So that's the person class. The student class extends the person class. And so it inherits a bunch of things from the person. And then what it does is it overrides the isAsleep method to slightly change the hours that a student is asleep. So a student in our world here is only asleep between the hours of 2 a.m. and 8 a.m. So if we call isAsleep between those hours, then the student will report being asleep. So the question for you is, what happens when we create a reference to a person, set that reference equal to a new student object, and then call the status method on that object at time 1 in the morning?
I'm Alicia.
I'm Joanna.
And I'm Justin.
So actually, when I looked at this code, I was wondering if person can actually even be a student.
I think student can be a person since it extends person. So
I agree with Justin because student is a person, and you know it's a person, so it's a more specific type of person.
What do you think it prints out?
I don't know. Will it even print out? Because there are two, if you look in the public class person and in the class student, there are, both of them have a method isAsleep, which is called in the second line of the method status. So how does the compiler know which one to call? So wouldn't it just freak out and stop and be an error?
I think it has something to do with the this call.
Oh.
So maybe this tells it which method it's calling. And I guess since we can have it be a student, it's probably calling students is asleep.
Yeah, I think that's correct. Yeah.
What I was confused about was within status,
Yes.
it calls isAsleep. And this, well, it calls isAsleep when it's in person. So shouldn't this be a person?
That's good. It's pretty tricky.
But we assigned person to be a student, right? So at this point, perhaps at compile time, maybe it'll call is asleep in the person class, but maybe at runtime, it'll say this is a student, and then call students is asleep.
Okay.
All right, there's a lot going on here, so let's trace through this very carefully. First thing we have to think about is, even though P is a person reference, the actual object it refers to is a student. So when we call P.status at 1 in the morning, we're calling that .status on a student object. This is what Java does at runtime. It determines that P refers to a student object, and that's the type that it's going to call the status method on. So we're going to look in the student class for the status method. And so we look here. Well, we don't see a status method, but that's no problem because student extends person. So Java will just go ahead and look in the superclass to see if there's a status method there. And it turns out there is. Here's our status method. So we can start tracing through the status method to see what actually happens. First thing we do is we have an if statement. And that if statement asks, this dot is asleep. So the question is this asleep at the particular hour? Now what is this? Well, even though we're currently in the person class, that's where the code is, this is, at runtime, determined to be a student object because the student object is the one that called this method originally. So this dynamically binds to the student object, and that's the class where the isAsleep gets called. So we go back down here and we use the student's version of isAsleep to determine if the student is asleep at 1 in the morning. Now, I already said that the student only sleeps between 2 in the morning and 8 in the morning, so the student is not asleep at 1 o'clock. And so we'll fall through to this else condition and print out that this student is online, says now online. This is what it'll print, now online. And the student's name is Sally. That's it. All right, if you thought that last polymorphism concept challenge was fun, you're going to love this one. This one's going to bring it to a whole new level. It's more challenging than the last one we just gave you. In fact, it's beyond what we've even explicitly taught you. So we want you to really push the bounds of your reasoning and understanding. You know the drill. Do it yourself, discuss it with your friends, watch our videos to confirm your understanding. So here's the challenge. We now have 3 classes in an inheritance hierarchy. So the base class that we're working with here is a person, and it has 2 methods, method 1 and method 2. We have a class that extends the person class, which is the student class. It overrides both method 1 and method 2. And then we have the undergrad class, which extends the student class, and it inherits the method 1 method, but it overrides the method 2 method. So that's in a nutshell what we're working with. Here's the code in more detail, and you're going to need to work through this code and look at it carefully as you work through this challenge. And what the challenge is when we create a new undergraduate object, refer to it with a reference of type person, and then we call method 1 on that newly created object, what gets printed out?
Hi, I'm Steven.
Hi, I'm Joanna.
Hi, I'm Justin.
So, what do you think?
I don't know, I was getting caught up on this first one. So it says it calls method 1, but I don't see a method 1 in undergrad. So I think it would be a compile error.
I don't think it'll be a compiler error. If you notice, undergrad extends student, so in the student class there's a method 1, so I think it inherits that method.
Yeah, I agree. So it does print student 1. What I got a little bit tripped up on was I wasn't sure which, when it calls super.method1 in the method 1 of the student class, I wasn't sure which method 1 it would call, because isn't it in undergrad? So wouldn't the super.method1, it might just call student and go into like an infinite, like calling itself over and over, right?
Yeah, I could see how you get caught up on that. But I think when super, it's always talking about the class above it. So I think it'd actually be calling the method 1 in the person class.
Okay.
What about method 2? Does it call students method too? Or which method too does it refer to?
I think that since it is an undergrad, it will call undergrad's method too, and it'll print undergrad too. So if it doesn't go infinitely, like you said, then it should be D.
All right, let's trace this together because it's non-trivial. We're going to start our tracing up here where the method is originally called. So the type of the object referred to by you is an undergraduate. So at runtime, that's where Java is going to look for this method, method 1. Well, if you look down here in the undergrad class, we don't see a method 1. But luckily, we can see that undergrad extends student. So Java's going to go look in the student class for method 1. So looking up here in student class, it finds method 1. Great. So now I can start executing. So the first thing it's going to do is execute that first line, which prints student 1. So what gets printed so far is student 1. Now we keep going to the next line. The next line says super.method1. So what is the superclass of the student class? Well, it's the person class. So this happens at compile time. When this code is compiled, Java notices that there's a call to the superclass inside this method. And so it looks and sees, well, what is the superclass of student? It's person. So it's going to bind to the method 1 inside the person class. And that's where we'll go now. So we go up here to method 1 and we execute its code. Its code says it should print out person 1. So that's what gets printed next. So far we've printed student 1 first and then person 1. But let's continue. We now return back to where we were, which was inside the method 1 method in the student class, and we say call method 2. All right, well, where are we going to go now? Which method 2 are we talking about? In order to answer this question, we first need to notice that since we don't have a calling object at this point, what Java is going to do is insert the keyword this. So we're calling method 2 on the calling object. Now, as you saw from the last concept challenge on polymorphism, this is going to bind at runtime. So we're going to look at the actual type of the object this at runtime. This is what's tricky about this example. So the actual type of this object at runtime, as you recall, was an undergrad object. So we're going to go down here into the undergrad class and call the method 2 inside the undergrad class. So that's going to print out undergrad 2, and we have the following that gets printed. First, student 1, then person 1, and then finally, undergrad 2. So the purpose of this example was to show you the difference between what happens with a call to super and then a method, and a call to this and a method. Those calls to super and then a method get bound at compile time. So at compile time, Java is going to look at the code and figure out what class it's in and what the superclass of that class is. But when we call this and then a method name, that's going to happen at runtime. So Java is going to use the actual type of the object at runtime. It's a little confusing, but understanding these details can help you debug some nasty bugs that you might otherwise encounter in your code. So good luck.
All right, welcome back to our module on inheritance and polymorphism in Java. In this video, we're going to be discussing abstract classes and interfaces. Specifically, we're going to be talking about what it means to be an abstract class or an interface, and how to use keywords like abstract or interface. We're going to be comparing inheritance of implementation against inheritance of interface, and we're going to give you the tools to help decide between an abstract class or an interface when designing your class hierarchy. To get started, let's look at our hypothetical with our person class. So now we're still working at the university, but let's change things a bit. Let's change it so we're working for the accounting department. And here we're essentially responsible for handling bills and paychecks. Now in this context, it doesn't really make sense to have a generic person object anymore. Right? We're only going to be working either with students or faculty. And we're also going to change the context in the sense that I want to be able to send out monthly statements. So essentially I'm going to want a method in the person class which sends out a monthly statement to either students or faculty. the features I'd like to have here is I'd like to be able to force my subclasses, both my student and my faculty class, to override this method. I'd like to stop having actual person objects because they don't make sense in this context anymore. But I'd like to keep having person references. And I'd also like to keep that common code we had, like the name of the person. If I want to do all these things, I want to use an abstract class. The way to define an abstract class is essentially just to use the keyword abstract. So if I say public abstract class person, it means this class, you cannot create instances of objects of this type. So I can't actually create an object of type person, but I now can create objects of, say, derived classes, which are concrete. If I have any method within this class be abstract, then I have to make the whole class abstract. But what I can do then is say, have an abstract, public abstract void monthly statement. I can say my derived classes have to override this method. It's a nice way of forcing the subclasses to have methods. With an abstract class, you get two things. You get to inherit both implementation and interface. And what I mean by that is with an implementation, you get instance variables or methods, which essentially define that common behavior that any person should have. And you also get an interface. You say what method signatures have to be overridden in my subclasses. Now there's going to be times when you don't necessarily want both. You may just want the interface. If you want just the interface, then you're going to use interfaces. And if we go back to our example, I really believe an abstract class is appropriate for the hypothetical that we were just talking about. But let's say that you had no common code in the person class. If there's nothing common there, then you just use an interface. And an interface will give us the ability to force subclasses to have the method, to stop having actual person objects, and will allow us to keep having person references. Now, interfaces only define the methods that are required, and classes can inherit actually from multiple interfaces. So you can inherit from an abstract class and also inherit from multiple interfaces, all within one class. So let's look at an example of an interface. So the most common one discussed is the comparable interface. Now, comparable gives you the ability to compare to an object to another object of that same type. You're going to notice some terminology here, those brackets with the E, that refers to generics. And we'll discuss those a bit more later. But this allows us to compare two objects. Now, why would I want an interface like this? Take a few seconds to think about it, and we'll come back. All right. If you're thinking it's useful to be able to compare objects in case you, say, want to sort them, that's exactly the purpose for having comparable. So if you want to have a data structure and know some way of storing and ordering among those objects, comparable is exactly what you want to do for the objects. And the way that we would do this for, say, the person class is to say, have the person class implement a comparable interface. And then within that, all I have to do is override that one method, compare to, and then define the behavior I want. In this case, I've defined the behavior to be a comparison of the strings using the compare to method in the string class, because the string class implements the comparable interface. So if you're trying to design a class hierarchy, you're often going to be wondering, should I be making this an interface or an abstract class? And the general rule of thumb is, if you just want to require methods, that's an interface. If you want to potentially require methods, you don't have to, but if you potentially want to require methods, and you want to require common behavior, that's where an abstract class comes in.
So one of the ways that Google is able to tell some new application or service that you have successfully logged in is by issuing tokens. And there are many different reasons that an application or website can ask for tokens from an identity provider like Google. But when we started out, there were far fewer. And the different flows that determine what kind of token you will get back are determined by, say, a parameter called grant type. So I can ask for a token with a grant type device, or with a grant type access token, or with a grant type code, or with a grant type assertion. Now, as the years grew on, we got more and more grant types that we added to this same endpoint. So whenever someone goes to googleapis.com/v3/token and asks for a particular grant type, they all make a call to the same class in our code base. Now, obviously, over the past 2 years, that particular class has grown really, really large. But there's a lot of similarities between each of the different grant types or what needs to be done. The overall processing of the request, the validation of the various other parameters that are sent into the request, and the eventual creation of a response that needs to be sent back to the user, all of which will always contain a token. So it's possible to pull out each of these aspects, or to pull out each of these into a separate method and put them into an abstract class, so that each grant type can be processed separately and they all get to do the same thing, which is to create a token response. And that's my project for this quarter, and essentially that's inheritance.
As with the previous walkthroughs, it's a good idea to make sure you watch the overview video before you walk through this one. This overview video again gives you the high-level picture of what's being asked of you for this project. So let's just dive right into the write-up. In this programming assignment, we're going to be adding new features just like we did for Module 3. It's a good idea to make sure you read through the learning outcomes as well as the introduction. Again, just like in the last module, make sure you have these two references open when you're working. So what are you going to do for this assignment? First is you're going to make sure you find and open up the starter code. So here's our starter code for Module 4 right over here, and you're going to notice that we have 5 classes in there. So that's kind of your first step. Open up these files, and you may want to check to see what the relationship is between them. So for example, Earthquake City Map, it sends papplet just like it did before. Then you'll notice that City Marker is going to extend Simple Point Marker, and so on. It's a good idea to walk through those so you can figure out the class hierarchy. In the next step, you're going to want to trace to the starter code, predict what happens when you run it, and then run it. Now notice that we've made some changes to the code from the previous assignment, so you're going to want to make sure you identify what those changes are. The next major step is to implement the isLand method in the Earthquake City Map class. So let's go to Earthquake City Map. You scroll down for a while. You're going to find that there is a earthquake. Scroll down even more. You're going to find the isLand method. The reason we're going to use this is for this next step in the assignment, where you're trying to figure out whether or not an earthquake occurred in land or under the oceans. And if it did occur in the land, you're going to know what country it occurred in. Now the good news is we've given you a method a little bit further down called isInCountry. So this is going to allow you to essentially check, is my earthquake occurring in this country? And the process of checking that is actually going to set that property of the country that it's part of. So if it is actually inside that country, it will set the earthquake to be attached essentially to that country. You'll want to use that in a future step. So you want to use this method, isInCountry, within your isLand method. The next step is to implement your printQuakes method. The idea for the printQuakes method is to print out all the earthquakes that occur in each country, as long as there's at least one earthquake in that country, and then also print out how many earthquakes occurred in the ocean. You're going to want to use that country property that's attached to earthquakes to help solve this. The next step, after you've coded these, is just like any piece of code, you're going to test it to make sure it's working properly. So the way to test this is we've given you two tester input files called test1.atom and test2.atom. And you can essentially just use those test cases to make sure you get the right output. And we've given you the test1.out.text and the test2.out.text as essentially the right answers to verify against. If your printQuakes method and your isLand method are working properly, this should work just fine. Your next step is to draw a UML class hierarchy. As I was showing you just before, you can always look in, say, earthquake marker to figure out, go back to your code, look in earthquake marker, and see what it extends. So this extends simple point marker. And we know that simple point marker, if you look in the documentation, extends from marker. So this is the way that you're going to essentially piece this all together, what the class UML hierarchy looks like. The next step is to complete the method definition for the draw method within your city marker class, because we're going to want to add all the cities to the map. So this is essentially our goal at this point, and to do this you're going to go into your city marker class, you're going to find the draw method, and you're going to find that there's a big to-do which says this is where you're going to want to draw a triangle to represent the city marker. To draw a triangle, again, you're going to have to think about where is the center location, which is denoted by this X and this Y, and how will I draw a triangle essentially around that. Your next step in the project is going to be completing the method definitions for draw earthquake in the land quake marker class and draw earthquake in the ocean quake marker class. Notice that if you go into earthquake marker, there is a draw earthquake class, draw earthquake method, that's an abstract method. So this is a method that you're going to have to override within the derived classes. So both land quake marker and ocean quake marker have to have these methods. They already have them, but they're essentially stubs. They don't do anything yet. So for draw earthquakes, you're going to want to add the code to draw a circle in the land quake marker class, and for the ocean quake marker class you're going to add the code to draw a square. Your next step is going to be completing the color determine method within the earthquake marker class. Let's look real quickly at where that's called and then what it's going to do. So if we pull up our code for earthquake marker, we're going to find we have a method called draw. So this is what the earthquake marker is going to look like, and it essentially does a few steps. It's going to call this color determine method, which we know we have to write for this step, and then it calls that draw earthquake method, which you wrote for the previous step. So let's look in the color determine method. Within the color determine method, we don't have any code yet. So what we're going to want to do here is figure out whether or not it should be red, blue, or yellow. These are just colors we suggest based on the depth of the earthquake. If you're curious to figure out, well, how do I figure out depth? Notice that there's a bunch of helper methods within earthquake marker class that are going to be useful to you, from getting the magnitude to getting the depth. Now I would talk real quickly about why we laid this out this way. So you have your draw method in the earthquake marker class, which is the parent class of both land quake marker and ocean quake marker. Because you're going to want to determine the color to be red, green, or blue, regardless of whether or not it's a land or an ocean quake marker, it actually makes sense to put this color determination call in the parent class and define it there. Because if you try to put in the subclasses, land quake marker or ocean quake marker, you just write the same code twice, and that doesn't make any sense. Alright, back to our steps. We are almost done at this point. If you want, you can add this extra feature, which is to check to see if the earthquake has occurred recently, and if it has, then you'll want to draw these kind of X's. And the place you want to do that is actually, we just saw it, we scrolled right past it. You want to check to see right here, right after draw earthquake, whether or not it's occurred within the last day. If it has occurred within the past day, you'll want to put an X. Alright, I hope these steps help you get started. As always with these projects, you want to work through this step by step. So go right back up to step 1 and start working through. You want to read this fairly carefully because we try to give you the necessary details to solve that part of the problem in text right here. If you do run into problems though, feel free to review the videos, check the forums, and again, try to have fun.
You've made it to our final module, where we'll talk about searching and sorting, as well as giving you the opportunity to extend the project in a direction of your choosing. All right, here's your overview of the last part of the project. I'm actually only going to demo part of the last part of the project, because the very last part of the project is an open-ended extension of your choice. So you'll get to have some freedom and some creativity with that. Really, anything goes. It's up to you. But for the first part of the project that everybody will do, what we're asking you to do is actually make no changes to the map at all. So your map is going to behave basically just like it did in the last part of the programming assignment. But what you are going to add is you're going to add code that will sort the earthquakes in descending order of magnitude. So when you run the program now, in addition to printing out the number of earthquakes per country, it will also print out a list of the earthquakes in the RSS feed that you read sorted in reverse order. So strongest magnitude first, and then in descending order. And you'll write a function that allows you to control the number of earthquakes that get printed out here. So that's really it, and then you'll get to work on that open-ended extension. So have fun with it. You're going to get to learn about some searching and sorting algorithms to write this part of the project, and then dive into that open-ended extension.
Hi, my name is Nida Yi. I'm on the Google Fiber software engineering team. Search and sort are both used very commonly in the work I do at Google Fiber. Actually, don't some people use the word Google and search interchangeably? Let me Google this movie. Can you Google that recipe? On fiber.google.com, which my team works on, one of the most used features by our users is the check address button. It lets our users enter an address and check whether Google Fiber is coming to, or if it's already available in that location. Once user enters an address, the system searches through an address database of millions and millions of records to find the Google Fiber readiness status for that entered address. And the result is expected to come back almost instantaneously to the user. For that, we need a very robust and high-performing search algorithm. Sorting is used in day-to-day programming too. For instance, to show a list of choices of something in an organized format, we sort the list before displaying them to the user. In Google Fiber sign-up web pages, the sports TV packages available for customers to choose from are displayed in alphabetical order.
All right, in this lesson, we're going to learn some core algorithms for searching for data. Searching for data is something you probably do every day, many times a day. And so we're going to focus on some of the fundamentals of how to search for data and how to do that quickly. So by the end of this video, you're going to be able to motivate why we want to search for data, as well as to be able to write code to perform linear search. And then we'll build on this in subsequent videos. So let's start off with a motivating example. Say I'm going on a trip, which I am. I'm going on a trip and I want to plan my airline travel. And in order to do so, if you've booked airline tickets online, you probably know that those airline ticket booking sites use a 3-letter code for the airport that you're trying to book from. So I'm coming from my hometown of San Diego, and I want to figure out what is the 3-letter code for the airport in San Diego. So there's a lot of ways I can find this information, and probably one of the most popular ways is I can go to my favorite search engine like Google and type in this query into Google, and Google will go off and search the information that's on the web to find me a page that will hopefully answer my question. Now, this is an example of search, and in fact, internet search is a fairly complex search, so there's a lot going on here in order to organize all the data and return me results quickly, results that I find useful, and so on and so forth. So this kind of search is a little bit beyond the scope of this course. But the idea is the same. We have a big repository of data, and I want to find some information in that data in order to answer some questions about it. This is kind of fundamental to almost everything that we do in computer science. So let's simplify the problem slightly. Instead of searching the entire internet, I'm going to take a subset of the data on the internet, a very small subset, that I can find in a file called airports.dat, which is on the website whose URL that you see here. And this file has information about almost 7,000 different airports around the world. And it's represented in terms of a number of different fields. So each line in the file has a number of different comma-separated fields. Those fields include a unique ID inside this database, the name of the airport, the name of the city that the airport is located in, the name of the country, and that 3-letter airport code, and a bunch of other information as well, which you can find out by going to that URL. So I'm going to be searching within this lesson in only this data, not on the whole internet. So what I'm going to do is I'm going to read in all of this data into my Java program, and then I'll search for a particular city that I care about in order to find out some information about its airport, like its 3-letter code. So here's the first step that I need in order to read in this data into my computer program. I need some way to represent this data. So we know how to do that. We know how to write classes and create instances of those classes. So let's do that. Let's write a class called airport, and it's going to have a field for each piece of information we want to represent about a particular airport. In this case, we'll represent a city, a country, and that 3-letter code, as well as whatever information we want to keep about our airport. Each of these fields is going to be private. As I mentioned, a rule of thumb is to keep all of our data private, but we'll provide getters so we can access each of those pieces of information. So they'll get set in the constructor when I read in the data from this file, and then I have access to all of these pieces of information for each airport that's stored in my program. So let's imagine that I've done that. I've written some code that reads in this file that has all this information about these airports into my Java program by creating one instance of this airport class for each airport in that file. I'm going to simplify things a lot, and I'm going to imagine that my entire file only had 8 airports in it. So I'll read those all into each into an individual airport object, which I'm going to store in an array. So my array is going to be called airports. It's an array of references to airport objects, so one object for each airport. And what's stored in the array, again, is a reference to this object, which you see depicted here in the blue boxes. And those objects exist somewhere in your computer's memory, somewhere in the heap. And again, what gets stored in the array is the references to those objects. But this diagram is a little bit too complicated for my needs for this lesson, so I'm going to simplify things a little bit by writing all of the information from each object directly in the box for the array itself. So this is going to be my representation of the data that I've now read into my computer's memory from that big airports.dat file. And again, this is a very simplified version for the purpose of illustration. So now I've got all the data about all my airports read into my array, and now I can write a program to answer questions about the airports in that array. And in order to answer a question about a particular city's airport, I have to find that airport object first. So let's look at how to do that. So let's say I'm looking for information about the Beijing airport, and I want to find out what is the 3-letter city code of that airport, Beijing. So how am I going to do this? Well, first I need to find it. One way I can do that is just basically by starting at the beginning of my array and looking at each element in my array one after the next until I come across the airport I'm looking for, or I get to the end of my array and I haven't found it. And that's an algorithm called linear search, which we're going to look at right now. The way it works is I start at the beginning of my array, so I start at index position 0, which is the first index in my array. And then I'm going to look at the element in that index, and I'm going to ask, is this a match for the thing that I'm looking for? In this case, I'll ask, is the string to find, which is the name of the city I'm trying to find, equal to the city field in the object that's located in that array position? And in this case, I'll see that Montreal is the city in the object at position 0, and Beijing is the city I'm looking for. Those two strings are not the same, so there's no match. I'll go on to the next element in my array by incrementing index by 1. So now I look at the element in position 1. Is that a match? Compare the cities. Again, I find that's not a match, so I'll continue. Here's the index position 2. Match? Nope, still not a match. Index position 3. Still not a match. Index position 4. Finally, I look at index position 4 and I see that its city is Beijing, which exactly matches the city that I'm looking for. So now I've found the airport object in question, and I can use it to answer the question of what is the 3-letter code for Beijing. So I read that out of the entry, and I can return it to my user. So this is a match, and we're done. That, in a nutshell, is the algorithm called linear search. And here's how it looks in pseudocode. So in the beginning, we initialize that index variable to the start of our array. And then we're going to have a loop that keeps going as long as we haven't found what we're looking for, in which case we just return it, or we get to the end of the array, in which case we conclude that the element is not in our array. So while our index is not equal to the length of our array, while it's less than the length of our array, we'll look at the element in the particular position where index is referencing, where index says we should look, see if the city in that element matches the city we're trying to find. If it does, we'll return the 3-letter code, thus breaking the loop and breaking the whole method, basically returning out of that method. Otherwise, we'll keep going by incrementing our index variable by 1 and going back to the top of the loop. When the loop ends, we can conclude that the city we were looking for was not in the array at all, and we return some value to indicate that we didn't find it. Okay, so now it's your turn. This is an interactive piece of the video. I want you to pause the video, and I want you to get out either a piece of paper and a pencil, or better yet, just open up Eclipse and go ahead and write the code for linear search before you unpause the video. Once you unpause the video, we'll go back over it, but I really do want you to take a shot at going back to the algorithm that you just saw, going back to the example, and writing out this code. See if you can do it. I bet you can. All right, welcome back. I hope you had a good time writing this program, writing this method. And I'm now going to write it out step by step on my tablet PC. If you really think you've got it, no problems, just go ahead and zoom ahead. You can see my solution, just check it against yours. But I encourage you to also follow me through the thought process as I write this code. So thinking back to that algorithm, the first thing that we need to do is we need to declare a new variable called index, which is going to be the variable that steps us through the array. So I'm going to do that. I'm going to declare a new variable. It's type integer called index, and its initial value is 0. So now I'm ready for my loop. And my loop is going to be a while loop. And it's going to run as long as that variable index is less than the length of my array. So airports dot length. Okay, so now inside the loop, remember what we want to do is we want to look at the airport object that's in the cell indicated by that index variable. So we're going to get that airport object out first and store it in its own separate variable just to make the code a little bit cleaner. So I'll declare a new variable, airport A equals airports at position index. Now I'm ready to work with that airport object, and I can compare the string that I'm trying to find, the name of the city I'm trying to find, to the name of the airport that's in that object pointed to by the variable A. So I do that with an if statement, because if they're equal, I want to do something. So if my toFind equals a dot get city. Now notice that I've used the dot equals method here instead of the equals equals operator. And that's pretty important, because what dot equals is saying to Java is, I want to compare the string representations in these two objects by essentially their characters. I want to know, are they the same string? I don't care if they're the exact same object in memory. I just want to know, is it the same string of characters? And the dot equals method will do that. On the other hand, the equals equals operator, that's just going to compare the references that are stored in two particular variables. And so that will only be true if those are actually the same literal object in Java's memory. So in this case, and almost always when you're working with objects, the dot equals method is the appropriate way to compare those two different objects. So if I find that the string that I'm looking for is equal to the object's city that's stored in A, then I'm going to return the airport code. So return a.getCode. Otherwise, I need to keep looking. So there's nothing really more to do except to go on to the next location. So I can say index plus plus. Notice I don't need an else statement here, because if the if statement was true, then I just return out of the function and there's nothing more to be done. But if that if statement is not true, then I increment my index and I'll go back to the top of my while loop and repeat the process. Now if my while loop completes, that means my index has gotten all the way to the end of my array and I still haven't found the city that I'm looking for. So now I need to return some value that indicates that the city is not there. And in this case, I'll just return the value null. And that's appropriate because my method is supposed to return a string, so null is a good value to indicate, hey, we couldn't find it. It wasn't there. So that's it. That's it for the code. I want to leave you, oh, there's the code a little bit more cleaned up for you. But I do, after you're done sort of looking at and digesting the code, what I want to leave you with is a thought question. Actually, two thought questions. I want to ask the question of, if we're really unlucky, so if we're looking for some airport and it's very unluckily way at the end of the list, or it's not even in the list at all, how many airport objects are we going to have to look at to figure out either the airport code of this particular airport or to figure out that the airport's not in the list at all? So try to think of how you would answer that question in terms of some number of airports in the list. And then the more important question is, can we do better than that? Is there a way to answer this question faster? And that's what we're going to look at next. All right, in this video, we're going to improve on that linear searching algorithm that we looked at in the last video. And we're going to talk about an algorithm called binary search. So by the end of this video, you'll be able to explain what binary search is. You'll be able to write code to implement binary search. And you'll also be able to explain what conditions need to be true for binary search, as well as explain why binary search is so much better than linear search. All right, to motivate the need for binary search, let's go back to our linear search algorithm. We were looking for airport objects that had particular city names so that we could answer questions about those airports, like what are their three-letter airport codes. And what we did was we started at the beginning of our array at index position 0, and we just marched through this array element by element until we either found the city we were looking for or didn't find it but reached the end of the array, in which case we concluded that the city wasn't there. And it worked, but I asked you this thought question at the end of the video. I said, if we're very unlucky, how many elements do we have to look at in order to either find the city or conclude that it's not there? And then the second part of that thought question is, can we do better? So to answer this question, I'm going to step over into the real world. So I'm going to use a dictionary for this example. And this is a physical dictionary, which some of you maybe have never used in your lives. But this is what it looks like. It's an enormous book that has basically every word in this case, the English language in it. And I can find definitions of the word. I can find their origins, the spelling, so on and so forth. And so if I was going to find a word in this dictionary, here's an example of how I might use linear search to find that word. Let's say I'm looking for the word shark. So I open up my dictionary to the beginning. Let's see, okay. Acrobatics, let's see. All right, not on this page. And over here, not there. Acupuncture, nope, still not there. I'm looking. Are you getting bored yet? I'm getting very bored. I'm not going to make you watch me page through this dictionary, page after page, to find the word shark. It's way back here at the S's. This is going to take a really long time. But this is effectively what we were doing with linear search. We are starting at the beginning, looking all the way through in a row, our array. So what's a better approach to approach this problem? Well, it's an intuitive approach that we all use when we're opening a dictionary and trying to find a particular word. I don't open to the beginning because I know S is sort of in the middle towards the end of the alphabet. So I'm going to open sort of about halfway, maybe a little bit more. And I found myself in the R's. Okay, R, S, S comes after R, so I need to go a little bit further. So I'll take another chunk of the dictionary and flip it over. Oh, I've gone way too far. I'm now in the Y's. So let me flip back a little bit. Okay, now I find myself in the T's. Keep going back. Great, I'm in the S's, S-O. I need to go back a little bit more. So on and so forth until I find the word I'm looking for. And already, after only about 3 or 4 flips, I'm much closer to shark, the word I'm currently looking at is shirt, than I was when I started the A's and was just flipping through one page after another. So this is an example of the binary search algorithm. What I'm doing is I'm starting with my entire pool of data. In this case, it's the dictionary. And then I'm going to go halfway. And I'm going to reassess where I am to see if I've found the thing I'm looking at. And if I haven't found the thing I'm looking at, I'm going to use some information to decide whether I should go to the second half or go back to the first half. And then I just have a smaller version of the same problem where I'll again flip the book open about halfway. So notice each time I flip, my pages are getting smaller and smaller and smaller, the number of pages that I flip. And that's the exact same intuition behind binary search. So let's step back over now into the code so we can figure out how to write this algorithm on the computer. So we're going to need to implement this algorithm by taking our data in our array. And what we want to do is be able to cut the list in half each time. But if you look at the list as it stands right now, you'll notice a really important difference between the data that's in this list currently and the data that we had over here in our dictionary. So think about it for a second, maybe pause the video, see if you can identify the issue that we have right now. All right, hopefully you saw it. The list has to be sorted. The reason that we can eliminate half the data in the dictionary is that the list of words in the dictionary is in sorted order. So if I'm looking for a word that starts with S, I know that nothing that starts with P or before matters to me, and I can just get rid of it. So the same has to be true in order to do binary search of the data in an array. It has to be sorted on the element that you're looking for. So in this case, it's sorted now by city name. And here's how the binary search algorithm is going to work. I'm going to start by identifying the string I'm looking for. Let's look for Beijing again. Notice Beijing is now at the beginning, towards the beginning of the list, because it starts with B. And what I want to do now is I want to keep track of what range of the array is currently active to be searched versus the part of the array that's kind of been ruled out. So I'll keep track of the active range of the array with two variables, a low index and a high index. And these are just going to indicate where in my array I'm allowed to look for my data. Outside of this range, I've already eliminated all the possible data outside of the range. So my range starts with the whole array, so low starts at 0, and high is length minus 1, in this case 7. And now I want to go to that middle element, just like I did in the dictionary. So I calculate the midpoint. I calculate the midpoint by taking the low plus the high and then dividing by 2. In this case, it's 0 plus 7 divided by 2. Now you might be thinking, oh, okay, the midpoint is 3.5. But the problem is that there's no position 3.5 in my array. Luckily, we're doing integer division here. And so we don't need to worry about decimal points or anything like that because Java will automatically truncate that 0.5 and give me the value 3 as my middle position. So 0 plus 7 divided by 2 is 3. And that'll be my mid. So now I'm going to look at the element that's at that midpoint. In this case, it's the element Essen, representing the city Essen in Germany. And I'm going to compare it to the string that I'm looking for. I'm going to say, does it match? Because maybe I found the thing I'm looking for. In this case, no, it doesn't match. But instead of just giving up, now I need to get some more information out of this element. Now I want to know which half of my array can I discard. Should I discard the lower half or should I discard the greater half? So I'm going to compare Beijing to Essen and see whether Beijing is smaller or larger than Essen. And I'm doing this alphabetically. So Beijing comes before Essen in the alphabet. So Beijing is alphabetically smaller than Essen, which means that everything that's larger than Essen in my array couldn't possibly be the string I'm looking for. So I can eliminate it. And the way I eliminate it is by adjusting my range to no longer include those elements. So I'm going to move the high point in my range to be one less than that middle element that I've just ruled out. So this is what it looks like. I will change my high to be mid minus 1, which in this case is 2. And that effectively rules out everything that's either 3 or greater. So now I have another version of the exact same problem. I have a low value, which is still 0, and a high value of my range, which is now 2. So I only need to look in this range of the array, and I'll do it the exact same way I did it before. I calculate a mid value, so 0 plus 2 divided by 2, which is 1. And then I'll look at the element that's at that position, in this case it's Beijing. I compare the city I'm looking for, Beijing, to the city that I see, which is also Beijing, and I see that I found a match. So that's great, I'm done. I can just return that 3-letter city code. And you can see that this was a lot faster than my algorithm before, which had to look through about 5 different cities before it found Beijing. Now, I recognize that Beijing moved now, so it's further towards the beginning. But in general, this is going to be a lot faster than our linear search algorithm, and we'll look at just how much faster a little bit later in this lesson. So here's our algorithm in that same pseudocode we used before to look at the linear search algorithm. We're going to now need to initialize 2 variables, which are the low and high end of our range. And again, we initialize low to be 0 and high to be the length of the array minus 1, which is the last position in our array. So we've got the whole array in our range. Now we're going to enter a loop. And it's a little bit unclear yet when our loop is going to stop. So let's leave that as a question mark for the future. That'll be for you to think about in just a second. But inside the loop, here's what we're going to do. We're going to calculate that midpoint of the array, and then look at the element that's in that midpoint of the array. If that element matches the city that we're looking for, then we're done. We just return that 3-letter city code. Otherwise, if the city is alphabetically less than the city that we're looking for, if the city we're looking for is alphabetically less than the city at the element that we found, we want to update our range so that we're looking at only the small half of the array by moving high to be equal to mid minus 1. Otherwise, we know the city that we're looking for is in the larger half of the array, in which case we update our low value to be equal to mid plus 1. That's what the loop does. Again, we don't quite know when it stops, but if it stops, what that means is we haven't found the thing we're looking for, in which case we can conclude it's not there, and we'll just return that value that indicates that it's not there, for example, the value null. So that's pretty much it, and the only thing left to figure out is, when do we stop that while loop? This is a question I'm going to give to you. So I want you to spend some time thinking about what should the while loop condition be. And there's going to be a quiz that is going to ask you a bunch of choices, and you're going to want to select the correct choice. And in order to do that, what I recommend is that you work through on your own several examples of cities that aren't in this list. So trace through that algorithm using the loop that never ends yet to figure out what the algorithm does and figure out when it makes sense to stop that loop. So let's trace through an example of a city that's not actually in this list to see when we should stop the while loop and conclude that the city is not actually in the list at all. And the city I'm going to use is Istanbul. So let's go ahead and run the algorithm looking for that city Istanbul. I start off with a low of 0, high of 7, and that midpoint is 3. So I look in position 3, I see the city Essen, not Istanbul. Istanbul comes alphabetically after Essen, so I look in the greater half of the list by moving my low up to be mid plus 1. I'm going to calculate a new mid value, look in the middle of that list. I see Montreal. Montreal is not equal to Istanbul. Istanbul is alphabetically less than Montreal, so I'll again adjust my range appropriately. Now I'm down to just one element. I have a range that includes only one element, so high and low are the same. But that's okay, that's no problem. This is still a valid element that we can look at. This element is Lagos, and it is not equal to Istanbul, so I again conclude that I need to move my range. And in this case, Istanbul is alphabetically before Lagos, so I'll change my high value to be 1 less than mid, in this case making it 3. But now I'm kind of stuck. If you look at the array, all the elements are grayed out, so I've effectively ruled out every single element in this array. So how can the computer know this? Well, let's look down at our low and our high values, and something kind of funny has happened. Low is 4, but high is 3. So our low has actually gotten to be greater than our high value, which indicates to our algorithm, essentially, that we've exhausted all of the range that we can look at. So we've squeezed our range so tightly that high and low have actually switched places, and we're out of places to look. So at that point, we can conclude that the element that we're looking for is not actually in the array, and we can simply return this null value indicating we didn't find it. Okay, so now it's your turn again. Go ahead and finish off this code. I'm showing you a skeleton code here for that binary search algorithm, and you can go back to the algorithm and compare it to this code. One thing I'll point out is this method compare to that you might not have seen before. What compare to does is it compares a parameter object to a calling object. In this case, it will compare the city that we're looking at, the city name that we're looking at in that airport object, to the toFind city name. And it will return -1 if the calling object, so in this case toFind or Istanbul, is less than, alphabetically less than, the city object in the airport, so the parameter object. It will return 0 if they're the same string, and it will return +1 if the city we're looking for, the toFind, is alphabetically greater than the city that we passed in as the parameter. So we can use that to make our choice about whether we should go look at the smaller end of the array or the larger end of the array, or if in fact we're actually done. So use that information to complete this code. Pause the video, and I'll pick up with you again in just a minute. All right, welcome back. Let's fill in this code. There's not too much you have to write. Just have to write what happens in those 3 conditions, depending on where the thing you're trying to find is relative to that mid location that you're looking at. So in the first case there, that if compares less than 0, what that's saying is the element we're trying to find, the city name we're trying to find, is alphabetically less than the element that we're looking at in our array. So we need to adjust our range so that it's in the lower half of the range we were previously looking at. That means we need to bring high down. So let's change our variable high so that it's down at mid, but not just at mid, it actually needs to be 1 less than mid because we already looked at mid. So we'll subtract 1 from mid, and that's our new value of high. And then the loop's ready to start again. But if compare is greater than 0, that means the thing we're trying to find is alphabetically greater than the thing we're looking at mid. So we need to adjust our range up. In that case, we need to change our low variable. So we'll change it to be equal to mid plus 1. And if neither of those things are true, that means that compare is actually equal to 0, which means we've found the element that we're looking for. In which case, we can just return that 3-letter airport code. That's all we need to do here in the else statement is return airports at position mid dot get code. And that's it. That's the complete code. And there you can see it a little bit cleaned up. Now I just want to make one small comment about this code. Most people, if you show them this code, if they're sophisticated programmers, they kind of cringe. They'd say, oh, there's kind of a problem here. It's not really a functional problem. It's going to work correctly most of the time, except when your data is very, very large and your numbers for high and low get very, very large if your array is really, really big. What's going to happen is when you add high and low together, it's going to do something called overflow. You're going to get a number that's so big that you can't represent it essentially in Java in an integer value. So we can help guard against that situation by, instead of adding high and low together and then dividing by 2, what we really should be doing instead is subtracting low from high to get the range we're talking about, dividing that value by 2, and then adding it to our low to get it back into the correct range. So that's a better way to write this code. The other way will work as long as your numbers don't get too big, but to be a sophisticated programmer, start getting into the habit of thinking about things like this. You don't ever want your integer values to get too big when you can help it. So let's end going back to these same thought questions. So we said before, in a linear search, if we get unlucky, we're going to have to look through every single element in our array. And if there are a lot of elements in our array, like there are a lot of words in the dictionary, that can be a very, very slow, cumbersome process. So binary search is going to improve on that a lot. So you notice when we were tracing through the algorithm and when I was looking through the dictionary that I could eliminate essentially half of the remaining choices without even looking at them every step through the loop. That was great. And if I do this process repeatedly, what I'm doing is I'm dividing the number of things I have to look at in half every time. So I divide my original numbers in half, I have half as many. I divide that in half as many again, in half, in half, in half, in half, until I get down to just a single element that I'm looking at. And it turns out that the function that expresses that half, 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 half notion is the logarithm. It's the logarithm base 2. So if I compare the function that represents the number of elements that I have to look at in linear search, which is just equal to n, the number of elements that I have in my array, to that log base 2n function, I can see that these two functions behave very differently. So when my n is fairly small, say 2, 32, 1024, my log is also quite small, but the two values aren't horribly different. But as n gets very, very large, you can see that a huge difference emerges between these two values. N grows, and it can get pretty darn big. So it can get into the billions. There are about 7.2, 7.4, depending on when you're watching this video, billion people on the planet. So if you think about that in terms of n, 7.2 billion, and log n, which really isn't that much more than 30, that's a huge difference. And so these numbers are really going to make a difference when we're talking about extremely large data. So that's our first taste of comparing basically how long these algorithms take to run. And you're going to see much more of that in the next couple lessons on sorting.
So one thing I really struggled with when I was learning arrays and sorting algorithms was array bounds. I was getting exceptions everywhere. I didn't know what to do because I was getting so many exceptions. And one thing that really helped me was when I talked to one of my professors. He told me to draw, simply draw the array and make the numbers and everything, and go through each step of the algorithm and doing the sorting, the putting the indexes, And it was one thing that after that I didn't get any array bound exceptions, and it was perfect.
In the previous videos, Christine talked about some algorithms for finding information in large collections of data. What you saw is if the data is organized, then it's easier to do some of these algorithms. So in this video, we'll talk about ways of organizing data, and in particular, how to sort it in some order. And then you'll see some advantages of having it sorted. So let's think back to binary search, which is one of those algorithms for searching that Christine presented. Remember that when we do binary search, at each step of the algorithm, we reduce the number of elements that we need to look at by half. And so, all in all, we look at about log n number of steps if n is the size of the list of elements that we started. Okay, so what we remember now is that in order for binary search to work, the data in our list of elements has to be sorted by what we're searching at. So for example, if we're looking for the country code, the airport code of Essen, then what we do with this particular list is we look about halfway through our list of elements and, oh, we found it, excellent, Essen is right in the middle. All right, so that's kind of silly. Let's look for another element. Maybe let's look for Beijing. Let's look for the airport code of Beijing. And so again, we start by looking in the middle of our list of elements, and then we compare Beijing with Essen, and we see that Beijing is alphabetically earlier than Essen, and so we only need to look at the first half of the list because we have the list sorted in alphabetical order. So the order is really helping us out here. Now, think about this order. Sorting means that we list our elements in some order that we've decided ahead of time, and that is compatible with the search algorithm that we're trying to do if the sorting is done as a first step towards searching. So in particular, for this example, what we're trying to do is find a city name, and so we're sorting our data based on the first letter and then the second letter of the city. So we're sorting the city names in alphabetical order. Now, when you think about airports, the city is not the only piece of data associated with the airport. We also have a country that the airport is located in. And so it's conceivable that instead of sorting by city, we would want to sort our airports by, say, country. And so we'd want to organize the airports alphabetically according to country. There's nothing stopping us from doing that, but we have to think about why we want to do that. And so if we're looking for an airport in a given country, then it would make sense to sort all the airports based on the country name. And so that's why the sorting has to be compatible with the searching. Now, binary search, when Christine presented it, she showed you how it was absolutely necessary for the list to be organized in order for binary search to at all work. But before she talked about binary search, she already talked about linear search, which was this sort of simpler algorithm for looking through a collection of pieces of data to try to find one particular item. And with linear search, we didn't have to make any assumptions about how the data was organized. Remember that in linear search, we start at the beginning and we flip through one at a time, keep on going, looking for our particularly desired piece of information or piece of data. And that's fine. But actually what happens is if we happen to know that our information is sorted, then we get a performance payoff. So let's think about the array of airports in cities and countries, and let's think about trying to find the airport code for Istanbul, for example. What we might do in linear search is start with the first element of our array, Agra in India, and see, okay, that's not Istanbul, we have to keep on going. And then we go to Beijing, so that's not Istanbul, we have to keep on going. Chicago, Essen, Lagos. Well, if we were just doing linear search, we'd have to keep on going. Montreal, Quito, Sydney, and then only once we got to the end of the array, we would say, okay, Istanbul wasn't there, it's missing from our array, we can't do anything, we return null. But if we know that our array is sorted, we actually could have stopped a little earlier when I paused, right? As soon as we got to Lagos, we noticed that Lagos starts with L, which is alphabetically after I in the alphabet, and so if Istanbul was in our array, it would have to happen before Lagos. And so we don't have to look at the rest of the elements in the array to know that Istanbul is missing from this collection of data. And so what we get here is that if we do some upfront work, if we sort our array, if we sort our list, then in certain cases, our algorithm can run much faster. And we can have some logic built into our algorithm that says, if we're sure that our element that we're looking for is missing, we don't have to keep on going. We can stop right here and say, we've reached somewhere past the alphabetical location of where our element would be. We don't need to keep going. Okay, so far we've seen that sorting, which means arranging in order, can help us in both binary search and linear search. And there's actually another algorithm that is helped by having our data sorted. And so let's think about the problem of having a huge amount of information and we want to look for duplicates. Okay, that you can imagine all sorts of use cases for this, but for that, let's abstract away all the applications and just think about how we would approach this question. And so if we're given a whole bunch of unorganized data, this might be kind of hard and we might have to loop through the list a few times and figure out if there's any two pairs in the list that are the same. But what if we were willing to pay some upfront cost and sort the information first? Well, then we just need to do one pass over the information after it's sorted and look at consecutive pairs of elements and see if they're equal, because the duplicates would show up right after another in the sorted list. And so in the data that we started with, we see that it's pretty quick to find that 84 appears twice once we've sorted the list. All right, so I'd like to leave you with a few questions. What we've done in this video is given a taste for the algorithmic questions that we think about when we're developing new strategies for solving problems. So when we have an algorithm like binary search or like linear search, we like to ask ourselves, for particular cases, how fast will this algorithm run? How slow will it run? How many steps do we need to take? And how lucky can we be? So can the data or its organization, the input from the outside world, have an impact on the runtime of the algorithm? What's it going to be like in the worst case? What's it going to be like in the best case? And also, when we're developing algorithms, sometimes we're willing to spend a lot of energy at the beginning if we're going to be able to reap benefits from that upfront cost by having the later algorithms that maybe we do a lot of times be much more efficient because we did some overhead initial work. So in the next few videos, we're going to be talking about algorithms for sorting, and hopefully now you understand why they're so important, because having sorted data can really help all sorts of follow-on algorithms. So in this video, we're going to look at a specific algorithm for sorting data. And throughout the examples, we're just going to use an array of integers, but the same ideas and principles translate whenever we have information that's all of the same type, and we can compare pairs of information of that type. So by the end of this video, you'll be able to explain the selection sort algorithm and write code for it yourself. So let's get started, and let's think of a toy example. And it's always useful when developing algorithms to think of a specific concrete example that we can work through the steps of the algorithm with respect to this example, and then afterwards think about generalizing it. So let's think about this array of integers, and there's only 6 elements in this array, so we can probably do it in our head, but let's think about it systematically, how we would go about sorting these elements. And what we might do is, first of all, say, at the end, I want the smallest element to be in the first position in the array, the second smallest to be in the second position in the array, the third smallest to be in the third position in the array, and so on and so forth. And so let's look for the smallest element. So we're looking through our entire array, and we're looking for the smallest element. And lo and behold, we found it. It's 7. It's already in the first position. So we really don't need to do anything else to it. It's already where it's supposed to be. And so we don't need to ever think about it again. It's in place. It's done. And so now what we want to do is move forward and say, well, what about the rest of the elements in the array? What's smallest among those? Because whatever's smallest in the rest of the array is going to be the second smallest out of everything, and so we should bring it into the second position in the array. Okay, and so we have now 5 elements to consider, 1 less than before, and we're looking for the smallest element, and oh my goodness, we're lucky again. 16 is the smallest. It's already at the beginning. We don't need to do anything. Leave it in place. Okay, our problem is reduced further yet. Now we need to find the third smallest element overall, but that's just the smallest element in the remaining unsorted elements that we haven't thought about yet. And so we've got 4 elements to consider, and we want the smallest one. Now we see that it's 43. It's not the first one like we had in the previous 2 examples. And so what we need to do is to put it in its correct location, as it would be in the sorted version of the array. And so we need to swap it with 66 in order to move 43 to its correct location. Okay, and so we go ahead and do that, and now 43 is in its correct location for the sorted array. We don't think about it anymore, and we move on to look at the remaining 3 elements, look for their smallest, 51, and now we move 51 to its correct location where it's going to be once the array is sorted, and so we have to swap it with 66. Go ahead and do that, and now 51 is done, and it's in its correct location. We don't need to think about it ever again. And we look at the remaining 2 elements, look for the smallest among those, that's 66, swap it, and now we're actually done. Because for the last item, well, the only reason it's in the last position is because it wasn't the first smallest, it wasn't the second smallest, it wasn't the third smallest. It's already in its correct position. We can't compare it to anything else. And so when we've got to our last position in the array, we're actually done. We don't need to do anything. Okay, and so what that means is that we've got an algorithm, a series of steps that we can take algorithmically to perform this task. So we've got selection sort being described here as first find the smallest element and put it in location 0 in the array, then find the next smallest, put it in location 1, etc. In the previous video, we developed an algorithm for sorting a bunch of pieces of data and organizing them in some order from smallest to biggest. What we'd like to do in this video is translate that algorithm or high-level description of the strategy into Java. So what we're going to do is think step by step about how to go from natural language descriptions of the strategy to actual code. And so let's start by thinking about what that strategy even was. And so we talked about selection sort. So selection sort has as its general approach, first of all, we think about the smallest element overall in the entire array. And we look for that smallest element and we try to put it first, because that's where it's going to need to be at the end. And then we move on to the rest of the array, try to find the smallest element among those elements, and then put it in the second position overall, because that's its correct location at the end. And we keep going, and we keep going, etc. So let's think about how we can translate this approach to constructs that we know from programming. And so let's start by thinking about the big picture. And what we're doing in selection sort is we're looping through all of the positions in the array, and for each one of those positions, we're trying to find the true value in the sorted array. So for each position I, from the very beginning of the array all the way until the end, we're trying to find the right element to put in that position. But actually, not all the way until the end. Remember from the previous video, we talked about a small optimization that once we've sorted the first, all but last elements of the array, then the last element is going to be in the correct position because there's really nowhere else for it to go. Okay, so we've got that little tweak, and the big picture here, what's important is that we've got a for loop that looks over each position in the array and tries to find the right element there. And it's also useful to keep in mind that as we're going through this algorithm, we have an invariant property, a property that never changes, and that's that once we've worked on position 0, position 1, position 2, then the elements in those positions are sorted, and they're never going to change at all, no matter how many more steps we have to go or how big the array is. Those positions are done, and the correct elements in the sorted array are already there. And so what we have is this array where slowly, we're organizing the first bit of it, and then we're focusing on the very next position, say position I, and looking for what element to put there. So let's think about the body of the for loop and what we need to do in that body of the for loop. And so a way to think about that is to look for the smallest element in the not yet organized piece of the array, and whatever is the smallest element among the elements of the array that we haven't put in their correct position, that's the one that's going to need to be in position I. So we need to find the smallest element in all of the elements that remain, and then swap it with the element that's in position I so that that element is in its correct location. Okay, so let's formalize a little bit what it means to be in the still unorganized or unsorted part of the array. Well, those are all of the elements in position I through the end of the array, length minus 1. All right, so as you can tell, we're getting a little bit closer to coding up the solution. And what I'd like you to do now is pause the video and try to write the code. Welcome back. Let's work through it together and see if the code that we develop is similar to what you did on your own. So you probably declared a method that is going to be called something like selection sort and takes as input the array of values that we want to sort. Now, in this method, the way that I've designed it, we're not going to return any values. So the return is listed as void because what we're going to do is sort the elements of the array in place. So we're going to move them around in the array that we're given. And now remember that we have the outer for loop, and that outer for loop is looking at all positions I from the very beginning until the second last element. Okay. Now for each of those positions, we had to find the correct element to put in that position. And so now we have to implement that piece of the algorithm. And so what we're going to do is try to find the smallest element that has not yet been put in its correct location. And so we want to keep track of the index of that smallest element, the location of where that smallest element is in the list. So at the beginning, we think, well, maybe the smallest element is already in its correct location in I. So our first guess is that the smallest element is in the first place that we look at, namely position I. And then we want to step through all possible positions in that unsorted part of the array and compare the elements in those positions with the value of the element at our current best guess for where the smallest element is located. So we're comparing the element at position index min with the element at position j. And if it so happens that the element at position j is smaller than the element at the position which is supposed to record the smallest element, well, we need to update what we think is going on. Now, in this case, we think that the smallest element is actually in position j. And then we have to keep on going and keep on checking all of the elements to make sure that index min really records the position of the smallest element in that remaining piece of the array. So once we've gone through this inner for loop, what we have is index min recording the position of the smallest element in the remaining part of the array. And then the last piece of our algorithm is to put that smallest element in its correct location, namely in position I. And so we might have a helper method swap that we define somewhere else, and that swap method looks at the array vals and it swaps the element at position index min with the element at position I. And so what that would do is take the element that's supposed to be in position I and really put it there. Okay, and so what we've done here is we've gone from the high-level description of selection sort, and we've now gone ahead and implemented it using Java. All right, so before we leave this algorithm and say, whew, we've done it, pat on our back, we can stop thinking about it now, it's useful to probe further and always ask ourselves some questions. How do we know that this algorithm and this implementation always works, no matter what array we give it? And if we believe that it does work, how well does it work? And of course, as good engineers and scientists, we always want to do better. And can we? So in the next video, we'll talk about some of these questions. In the previous video, we implemented selection sort in Java, and then we stopped and thought about some questions to do with this algorithm and how well it performs. So far in this course, we haven't really asked ourselves whether algorithms are correct and how well they run, and so let's take a few minutes now to think about how we might even formulate answers to these questions. So let's think about correctness first. We had a problem, that of solving sorting an array, meaning organizing the information in the array. And then we had a candidate strategy, selection sort, that we think did pretty well, and we think that it really does organize the elements in the array. But if this was a really mission-critical problem that we are trying to solve here, it's not enough for us to just sort of say, yeah, I guess it's going to work. Hopefully there won't be any bugs, right? We want to be certain and convinced that our algorithm is really going to do what it's supposed to do, no matter what edge case we throw at it or how big an array we give it. And so let's think back to the high-level picture we have of selection sort and think about how that high-level picture can give us confidence that the algorithm works. So remember, what we're doing in selection sort is at each step through the for loop, we're looking at a new position in the array, and we're swapping into that position in the array the element that's going to be there when the array is really truly sorted. And so what we have is some initial piece of the array that is sorted and that keeps growing each time. And so as this sorted part of the array, the dark gray part of the array, grows with each iteration of the for loop, more and more of our array is in good shape. It's organized and it's sorted. And so by the time we finish the for loop and have gone through the entire length of the array, then our entire array is sorted. And so this argument that we just went through can be completely formalized and can be used to prove the correctness of selection sort. Okay, so we're convinced that it works, but how well does it work? And what does that even mean? And so the question of performance is a really tricky one, but a super critical one. And it makes the difference between a very sluggish computer that no one really ever wants to use because it takes seconds between when you click a mouse and when it actually responds, to a super snappy computer that everyone is really happy running apps on and maybe even multitasking. Because performance we can measure with time, we can measure with resource use, and the experience of how an algorithm runs makes a big difference to how far we can push that algorithm and how big a data set we can expect it to work on. So it turns out that selection sort, even though it's correct, doesn't do so well when we think about its performance. It turns out to be a very slow sorting algorithm. Now, we won't talk about the details of what it means for one algorithm to be slower than another and how we can compare algorithms when their performance might depend on their input in this course. But we will talk a lot more about it in the next course. And so stay tuned. It's a beautiful theory of computation and complexity that we'll get to in a little while. Now, what I want to mention, though, is that aside from performance issues, and somewhat motivated by performance issues, we're always on the hunt for other algorithms for solving even the same problem. So we had this sorting problem, and we had one solution for it, namely selection sort. But even if we didn't know that it was kind of a slow one and maybe not so great, we'd still be interested in finding other algorithms that solve sorting. And that motivation for finding other algorithms comes from recognizing that in the real world, different contexts might require different properties from our algorithms. Sometimes we might have a nearly sorted list, a list that is usually pretty organized, but occasionally we add on to it, maybe as new computers join a network or as new people join a team. And so we might want an algorithm that responds really well to almost sorted data and is really fast in that situation. On the other hand, we might have a context where our data is going to be coming from all over the place and is not organized at all, but maybe is not going to change too often. And so maybe we have a different algorithm that doesn't respond so well to dynamically changing data, but does really well even if the incoming information is completely unorganized. So even if one algorithm is often slower than the other, it might still be useful for other reasons if we know something about the problem that we're solving and the real-world context that we live in. In the next video series, what we're going to be doing is thinking about other algorithms for sorting and foreshadowing some of the other techniques that we'll be thinking about in the future courses.
Hi, and welcome back to our module on sorting. It's time for another one of these concept challenges. You've already got a good feel for these. You know that you're going to try to solve the problem yourself. You're going to discuss this if you have other learners around you. You're going to watch our UC San Diego learners talk about the problem, and then you're going to see my explanation of the answer. So you've already seen the selection sort algorithm. You know that selection sort goes for every element in the array and essentially looks through the unsorted portion of the array, finds the smallest value, and adds that to the next smallest value and adds that into the array. So if I have two arrays, is sorting faster on one or the other or neither? Go ahead and think about this, and we'll come back.
Hi, I'm Luis.
I'm Melissa.
I'm Gustavo.
Well, I think it would take the same amount of time because there is one for loop that iterates over the entire thing.
For me, I thought it would be answer A because why would you have to sort something that's already sorted? Wouldn't it take least number of steps, you know?
Yeah, I thought the same thing. Like, if it's already sorted, but like the computer doesn't know that, so you have to go like to the end.
Hi, I hope the UC San Diego Learner video was helpful. What we'll do now is just walk through both of these arrays and apply a selection sort to each of them. So in the first array, we're going to do a pass. We're going to look at all the elements, and we're going to see what the smallest element is. And this is going to require us to look at essentially 6 elements. It's going to require us to look at all 6. And then we're going to find that 7 is the smallest, and we're going to put 7 in the very first spot, which is where it is already. In the next iteration of the array, we're going to look at the second element in the array. And we're going to see what's the smallest element. We're now going to scan. We're going to look at all 5 of these. And we're going to find that 16 is the smallest and keep it there. When we move to the next element in the array, we're going to scan the remaining. So I'm going to have to look at all 4 elements here to find that 43 is in fact the smallest, and then I'll swap them. So 43 now moves into the place that 66 was at. I'm going to move to the next element in the array. I'm going to look at this element along with the remaining elements to find the smallest element. It's going to take me 3 steps to find 51 as the smallest. And then I'm going to swap 51 and 66. In the next iteration of the array, I'm now going to be looking at 97. I'm going to have to look at 97 and 51 and 66 to find out that 66 is the smallest. That takes 2 steps. And now I'm going to swap 66 and 97. And then the last step of the array, I'm going to look at 97 to see if it is the smallest element of the remaining array. It is, and we're done. Now, that did seem like it took a number of steps because I was having to swap so many elements. But what's going to happen with a sorted array? Is it going to behave that differently? Well, with the assorted array, it's going to start at 7. And it's going to see, is 7 the smallest element? And it's going to look at all 6 elements again. It's then going to move on to 16. It's going to find the smallest element. It's going to have to look at 5 elements to do that. It's then going to look at 43, and it's going to say, is 43 the smallest? And it's going to have to look at all the remaining elements, find that 43 is, in fact, the smallest. It's going to move to 51, do the same thing. It's going to take 3 steps. It's going to move to 66, take 2 steps. It's going to move to 97 and take 1 step. So we haven't done as much swapping, but we've essentially taken as many steps. And what this really leads us now to thinking about is how do we define faster? So we can see that both of these arrays essentially took the same number of steps. But is that how we define faster? Well, if you're looking at a high level, the same number of steps means they essentially take the same amount of time. Now, some of you may be thinking, well, wait a second. I think if you look at the really nitty-gritty details, you can see that swapping only sometimes happens, or maybe this if statement only executes sometimes and it doesn't execute other times. And now you're starting to argue about individual machine instructions. But what view do we want to have? Well, for the most part, we tend to have a really high-level view when we look at algorithms to say whether or not one is faster than the other. In this case, we'd actually say that these are going to run the same speed regardless of the contents of the array. But we're going to spend a whole bunch more time in the next module talking about defining performance, defining how to compare different algorithms, and we're looking forward to doing that with you then.
So in the previous video, we talked about selection sort, which was one algorithm for sorting data. By the end of this video, you'll have seen another algorithm for sorting data, and we're going to play a little game. Instead of talking about the algorithm at the high level, what we're going to do is present some code that I promise you will sort the data, but what I'd like to do is work with you to figure out how to describe that code in high-level terms. And this is a really useful skill that helps with reverse engineering code and also working in big teams when other people are implementing different pieces of the code. And so then once we'll have traced the code and figured out what it does, we'll be able to describe alternate algorithms for sorting and compare their relative merits. So let's start with a code and let's see what we have here. So we're going to call this method mystery sort until we solve the mystery together. And at this point, there aren't a lot of comments to help guide us. We're just seeing some Java statements. And so let's see what we've got here, and we'll step through with a particular example. So we see that we've got a variable being declared, and we've got a for loop that does something and has an inner while loop. Okay, doesn't help us so much so far, but let's work through an example. And again, it's really useful to work through some concrete examples when we're working through these questions to help guide our understanding. And then later we want to generalize, we want to think about the full generality, but first let's make sure that we understand what's happening at a small scale. Okay, so we're working with the array of integers that we talked about last video as well. So we've got 6 elements, and we're going to trace through and step through the execution of our mystery method to see what happens. Okay, so at the beginning in our for loop, we are initializing the value pause to 1. And what's going to happen the first time we run through this for loop is that curInd, which you might guess means current index, is going to be initialized to the same value as position. And so what we see on the left of the code here is that we've got a memory model. So think way back to the earlier module, one of the first modules that we did in this course, where we talked about using memory models to help us reason through the changing values of variables as we run through code. And so we've got boxes for each variables, and at the beginning, each of those contains the values of the initial values of the variables, namely 1. Okay, now what happens is we look into the condition for the while loop, and we see, do we have to execute the body of the while loop? Well, we're checking whether the current index is greater than 0. So yes, it's 1. And we want to check whether the array element at position curIndex is less than the array element at position curIndex minus 1. So curIndex is 1, curIndex minus 1 is 0. So we're comparing the numbers 7 and 16, and we're checking whether 16 is less than 7. It's not, and so we don't need to execute the body of the while loop. We go right back up to the top of the for loop after incrementing the pause variable or position variable. Okay, so now position is 2, and the curIndex is initialized at the top of the body of the for loop to be 2. And again, we have to check the condition for the while loop. And we look, is the current index positive? Yes, okay. And now we want to compare the value of the array element at position 2 and compare that to the value of the array element at position 1. And basically look at what's happening here. We're asking whether they're in the correct relative position to one another. We're asking whether 66 is less than 16 or 16 is less than 66. And in the array as it stands right now, 16 and 66 are in the correct relative positions, so we don't need to do anything. All right, so far we haven't done much except for updating our helper variables pause and curInd, and we do that once more. Okay, we step up to the next execution of the body of the for loop, and so now the pause variable has value 3, and the current index has the same value of that at the beginning. And now we check whether the array element at position 3, which is 43, is less than the array element at position 2, which is 66. And it is. So 43 is less than 66, which means that these two array elements are out of order. They need to be swapped in order to be in the correct location relative to one another. And so that's what's happening in the body of the while loop. We're swapping these two positions. And we also need to update the current index variable. Okay, so we've swapped the two positions. Now we have 43 in position 2, we have 66 in position 3, and the current index is 2. And we go back to the top of the while loop and we check whether 16 and 43 are in the correct relative positions. They are, so we don't need to do a thing. In this execution of the body of the for loop, we increment, pause, we update curInd, and we go again. And now we're checking whether 66 and 97 are in the correct relative position. They are. Awesome. Keep going. Update pause, update curIndex, and we check whether 97 and 51, the elements at position 4 and 5, are in the correct relative position, and they're not. 97 is greater than 51, and so what we need to do is we need to swap them. We update the current index, and now we check again, and what we're checking is whether 66 and 51 are in the correct relative positions. They're not, so we need to swap them and update current index. Okay, current index is now 3. 51 and 66 are in the correct relative positions. And now we check whether 43 and 51 are in the correct relative positions. And they are. So sweet, we're done. Okay, so what that means is at each point of the execution of the for loop, at each time we've gone through the for loop, what we know is that we've guaranteed that an increasing part of the array is going to be in sorted order. So if you think about what happens and what the array looks like at the end of the body of the for loop when pos equals 1, what we have here is that 7 and 16 are in their correct final locations. Okay, at the end of position 2, we have 7, 16, and 66 at the head of our array. Now these are not going to be the correct final locations of each of these elements. At the end, when we finish sorting the array, 66 is not going to be in that third position. But what we do know is that the first 3 elements of the array at this point are in the correct relative order with respect to one another. And so what we're doing is we're growing an array that is sorted, even though there might need to be some elements that get put into that array later on as we go through the rest of the algorithm. Okay, so at the end of the for loop, when we've got position equals 3, what we have is that we have a list of 4 elements that are in correct sorted order. Then we have 2 elements that we haven't worried about yet, and they may need to go somewhere and nudge some of these sorted elements around, but these 4 elements will never switch position relative to one another. Okay. So what we have here is a beginning of a description in higher level terms of what this code is doing. And this transition between looking at the code and being able to trace its execution one step at a time to being able to describe it in higher level terms is a really, really hard cognitive leap, but that is really important. And so it takes practice. Keep at it, work on it, and you'll see you get much better at it. And one of the key strategies for doing it is to take it little pieces at a time. Okay, and so what we're thinking about is we're thinking about this for loop where we're growing a piece of the array that is in relative sorted order. So it's sorted, and even though the elements in this part of the array may not be in their correct final location, which is different from what we saw in the previous video, by the way, they are still always going to be in the same relative order to one another. And then we're increasing the amount of the array that is in this relative sorted order each time. Okay, and so what's happening here is in order to increase the piece of the array that's sorted each time, within the body of the for loop, we're finding the correct location of the next element that we haven't thought about up until now, relative to the first I-1 elements. And so then we want to nudge it into the sorted part of the array, nudge, 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 until it gets into its correct relative location, leave it there, and then all of a sudden we have a nice bigger part of the array that is sorted, and we can go look at the next element that we haven't looked at yet. So this is actually a well-known sorting algorithm. It's a mystery no longer. It's called insertion sort, and that's because we keep inserting new elements into a previously sorted array into the correct position relative to the other elements, and then this sorted part grows and grows. All right, notice that this algorithm is quite different from the previous algorithm that we talked about, the selection sort algorithm that we talked about in the previous video. And that's because in the insertion sort algorithm, we have the elements that we're taking care of, they get taken care of in a different way. We don't immediately put them where they're going to be and they stay in that position forever after, and we know their location in the complete array from that point on. Rather, we're looking at relative locations and relative ordering. And so we have 2 different algorithms, but they share some features. And so with each algorithm, as we go through it, we ask similar questions about correctness and performance. And similarly, we would want to compare the selection sort algorithm to the insertion sort algorithms and other algorithms as well as they come. So with insertion sort, the mystery sort that we were working through just now, how do we know that it's correct? Well, the argument that we were making before about the part of the array that is in relative sorted order, growing and growing and growing until we get to all of the elements in the array, well, if we were able to make that precise, that would be a convincing argument that this algorithm is correct, because no matter what we start with, at the end we get all of the elements in the array in sorted order, and that's what we want. So then there's a question of, can we do better? And when it comes to algorithms, well, we always want to do better, but what does that even mean? And so the question of goodness of an algorithm has a few levels to it and has a lot of complexity to it. So the baseline lowest bar of goodness that we want is that an algorithm does what it's supposed to, that it's correct. Okay, both selection sort and insertion sort have met that bar. But then we might want more. So for example, we want to be able to tackle huge reams of data. And so we might want our algorithms to be really fast. And so we want to be able to process billions and trillions of pieces of information very efficiently. And so we need to think about, how do we measure the speed of an algorithm? How do we talk about its performance in terms of time in general, when we don't a priori know what our data looks like? We want it to be good for all sorts of pieces of data. And so that will lead us to things like worst case analysis and asymptotic analysis that you'll see lots more about in the next course of this specialization. I want to also mention that there are other measures of goodness of an algorithm. For example, we might not want to waste a lot of memory while performing the execution of an algorithm, and so we might want to be very resource sensitive and not use up a lot of space. And so there's a notion of space complexity that we would want to think about as well. And then we also might want to think about other properties that the algorithm could preserve or not preserve. So for example, if we want to sort a lot of data on different dimensions, so you can think back about the airport data, we want to sort first by name of country and then by name of city, then we would want our algorithm to behave in a way that's compatible with doing multiple pass sorting. And so we might want to restrict which algorithms we consider based on only those that have properties amenable to our use case. So goodness and can we do better are always relative questions relative to how we plan to use the algorithms. Algorithms are actual living, breathing objects you can think about. They don't exist in a vacuum. We want to use them. And the measure of their goodness is only in terms of how we can use them and what they can tell us. In the previous two videos, we've seen two different algorithms for sorting data. Now, that's just the beginning, the tip of the iceberg. There are many, many, many algorithms for sorting. We're not going to cover all of them. What you do want to keep in mind is that it's possible to optimize these algorithms tremendously depending on the application. And that takes a lot of work, but if you actually just want to use sorting, you don't need to write the sorting algorithm yourself. So by the end of this video, you'll be able to use the predefined Java method to sort, and you'll be able to explain the properties of this built-in method. Because whenever we use a tool, we want to be able to know both its functionality and its limitations. So it's useful to be aware of what the built-in method is actually doing. So as a reminder, we've talked about both selection sort and insertion sort. We talked about why each of these give correct algorithms for sorting data. And we also talked about some potential limitations in terms of the time that it would take for these sorting algorithms to actually work through a lot of data. And we've talked about how to write the code for these sorting algorithms. But we don't want to write that code each time. And so here's this code snippet of how we might be able to sort some data as part of a larger method without actually writing the sorting ourselves. We do need to use some built-in utilities from Java, and so that's why the import method is up top there. And then once we've built a list of, for example, integers, then all we need to do is call the sort method, collections.sort, on that list of integers. And then lo and behold, if you run this, you'll see that our numbers are sorted. And so it's this one-line method that is kind of a cheat because we haven't actually implemented sort method. But if what we're focused on in the particular method that we're writing is not the sort, but that's just sort of a helper piece of our code, then it's useful to go to the library and pick out that built-in method and use that instead of having to implement it each time. The reason it's useful is that we get the benefit of a lot of other people's hard work. Turns out that in this built-in method, what's being implemented is an algorithm called merge sort that's then been tweaked and optimized for various reasons. In particular, it's been made to be super fast, and we'll talk again in the next course about what we mean by a fast algorithm and how we can compare algorithm speeds to one another. But merge sort is known to be provably faster than selection sort and insertion sort in most cases that we care about. And in particular, it's really good for nearly sorted data. If you think back to selection sort and insertion sort, trace through how those algorithms would behave if our data was already almost sorted. And what you'll see is that one of them does better than the other in responding dynamically to the kind of data that's being presented. And so it's really useful if we know that we're going to maintain, for example, our list of airports, and every so often a new airport is going to come up and we want to add it to the list and then resort the list to make sure that it's in the correct location. We want our algorithm to be able to be responsive to that and be fast when our data is almost sorted and we just maybe have a couple of things out of place. The optimized merge sort that is also built into Java has an additional property in that it's stable. So that means that if we run sort a bunch of times on the same data, and we have a couple of pieces of data that are duplicates in some sense, they won't switch orders as we run sort again and again and again. And that can be useful if we want to, for example, sort the data on different dimensions. So what you'll see is in the project you'll be using some sorting and searching techniques, but what we encourage you to do is to use the built-in sort and not have to rewrite sort on your own so that you can make use of these great properties that the optimizations have given us. In the previous video, we started talking about how to use the built-in sort that's available to us in Java. What I'd like to do now is to think about how to generalize that technique for more complicated objects. So by the end of this video, you will be able to define and use the comparable interface in Java so that we can have access to that built-in sort method. So if you remember last time, what we talked about is how to use collections.sort and then feed in a list of integers and somehow magically get the list returned to us as a sorted list. Now, what we observed happens when we use this method is that we're using the built-in merge sort. And the beauty of that was that we didn't have to implement merge sort ourselves. The issue, though, is that the list that we gave it was an integer list. So all of the values are numbers. But sometimes the objects that we want to sort, the data that we want to organize, isn't just numbers. Maybe it's more complicated objects. And so what we'd like to do now is think about using this built-in functionality, but for collections of non-integers. And so, for example, we might want to sort airports. So remember back to the beginning of the module and the motivating example that we've been talking about. We have an array of airports, and each of the array elements are references to airport objects. And what we'd like to do is to sort this array based on the city of the airport. Okay. So if we try to just go ahead and in our airport class define a method within the main method that just says, let's sort our airports. So we have an airports list and we're going to go ahead and sort it. Then we can hope for the best and try to compile this, but unfortunately we're going to get a big old error message. And the reason for that error message is that airports are kind of hard to sort. We don't know how to compare two airports. So this is where the comparable interface comes in. And the comparable interface says, I will be able to give you access to merge sort and all of these other built-in functionalities like sorting in Java if you only tell me how to compare two object instances of your class. And so, for example, if we think about the object that has the city Montreal in Canada with a particular airport code and the airport object that we have that's initialized to the airport in Lagos, then we might want to compare these two and say M comes after L in the alphabet. And so when we're thinking about the city names, then the object that corresponds to the airport in Montreal should come after the object that corresponds to the to the airport in Lagos. On the other hand, we might want to organize our data based on country names rather than city names. And so then we might focus in on a different field and look at the instance variable for country. And in that case, we see that Canada, starting with a C, comes earlier in the alphabet than Nigeria, starting with an N. And so we'd want our objects to be organized a little bit differently. All right, so how do we do that, and how do we tell Java this order? Well, if our class implements the comparable interface, and we say that by adding that keyword to the class definition, then our objects in that class will be able to be compared to one another. Now notice that special word that's after comparable, we've got the angle brackets and airport, and that's saying that we're specifying what kind of objects we're going to know how to compare. And this is using generics. Okay, so if we've told Java, we've promised that we're going to implement what's needed for a comparable class, what that's saying is that we have to fulfill the promise of the interface. And the interface comparable says you must implement a compare_to method. And the compare_to method has to be called by an object in that class, and it's going to tell us how to compare that calling object to an input other object. Okay, so let's think about how we might do that and think about what functionality we want. So we're going to return an integer, and that integer should demonstrate the relationship between the calling object and the other object. So if the calling object is supposed to be smaller than the other object, then the integer that we return is negative. If the calling object is supposed to be sort of the same size as the other object, then we should return 0. And if the calling object is bigger than the other object, then we're going to return a positive number. And so what you might think about is the comparison method is something like doing subtraction, subtracting the calling object minus other object. That's sort of the reference that we have for why these integers are returned the way they are. Okay, so what we'd like to do is to return some number when an airport calls compare to another airport. And what we're comparing to is using the city name. So we're going to have access to the city name instance variables in each of these objects, and we'd like to order those city names. But city names are just strings, and strings are objects, and strings can be compared because we can sort strings by alphabetical order. And so what we're going to do is really just be kind of lazy and say, someone else compared these two strings, and we just want to return the result of that comparison. So what we're returning here when we're comparing two airport objects is what happens when we compare the city name of our current object, the calling object, as compared to the city name of the other object. Okay, so let's try it out. Once we've implemented this compare_to method, what happens when we go ahead and try to sort a list of airport objects? So we go back to the main method of our airports class, and we call collections.sort on the list of airports. And now, beautifully, we get as our output the list of airports in sorted order based on the city name. So Agra in India comes first, and then Beijing in China, etc., etc. Cool. One more thing. When we first thought about this problem, we said we can compare airports in some different ways. Maybe we can sort based on the alphabetical order of the city name, but what about the country name? So what do we need to do in order to change our compare_to method in order to reflect the order of the country names? Well, we just need to change the body of that method to, instead of using the getCountry getter method for the instead of using the getCity getter method for the city name of the airport, we're using getCountry. And that's really all there is to it. We just need to change that one line of code, and when we run the same collections.sort method in the main method of the airport class, all of a sudden our list is ordered based on the country names, and we have Australia first, and then Canada, and then China, etc. And so at this point, you're ready to dive back into the project and use the comparable interface and the compare_to method to compare markers in your project.
Hi again, and welcome back to our module on sorting. At this point, you've seen two different sorting techniques, so we're going to see how well do you really understand both of them. You're very familiar with the concept challenges at this point. You know the approach is you're going to pause, think about the question, answer it yourself, discuss it with people if you have them around you, watch a video of UC San Diego learners learning about the material, and then confirm your explanation with our explanation. So without further ado, if you look at these two arrays, in the top array we have the initial setup, and the array below that we've got the state of the array after 3 loop iterations. Which sorting algorithm could have been applied to reach this state?
Hi, I'm Melissa.
Hey, I'm Ken.
Hi, I'm Michael.
So for this one, I thought it definitely can't be selection sort because the 1 will be at the beginning, right?
I was actually kind of confused in this question because I actually picked D. I thought it was both of them since like the first couple of elements are already sorted.
Yeah.
And we're sorting the elements. Shouldn't that be correct for both?
I'm actually pretty sure it's insertion sort because what happens is through the first iteration or the first loop, it checks the 4 and the 7, no switch, goes to the next 2 elements, 7 and 2, switches the 7 and 2, and then actually goes back and checks the 2 and the 4 and the 2, and makes that switch. And that would be 3 loop iterations, and that would be exactly what the bottom array is, and what she said, it can't be selection sort because the 1 would be at the beginning for selection sort.
And for the insertion sort, it never made it to the 1.
To reach this state. Hi, I hope the video with the UC San Diego learners was helpful. What we're going to do is just walk through both insertion sort and selection sort and see the state of the array after 3 loop iterations. With insertion sort, the key idea here is that you always keep the left side of the array sorted, but you're only looking at essentially the left elements. So the first pass, all you're going to do is look at element 4 and say, is 4 sorted? It sure is. Next iteration of the loop, it's going to look at 7, and it's going to say, where should 7 be in relation to 4? Well, it belongs in the same place. So the third iteration of the loop now is where it gets interesting because it's going to look at 2. And it's going to say, where does 2 belong relative to 4 and 7? And it's going to move 2 down all the way to the first place, and then 4, and then 7. So after 3 iterations of the loop, this would be the state of insertion sort. And this is what the question was asking for. So the right answer here is insertion sort. But let's talk through what selection sort would have done. Selection sort is always going to be looking through the remaining part of the array to find the smallest value and put that where we're currently looking. So with selection sort, you're going to be looking through the entire array at the start, and you're going to look to see that 1 is the smallest element. And then you're going to place 1 right at the start. Then you're going to look through the remaining part of the array, and you're going to find that 2 is the next smallest element. You're going to place that next. And then you're going to look through the remaining part of the array again. You're going to find that 4 is the next smallest element. You're going to swap that in. And this will be the state of the array after 3 iterations of selection sort.
All right, so it's time to get started on your project. In this project, there are 2 parts. The first, you're going to write some code to sort the earthquake data. And the second part, where we think you're going to have a lot of fun, is to add your own extension to this whole project that you've created throughout this course. So before we talk about what you're actually going to do for the programming assignment, let me say a few words about how you're going to submit this programming assignment. It's a little bit different from previous modules. So if you go over here to your week view on Coursera, these are the things you're learning this week. And down here at the bottom is, of course, the Check Your Knowledge lesson, which is the last lesson, just like it is in every assignment. And right now you're watching the programming assignment walkthrough. Of course, coming next is the programming assignment instructions, which I'm going over in this video. But let me talk to you about how you're going to submit the assignment. So as usual, what you'll do is you'll do a quiz, just like in previous modules, to check your understanding of the concepts and to make sure you've actually done the programming assignment correctly. But in this module, you're going to have an extra piece. Rather than just taking a quiz, we're actually going to ask you to submit a peer review assignment talking about part of your programming assignment for this module. So what's a little weird is you're going to see 2 peer review assignments, and they're right next to each other. So you can see one right here and the other right there. One of them has a due date, meaning that's the one that's actually due for a grade. The other one that you see right before it, this one is just basically a non-graded, kind of optional peer review assignment,
and it's actually identical to the graded version of the peer review assignment. Now, you may be wondering, why do we have an optional version of the assignment that's identical to the sort of required version of the assignment? And the reason for this is that we want you to be able to get preliminary feedback from your peers in a quick turnaround so that you can get some feedback to incorporate into the submission that you ultimately submit for a grade. So this version, this ungraded peer assignment, is optional, but you can use it to submit your peer review assignment, get some quick feedback from your peers, make some improvements on your peer review assignment, and then go ahead and submit it for a grade down here by the due date. So now that we've looked at how you're going to submit your programming assignment in this module, let's go back and take a look at what you're actually going to do.
So the first steps are the usual steps. We want you to find and open the starter code and take a look at it. Then we're asking you to compare our implementation to yours. And this is really more of a reflective question. How does what we did in the Module 5 implementation compare to your Module 5 implementation? Be ready to reflect on that in the quiz. The next part, you're going to be implementing the code to sort. So the first step says to implement the comparable interface in Earthquake Marker. So we go over here to the Earthquake Marker file, and you can see that there's a to-do in here that says implement the comparable interface. And so you need to figure out what that means. How do we change the class header so that it implements the comparable interface? And then, of course, there's a second part to implementing the comparable interface, which is to implement all the methods in the interface. In this case, it's just this one method, compare to, and you'll see a to-do down here as well. Remember that compare to compares the calling object earthquake marker to the parameter earthquake marker and returns either a negative value, 0, or a positive value, depending on the relationship between those two objects. And it's going to be up to you to figure out how to do the comparison and return the correct value so that you get your earthquake sorted in reverse order. All right, and then the second half of that piece is to implement this method in Earthquake City Map. So we go back over here to Earthquake City Map, and you'll be implementing a method. We can click here to this little to-do. We're going to implement this method sort and print. And that takes a parameter, the number of earthquakes we want to print, and it's going to print out the earthquakes in reverse order of their magnitude. So it's going to be the strongest magnitude first, and then weaker and weaker. So you're going to implement that method here, and then you'll want to call it from the setup method. So you'll be adding your call somewhere in here in the setup method. And then you can see here that the second part of the project, the main second part, is to add your own extension. So this is where we want you to get creative, have a lot of fun, and in case you don't have any ideas, we hope you have some ideas, but if you don't, that's okay. We have some ideas to seed your creativity. So there are two kind of major directions you could take this in. You could extend the functionality of your earthquake application, so continue to work with the earthquake data, and you're all set up for that. And we've got a number of different suggestions here that you might choose to implement. And then the other direction you could take is you could incorporate new data sources. So we have a couple of new kinds of data already prepared for you. So one is airport and airline route data that you can find over here. If you go here into the data directory back in Eclipse, you can see that we've got this airports.dat, and then we have a routes.dat file. And we're also providing you with some code that will give you a demo of this. So we've got this airport map and airport marker, so you can get a sense of how to use those data files. So you can work with that data source, or you can work with data from the World Bank. We've got the life expectancy data that Mia showed you way back in the first module on GUIs, and we've got some sample code that implements basically the example that she implemented from that module, and you'll find that over here in the lifeexpectancy.java file. So decide which direction you want to take, decide what you want to do, play around, have a lot of fun, and then after this, what you're going to do is you're going to be submitting this, in addition to taking the quiz, you'll be submitting this as a graded peer review assignment. So you can see, you'll get to see what all your fellow MOOC mates have done with this project. So have fun, and we really look forward to seeing your extensions.
Congratulations on completing our course. You've created a large project, and I hope you enjoyed it.
Think back to everything you've learned in this course. You've learned about object-oriented programming, you've worked with class hierarchies, inheritance, and polymorphism, and you've created an interactive graphical user interface. We hope you're really proud of your project.
And we hope you'll join us for the second course as well. We'll be thinking about the performance of the programs that we build, and we'll be incorporating data structures as the programs get even more complicated and interesting. So we hope to see you there.